the universe holds, striving to grasp even a fragment of the answers that lie beyond our reach. When matter, energy, or information enters a black hole, we encounter one of modern physics' most fascinating paradoxes. Imagine a particle carrying specific information about its properties, such as position and velocity. As this particle crosses the event horizon, the point of no return, this information seemingly disappears from our observable universe. This scenario raises fundamental questions because quantum mechanics asserts that information should never be lost. The apparent destruction of information in black holes challenges our comprehension of reality's underlying nature and the intricate relationship between gravity and quantum mechanics. This conundrum, known as the information paradox, remains one of the deepest puzzles in physics. Stephen Hawking once hypothesized that information falling into a black hole could be lost forever, a notion that contradicts quantum determinism, which states that the past and future states of a system should always be deducible from its present state. However, recent theories, including advances in string theory and the holographic principle, suggest that information may be preserved in some form. One idea proposes that information is encoded on the event horizon itself, similar to a hologram, preserving details without losing them inside the black hole. Another intriguing possibility is that information could slowly leak out through Hawking radiation, albeit in a highly scrambled form. This complex interplay between quantum mechanics and general relativity continues to fuel research and debate, keeping the mystery alive. Supermassive black holes, with masses ranging from millions to billions of times that of our Sun, are enigmatic giants residing at the centers of most galaxies. Their formation remains an active area of research, with several compelling theories woven into a fascinating narrative. One leading hypothesis suggests that these colossal black holes began as smaller, intermediate-mass black holes. Over cosmic timescales, they grew by voraciously consuming gas, dust, and even entire stars from their surroundings. This accretion process, combined with mergers between black holes, gradually built up their immense sizes. Another theory posits that the seeds of supermassive black holes may have formed very early in the universe's history, just a few 100 million years after the Big Bang. In these primordial conditions, giant clouds of gas could have collapsed directly into large black holes, bypassing the typical stellar-sized black hole phase. This direct collapse process might explain how supermassive black holes appeared so early in the universe. Additionally, galaxy mergers significantly contribute to the growth of these black holes. When galaxies collide, their central black holes can eventually merge, forming an even more massive black hole. The merging of galaxies often funnels large amounts of gas toward the center, providing additional fuel for the black hole to grow rapidly. Over billions of years, these gravity titans sculpt the galaxies around them, influencing star formation and the dynamics of galactic cores. Understanding their formation not only unravels the mysteries of these cosmic titans, but also offers critical insights into the evolution and structure of the universe. Hawking radiation, proposed by physicist Stephen Hawking in the 1970s, is a groundbreaking concept that merges quantum mechanics with general relativity to explain a previously unimaginable phenomenon. Black holes can emit radiation, and over exceedingly long timescales, gradually evaporate. Near a black hole's event horizon, quantum mechanical effects come into play. According to quantum theory, particle-antiparticle pairs are constantly created and annihilated throughout space, even in the vacuum around a black hole. Occasionally, these pairs form right at the event horizon. In some instances, due to the intense gravitational forces, one of these particles may fall into the black hole while the other escapes into space, carrying away some energy from the black hole. This escaping particle is what we detect as Hawking radiation. Over incredibly long periods, this process causes the black hole to lose mass and energy. As it continues to emit Hawking radiation, the black hole gradually shrinks, a process known as black hole evaporation. The full evaporation of a black hole is a slow process for most black holes, especially the supermassive ones. This occurs over timescales far beyond the current age of the universe. However, for smaller black holes, the loss of mass can accelerate dramatically as they shrink, leading to a final burst of radiation before they vanish entirely. Hawking radiation not only provides a mechanism for black hole evaporation, but also bridges the gap between quantum mechanics and Einstein's theory of general relativity. It represents a crucial step toward understanding the deeper connections between the laws governing the tiniest particles and the largest structures in the cosmos. The idea of harnessing energy from rotating black holes isn't just a concept confined to science fiction. It's grounded in fascinating theoretical physics. Rotating black holes, also known as Kerr black holes, possess enormous angular momentum and gravitational energy. The possibility of tapping into a black hole's immense power was first proposed by physicist Roger Penrose in the form of the Penrose process. This process involves a particle entering the ergosphere, a region just outside the event horizon of a rotating black hole where space-time is dragged around at astonishing speeds. Within the ergosphere, it is theoretically possible to split the particle into two. One part falls into the black hole while the other escapes, carrying off more energy than the original particle had. In doing so, the process extracts a fraction of the black hole's rotational energy. Another intriguing concept is the Blandford-Znajek process, which suggests that magnetic fields surrounding a black hole could interact with its rotation, channeling energy out in the form of powerful electromagnetic radiation. Jets of high-energy particles, often observed emanating from the regions around supermassive black holes at the centers of galaxies, could indicate such energy extraction mechanisms at work. While these theoretical methods present tantalizing possibilities, they come with immense practical challenges. The extreme conditions and vast scales involved make actual energy extraction a daunting, if not currently impossible, engineering feat. Nevertheless, studying these processes enriches our understanding of black hole physics and the incredible forces at play at the edges of our scientific comprehension. While we may be far from building black hole power plants, these ideas stretch the boundaries of what we consider possible, propelling us toward deeper inquiries into the universe as most enigmatic entities. Should you find yourself falling into a black hole, your experience would vary greatly depending on the black hole's size and mass. For a stellar mass black hole, typically several times the mass of our Sun, the journey would be extraordinarily violent and brief. However, falling into a supermassive black hole, millions or billions of times the mass of the Sun, could provide a longer, though equally unsettling, trip. As you approach the event horizon, the point of no return, gravity's effects become extreme. For a stellar mass black hole, tidal forces' extreme differences in gravitational pull would stretch and compress your body in a process whimsically known as spaghettification. You would be elongated along the direction of the black hole's pull while being compressed along the other directions, quickly leading to your demise before you even reached the event horizon. In contrast, if you fell into a supermassive black hole, the longer distance to the singularity at its core means tidal forces at the event horizon would be less intense. You could theoretically pass the event horizon without immediate catastrophic spaghettification. As you fall deeper into the black hole, the view to the outside universe would shrink to a small bright spot directly overhead, slowly fading as you approach the singularity where gravity crushes all matter to an infinitely small point. Once inside the event horizon, the laws of physics as we understand them break down. Theories suggest time and space become interchangeable, leading to speculations about what might occur. Some suggest you could encounter the singularity where matter is crushed to an infinitely dense point, ending your journey. Others hypothesize the possibility of reaching a region where space-time could connect to another part of the universe through hypothetical constructs called wormholes or Einstein-Rosen bridges. Whether the final moments involve a rendezvous with a singularity or passage through exotic cosmic pathways, falling into a black hole remains a mysterious and perilous voyage, an exploration on the very edge of our scientific understanding. Detecting exoplanets, or planets that orbit stars beyond our solar system, involves several ingenious methods, each leveraging different aspects of astronomy to unveil these hidden worlds. One of the most successful and widely used techniques is the transit method. When an exoplanet passes directly between its parent star and us, it causes a slight periodic dimming of the star's light. By carefully monitoring and measuring these dips in brightness, astronomers can infer the presence of an exoplanet, its size, and even some clues about its atmosphere. Another powerful method is the radial velocity or Doppler technique, which relies on detecting tiny wobbles in a star's position caused by the gravitational pull of an orbiting exoplanet. As the planet orbits, it tugs on the star, causing it to move slightly towards and away from us. This motion shifts the star's light spectrum towards the blue end when it moves towards us and towards the red end when it moves away. By studying these spectral shifts, scientists can estimate the exoplanet's mass and its orbital period. The direct imaging method, though challenging, involves capturing actual images of exoplanets by blocking out the overwhelming glare of their parent stars. Using advanced instruments and techniques like coronagraphs or star shades, astronomers can isolate the faint light reflected or emitted by the exoplanet. This method is particularly useful for studying larger exoplanets that are relatively far from their stars, in regions where the contrast between the planet and starlight is less blinding. Another intriguing approach is gravitational microlensing, which takes advantage of the warping of space-time caused by a massive object, such as a star or planet, passing in front of a more distant star. The gravity of the intervening object acts like a lens, magnifying the background star's light in a specific pattern. If an exoplanet is part of the intervening system, its presence can be inferred from the distinct characteristics of the light curve. These methods, often used in combination, have led to the discovery of thousands of exoplanets, painting a diverse and fascinating picture of planetary systems far beyond our own. With each detection, our understanding of the universe expands, revealing the potential for worlds that might harbor life or offer conditions vastly different from those we know. Super-Earths, a class of exoplanets with masses larger than Earth-SS but significantly less than those of ice giants like Uranus and Neptune, are particularly captivating to scientists. Typically, super-Earths boast masses ranging from about 1 to 10 times that of Earth. Their unique position in the planetary spectrum has piqued scientists' interest as they offer a window into diverse planetary formation processes and compositions. One reason super-Earths intrigue scientists is their potential similarity to Earth, which raises questions about their habitability. Many super-Earths lie within their star's habitable zones, the region where conditions might allow for liquid water to exist on the planet's surface. Water, a key ingredient for life as we know it, makes these planets prime candidates in the search for extraterrestrial life. The composition of super-Earths can vary widely, from rocky planets with thin atmospheres to water worlds with deep global oceans. Studying super-Earths also broadens our understanding of planetary formation. Our solar system lacks planets with masses between Earth and Neptune, so discovering and studying super-Earths in other systems helps fill in gaps in our knowledge. These planets might represent a common step in planetary evolution, providing clues on why certain planetary systems evolve differently. Some super-Earths have intriguing atmospheric compositions, detected by analyzing the starlight that filters through their atmospheres during transits. This spectroscopy can reveal the presence of gases like hydrogen, helium, and potentially even more complex molecules. By studying these atmospheres, scientists hope to learn about the processes shaping these worlds, including volcanic activity, weather patterns, and potential biosignatures. Super-Earths embody a diverse array of worlds, each with the potential to challenge and expand our definitions of habitability and planetary formation. As our detection methods and technologies improve, the study of these planets will undoubtedly yield more surprises, deepening our understanding of the myriad possibilities within our universe. Rogue planets or nomadic planets wander through the galaxy unbound by any star. These mysterious worlds, existing in the dark expanse between stars, raise fascinating questions about the potential for life in such isolated environments. While the absence of a parent star presents significant challenges for sustaining life as we know it, certain theoretical scenarios suggest it might not be entirely out of the question. First, Let us consider the possibility of subsurface oceans. If a rogue planet retains enough internal heat from its formation or experiences tidal heating from interactions with a large moon, it might possess a subsurface ocean insulated by a thick layer of ice, similar to the icy moons of Jupiter and Saturn in our solar system. Such oceans could potentially harbor microbial life or even more complex organisms, exploiting the energy from hydrothermal vents at the ocean floor. Another intriguing scenario involves thick atmospheres. If a rogue planet has a dense atmosphere rich in hydrogen or other insulating gases, it could trap enough heat to maintain liquid water on its surface or beneath a layer of ice. This atmospheric blanket would act like a giant thermos, retaining geothermal heat and potentially providing conditions suitable for life. This concept of atmospheric insulation expands the possible habitable zones far beyond the confines of starlight. Life may also arise from different biological principles than those on Earth. In the absence of sunlight, alternative energy sources, such as chemical energy from the planet's interior, might serve as the basis for an entirely different kind of biosphere. Extremophiles on Earth microorganisms that thrive in harsh environments like deep-sea vents and acidic hot springs hint at life's remarkable adaptability to diverse energy sources and conditions. Rogue planets push the boundaries of our understanding of habitability and challenge our perceptions of where life could exist. While the conditions are undoubtedly extreme, the resilience of life on Earth in similarly harsh environments suggests that life on rogue planets, though speculative, remains a tantalizing possibility. As our knowledge and detection techniques advance, these lonely wanderers might one day reveal themselves as harboring the secret to life's adaptability beyond the stellar neighborhoods we are accustomed to. Searching for biosignatures on exoplanets involves using sophisticated techniques and instruments to detect chemical and physical signs of life from light years away. These biosignatures are essentially indicators of biological processes that can be observed and measured from Earth or orbiting space telescopes. The quest for these telltale signs is one of the most exciting frontiers in modern astronomy and astrobiology. One primary method is the analysis of exoplanetary atmospheres, which can be done during transits when an exoplanet passes in front of its host star. A small fraction of the star's light filters through the planet's atmosphere. By examining this light with tools like spectrometers, scientists can identify the absorption lines corresponding to specific gases. Certain gases, such as oxygen, methane, or ozone, in particular concentrations, might indicate biological activity. For instance, on Earth, a combination of oxygen and methane in the atmosphere is mostly produced by life. Another approach involves studying reflected light from an exoplanet, known as direct imaging. Instruments use advanced techniques to block the overwhelming light from the parent star, allowing astronomers to analyze the spectrum of light directly reflected off the planet's surface or atmosphere. Reflected light can reveal various surface materials and atmospheric components. Detection of unusual surface compositions, like chlorophyll-like signatures associated with photosynthesis on Earth, might provide clues about potential life. Additionally, scientists consider the possibility of detecting technosignatures, which are signs of advanced technology. These might include unusually structured light patterns or radio signals akin to those our technology emits. Though the search for technosignatures is more speculative and challenging, the potential discovery of such signals would be a groundbreaking indication of intelligent life elsewhere. Groundbreaking missions like the Kepler Space Telescope and the James Webb Space Telescope, along with upcoming projects, utilize these methods to systematically explore exoplanets' atmospheres and surfaces. As our technological capabilities grow, so does our ability to detect subtle signs of life, pushing us ever closer to answering the age-old question, are we alone in the universe? With each advancement, the dream of discovering life beyond Earth moves from the realm of speculation to the cusp of scientific reality, making the search for biosignatures an exhilarating journey into the unknown. The Fermi paradox presents a fascinating puzzle named after physicist Enrico Fermi, who famously asked, "Where is everybody?" This question encapsulates the seeming contradiction between the high probability of extraterrestrial civilizations existing elsewhere in the Milky Way galaxy and the lack of evidence or contact with such civilizations. Given the vast number of stars and potentially habitable planets, Fermi's simple yet profound query continues to perplex scientists and stimulate intriguing hypotheses. One of the central tenets of Fermi's paradox lies in the Drake equation, which estimates the number of active, communicative extraterrestrial civilizations in our galaxy. Factors such as the vast number of stars, many of which have planets in habitable zones, suggest that statistically, intelligent life should be relatively common. Our Milky Way alone contains around 100 billion stars, many of which are orbited by planets that could host life. Yet despite the seemingly favorable conditions, we have no conclusive evidence of extraterrestrial civilizations. Several theories attempt to explain this paradox. One idea is the possibility of the Great Filter, a hypothetical stage in the evolution of life that is extremely unlikely or difficult to overcome. This filter could be behind us, meaning life rarely evolves to complex organisms, or ahead, suggesting advanced civilizations self-destruct before achieving interstellar communication. Either scenario presents sobering implications for our own civilization's future. Another hypothesis is the concept of the zoo hypothesis, where advanced extraterrestrial civilizations deliberately avoid contact with us, observing humanity from afar like animals in a zoo. They might be waiting for us to reach a certain level of technological or ethical maturity before making contact. Others propose that interstellar travel or communication might be inherently difficult or resource-intensive, limiting the spread or detectability of advanced civilizations. Additionally, some suggest that we might not be recognizing the evidence of extraterrestrial life because it differs significantly from our expectations. Life forms might be so alien in form and function that we fail to perceive their presence. The Fermi paradox remains a profound and open-ended question, driving both scientific inquiry and speculative thought. Each proposed solution, whether it leans towards biological, technological, or sociological explanations, brings us closer to understanding our place in the cosmos and the potential for others sharing it with us. The Great Attractor is a gravitational anomaly in intergalactic space that exerts a powerful pull on the galaxies in its vicinity, including our own Milky Way. Located roughly 150 to 250 million light-years away in the direction of the constellation Centaurus, this mysterious region is part of what is known as the Laniakea supercluster, a massive collection of over 100,000 galaxies bound together by gravity. The intrigue surrounding the Great Attractor arises from its immense gravitational influence. This gravity well draws galaxies towards it at velocities of up to several hundred kilometers per second. Observations indicate that entire clusters of galaxies are being pulled towards this enigmatic point. Even our local group of galaxies, which includes the Milky Way, is moving towards the Great Attractor at approximately 600 kilometers per second. Determining precisely what constitutes the Great Attractor is challenging because it lies within the zone of avoidance, an area of the sky obscured by the dense plane of our Milky Way galaxy, filled with stars, dust, and gas. This obscuration makes direct observation difficult. However, advanced observational techniques and the use of X-ray astronomy have allowed astronomers to partially peer through this dense foreground. Research suggests that the Great Attractor is likely a major supercluster structure with large concentrations of galaxies, dark matter, and hot gas contributing to its intense gravitational field. One key structure associated with the Great Attractor is the Norma cluster, a massive cluster of galaxies situated near the center of this gravitational anomaly. Nonetheless, the full extent of what comprises the Great Attractor remains an active area of research. Understanding the Great Attractor not only helps us comprehend the motion of galaxies within our local cosmic neighborhood, but also provides insight into the large-scale structure of the universe. This region of space exemplifies the complex gravitational interactions that shape the cosmos, influencing the movement and distribution of galaxies across vast distances. Cosmic voids are vast, relatively empty regions in the universe, devoid of much of the matter that makes up galaxies, stars, and other celestial structures. These voids, some spanning hundreds of millions of light-years across, form an integral part of the large-scale structure of the universe, often described as a cosmic web of filaments and clusters, with the voids as the spacious gaps in between. The formation of cosmic voids is closely tied to the evolution of the universe itself. Following the Big Bang, the universe was initially a nearly uniform soup of particles and energy. Over time, slight quantum fluctuations in this primordial matter density grew due to gravitational attraction. Regions with slightly higher densities attracted more matter, forming galaxies and clusters. Meanwhile, less dense regions lost their matter to these denser regions, expanding into the vast voids we observe today. This process, governed by gravity and the expansion of the universe, has been ongoing for billions of years. Inside these cosmic voids, things are not entirely empty. Instead, they contain very low-density gas, some dark matter, and a sparse population of galaxies and galaxy clusters. The average density of galaxies in these voids is significantly lower than in the more densely populated filamentary structures. The galaxies found within voids tend to be smaller, less luminous, and often isolated compared to those in richer regions of the cosmic web. Understanding cosmic voids not only sheds light on the distribution of matter in the universe, but also provides valuable insights into the fundamental processes driving cosmic evolution and the large-scale dynamics of the cosmos. The conditions within cosmic voids lead to unique evolutionary paths for galaxies, making these regions fascinating subjects for studying galaxy formation and evolution distinct from denser cosmic areas. Moreover, cosmic voids offer unique opportunities to study dark energy, the mysterious force driving the accelerated expansion of the universe. These voids, being underdense regions, react more sensitively to dark energy, making them excellent natural laboratories for probing its properties. Although seemingly empty, cosmic voids are rich in information about the universe's formation, the distribution of galaxies, and the enigmatic nature of dark energy. Their study continues to deepen our understanding of the universe's large-scale structure and the forces shaping its evolution. Galaxy filaments are colossal thread-like structures composed of galaxies, gas, and dark matter, forming the backbone of the universe's large-scale structure. These filaments can extend across hundreds of millions of light-years, connecting clusters and superclusters of galaxies into a vast, intricate cosmic web. They are among the largest known structures in the universe and play a fundamental role in its overall architecture. The formation of galaxy filaments began soon after the Big Bang, when slight density fluctuations in the primordial matter distribution acted under gravity's influence, pulling matter together into increasingly complex structures. As gravity continued to pull matter into denser regions, long, thin filaments emerged, linking galaxy clusters and sprawling across the cosmos. Dark matter, though invisible, constitutes the scaffolding around which ordinary visible matter congregates within these filaments. Galaxies follow the dense trails created by dark matter, driven by gravitational forces that funnel matter toward dense nodes where galaxy clusters reside. These nodes can merge to form even larger structures known as superclusters. Interactions within filaments play a critical role in the evolution and formation of galaxies, inducing galaxy mergers and triggering new waves of star formation. Studying galaxy filaments provides essential insights into understanding the large-scale structure of the universe and its composition. By mapping these filaments, astronomers can trace the distribution of dark matter, whose gravitational influence shapes these cosmic strands. Examining the properties and dynamics of galaxies within filaments helps scientists explore galactic evolution within different cosmic environments. Galaxy filaments illustrate how cosmic forces orchestrate the distribution of matter on grand scales, leading to the rich tapestry of galaxy clusters, superclusters, and voids that define our cosmos. These filaments reveal the intricate dance of matter and gravity that continues to shape the cosmic landscape. Galactic superclusters are among the most massive and monumental structures in the universe, comprising tens of thousands of galaxies stretched across hundreds of millions of light-years. Their formation and evolution are a testament to gravity's power over grand cosmic timescales from the earliest moments following the Big Bang to the present day. The journey of supercluster formation begins with tiny density fluctuations in the primordial matter distribution of the early universe. These fluctuations, remnants of quantum variances from the earliest moments of the Big Bang, were slightly denser regions of matter spread throughout the otherwise uniform universe. Under gravity-S influence, these denser regions began to attract more matter, slowly evolving into larger structures over billions of years. As these structures grew, they formed dense knots and then larger associations. Over time, multiple clusters merged into more significant formations, resulting in the extensive superclusters we observe today. The evolution of galactic superclusters involves complex dynamic processes. Galaxy clusters within superclusters continue to move under mutual gravitational attraction, occasionally colliding and merging to form even more massive and denser clusters. These interactions can spur new waves of star formation, alter the shapes and properties of galaxies, and drive the growth of supermassive black holes at the centers of galaxies. The ongoing expansion of the universe influences the evolution of superclusters, with some structures becoming more isolated as the space between them stretches. Today, we map these vast structures using tools like large-scale galaxy surveys, providing a 3D view of the universe and revealing the intricate web of clusters, filaments, and voids. Superclusters like the Virgo supercluster, which includes our own Milky Way, and the massive Laniakea supercluster, highlight the grand scale of cosmic architecture. The study of superclusters deepens our understanding of the universe's large-scale structure and provides crucial insights into the interplay of dark matter and dark energy in shaping cosmic evolution. By observing these colossal structures, we gather valuable clues about the nature of the universe itself, from its genesis to its ultimate fate. Dark flow is a mysterious phenomenon observed in the large-scale motion of galaxy clusters. Despite the general agreement that the universe's expansion should be uniform, some galaxy clusters appear to be moving in a specific coherent direction, different from the expected pattern. This movement is not accounted for by the standard cosmological model, which includes dark energy and dark matter to explain the universe's observed behavior comprehends physics and forces us to consider that the cosmos might be even more vast and complex than we currently comprehend. Exploring this further could lead to groundbreaking insights about the universe's fabric, its origins, and the potential existence of multiversal realms. Addressing these mysteries drives cosmology to think boldly, expanding our comprehension of everything that lies beyond our cosmic line of sight. Hypernovae are extraordinarily powerful stellar explosions, far more energetic than typical supernovae. They result from the collapse of massive stars, generally at least 30 times the mass of our Sun. When such a colossal star exhausts its nuclear fuel, its core collapses under gravity as immense force, leading to a cataclysmic release of energy. A primary characteristic distinguishing hypernovae from regular supernovae is their immense energy output. While supernovae release an astounding amount of energy, hypernovae can be 10 to 100 times more powerful. The underlying mechanisms for this heightened energy relate to the star's mass and the nature of its collapse. In a hypernova, the core collapse may result in the formation of a black hole rather than a neutron star, as is common in many supernovae. Hypernovae also exhibit unique features in their emissions. For instance, they are often associated with long-duration gamma-ray bursts, some of the brightest electromagnetic events in the universe. These bursts are thought to arise from jets of particles moving at nearly the speed of light, emanating from the star's poles as it collapses into a black hole. This jet formation requires very specific conditions, typically found in the most massive stars with rapid rotation. Another difference is their impact on the cosmos. Hypernovae play a crucial role in seeding the universe with heavy elements. During these colossal explosions, elements heavier than iron are forged and dispersed into the surrounding space, aiding in the creation of future stars and planetary systems. While supernovae also contribute to this process, the sheer scale at which hypernovae do so is significantly greater, ensuring their indelible mark on the universe's evolutionary tapestry. Magnetars generate the most powerful magnetic fields in the universe through processes initiated during their birth from certain types of supernova explosions. When a massive star, typically around 10 to 25 times the mass of our Sun, exhausts its nuclear fuel, the resulting core collapse often forms a neutron star. However, if conditions during the collapse are just right, particularly involving the star's S-core rotation and magnetic alignment, a magnetar can be born. In a magnetar, the collapsing core S rapid spin and the intense compression of magnetic field lines significantly amplify the magnetic field strength. This amplification can be up to a quadrillion times stronger than Earth's magnetic field. The star's magnetic field lines are tightly wound as the core shrinks dramatically in size, concentrating the magnetic energy into a far smaller volume. The extreme density and pressure inside a magnetar also contribute to the intense magnetic fields. The particles within the core, primarily neutrons, align in such a way that their magnetic moments reinforce each other rather than cancelling out as they do in less dense conditions. This collective alignment magnifies the overall magnetic effect across the neutron star. Magnetars are distinguished by their highly unstable magnetic fields, which can cause dramatic and violent effects on their surfaces. These magnetic instabilities lead to starquakes and the release of enormous bursts of X-rays and gamma rays. These bursts are so powerful that they can affect satellites and even Earth's atmosphere, despite happening thousands or even millions of light years away. These cataclysmic energies and magnetic forces ensure that magnetars stand as some of the universe's most extraordinary and enigmatic objects. Fast radio bursts, FRBs, are brief, intense flashes of radio waves that originate from far beyond our galaxy. These bursts last only milliseconds but release an immense amount of energy, comparable to what our Sun emits over several days. The mysterious nature of their origins has captivated astronomers since the first one was discovered in 2007. One leading hypothesis is that FRBs are caused by highly magnetized neutron stars known as magnetars. Magnetars possess incredibly powerful magnetic fields, and these fields can sometimes undergo sudden changes. These magnetar starquakes or other magnetic instabilities might produce the rapid bursts of energy that we detect as FRBs. Some FRBs have been traced back to regions in space where massive stars often end their lives, lending support to this theory. Another potential source of FRBs is the collision or merging of compact objects, such as neutron stars or black holes. When these dense stellar remnants collide, they can create shock waves and potentially emit these powerful radio bursts. The rare nature of such collisions matches the observed scarcity and randomness of FRBs, making this a plausible explanation for at least some of the bursts. Interestingly, some FRBs repeat, providing further clues to their nature. The repeating nature suggests that the same source can produce multiple bursts over time, contrasting with cataclysmic events like collisions that happen only once. This observation has led to theories involving objects with continuous emissions like rotating neutron stars in binary systems or interactions between a magnetar and its surrounding environment. While our understanding of FRBs is still evolving, each new discovery adds pieces to the complex puzzle of their origins. As we improve our detection abilities and gather more data, we hope to unravel the enigmatic nature of these extraordinary cosmic phenomena. Binary star systems consist of two stars orbiting a common center of mass, and their evolution and interaction can be profoundly different from that of solitary stars. The dynamics within these systems lead to unique behaviors and phenomena that are fascinating to astronomers. Initially, when both stars in a binary system are relatively young and still on the main sequence, they interact primarily through gravitational influence. Each star orbits the system's center of mass, a point determined by their respective masses. If the two stars are close, gravitational interactions can become quite complex. These interactions can cause changes in their orbits and, in some cases, result in mass transfer, where one star pulls material from its companion. As these stars age and exhaust their nuclear fuel, the more massive star typically becomes a red giant first. As it expands, its outer layers may overflow its Roche lobe, an imaginary teardrop-shaped region around each star where material is gravitationally bound to that star. When this occurs, material can transfer to the companion star. This mass transfer significantly alters the evolution of both stars, potentially spinning up the receiving star and affecting its stellar life cycle. In some cases, this mass transfer can lead to dramatic phenomena. For instance, if the donor star sheds its outer layers rapidly enough, it might become a white dwarf. The accreting star might gain enough mass to experience increased nuclear activity or even explode as a supernova if it surpasses critical mass thresholds. Additionally, if the stars in the binary system are close enough, they might eventually merge, leading to further stellar cataclysms and potentially forming a new single massive star or a neutron star. Binary interactions can also lead to the production of exotic objects, such as X-ray binaries or millisecond pulsars. In X-ray binaries, the compact remnant of one star, such as a neutron star or a black hole, accretes matter from a companion star, emitting intense X-rays. Millisecond pulsars, on the other hand, are neutron stars that have been spun up by accreting material from a companion, rotating hundreds of times per second. Overall, the interplay between stars in binary systems showcases nature's complexity, leading to some of the most energetic and exotic phenomena in the universe, continually reshaping our understanding of stellar evolution and interaction. Quark stars are hypothetical celestial objects representing an extreme state of matter. They are thought to form under conditions even more extreme than those that create neutron stars. Essentially, a quark star would be formed if a neutron star's core density surpassed a critical threshold, causing neutrons to break down into their constituent particles known as quarks. When a massive star exhausts its nuclear fuel, it undergoes a supernova explosion, often leaving behind a dense core. Typically, if the remaining core S mass is sufficient, it will collapse into a neutron star, where matter is compressed to a state where neutrons are densely packed together. However, if the mass and pressure exceed a certain limit, it is theorized that these neutrons could decompose into quarks, resulting in a quark star. These quark stars would be composed of quark matter, a substance theorized to be denser than neutronium, the matter found in neutron stars. There are two primary types of quarks thought to make up this ultra-dense matter: up quarks and down quarks, which constitute neutrons, along with possible strange quarks, creating what is sometimes referred to as strange matter. This state of matter is so compact that it would have a bizarre property. Any additional matter falling onto a quark star would be immediately integrated into the quark matter, contributing little to increasing the star's size. Observationally, distinguishing quark stars from neutron stars poses a significant challenge, as both types of stars would exhibit similar characteristics. However, if quark stars exist, they might display slightly different mass and size relationships, known as mass-radius relationships, compared to neutron stars. They may also exhibit unique cooling patterns or emit bursts of energy detectable by astronomical instruments. The existence of quark stars remains hypothetical, yet the concept pushes the boundaries of our understanding of particle physics and stellar evolution. Confirming the existence of quark stars would not only provide insights into the behavior of matter under extreme conditions, but also deepen our grasp of the fundamental forces shaping the universe. Evidence for the existence of dark matter is drawn from various astronomical observations that reveal discrepancies between the predicted and observed behavior of cosmic structures. One of the earliest and most compelling pieces of evidence comes from the study of galaxy rotation curves. When astronomers, including Vera Rubin in the 1970s, measured the rotation speeds of stars in galaxies, they found that stars at the outer edges rotated just as quickly as those near the center. According to Newtonian mechanics, the stars further from the center should rotate more slowly unless there is additional unseen mass providing gravitational pull. This suggests the presence of an unseen or dark matter component. Another significant source of evidence comes from gravitational lensing, where light from distant galaxies is bent around massive objects like galaxy clusters. The degree of bending observed cannot be accounted for solely by the visible matter in these clusters. Instead, it indicates that there is much more mass present, exerting the gravitational forces necessary to curve the light to the extent observed. The cosmic microwave background radiation, the afterglow of the Big Bang, also provides clues. Measurements taken by satellites such as the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft reveal subtle temperature fluctuations in this ancient radiation. By analyzing these fluctuations and the distribution of galaxies in the universe, cosmologists can infer the total amount of matter and energy. The results indicate that only about 1/6 of this matter is the regular baryonic matter we can see, and interact with the rest is dark matter. Finally, observations of galaxy cluster movements offer additional evidence. One famous example is the Bullet Cluster, where two galaxy clusters collided. The collision separated the dark matter from the normal matter, producing distinct gravitational effects observable through gravitational lensing. The visible matter, predominantly gas, slowed down and collided, whereas the dark matter continued largely unimpeded. This separation provided a clear picture of dark matter's presence and its different physical properties compared to normal matter. All these observations collectively build a strong case for dark matter's existence. Despite being invisible and not interacting with electromagnetic forces, dark matter's gravitational influence is critical in shaping the structure and evolution of the universe. Its detection remains one of the most exciting frontiers in modern astrophysics and cosmology, with experiments ongoing both in space and on Earth to directly detect dark matter particles. Dark energy is a mysterious and pervasive force believed to be responsible for the accelerating expansion of the universe. Discovered in the late 1990s through observations of distant-type Ia supernovae, dark energy is thought to make up about 2/3 of the total energy density of the universe. Its properties and behavior remain among the biggest questions in cosmology. One way to conceptualize dark energy is through a term in Einstein-Is equations of general relativity known as the cosmological constant, often symbolized by the Greek letter lambda. This constant can be thought of as an inherent energy of empty space, which exerts a repulsive force counteracting the gravitational pull of matter. As the universe expands, more space is created, and with it more dark energy. This amplifies the repulsive effect, leading to an accelerating expansion. Another perspective is that dark energy could be a dynamic field, similar to but distinct from gravity, dubbed quintessence. Unlike the static energy of the cosmological constant, quintessence would evolve over time, changing the rate at which the universe expands. This viewpoint allows for more complex models and could potentially explain the observed variations in the acceleration rate more flexibly. Dark energy's effects are not immediately noticeable on small scales, such as within galaxies or even galaxy clusters where gravitational forces dominate. However, on the cosmic scale, its influence becomes profound. The accelerated expansion was confirmed through various means, including the study of the cosmic microwave background radiation and large-scale galaxy surveys, which show that galaxies are moving away from each other more rapidly over time. Current and future observational projects like the Euclid satellite mission and the Vera C. Rubin Observatory aim to map the distribution of galaxies and measure the expansion rate of the universe with unprecedented precision. By examining the large-scale structure of the cosmos and the behavior of dark energy over time, scientists hope to uncover its nature, potentially leading to groundbreaking discoveries that could reshape our understanding of physics and the universe. The intriguing possibility that dark matter might be composed of primordial black holes has garnered considerable interest among scientists. Primordial black holes are hypothetical objects that could have formed in the very early universe shortly after the Big Bang due to high-density fluctuations. Unlike typical black holes, which form from the collapse of massive stars, primordial black holes could be much smaller and represent an entirely different origin of dark matter. One point in favor of this hypothesis is that primordial black holes naturally exhibit many characteristics expected of dark matter. They are massive and do not emit light, fitting the profile of the elusive dark matter that influences the gravitational dynamics of galaxies and galaxy clusters. However, several constraints challenge this theory. Observations of gravitational lensing, where light from distant stars and galaxies is bent by a massive object, have not detected the expected number of lensing events that primordial black holes would cause if they were present in sufficient quantities to account for all dark matter. This places a significant limitation on their possible abundance and distribution. Additionally, primordial black holes of intermediate mass ranges might emit detectable levels of Hawking radiation, or could lead to specific observable effects, such as interactions with stars and gas clouds, which we have not witnessed. Constraints from cosmic microwave background radiation also indicate that the contribution of primordial black holes to the total dark matter content must be small. Despite these challenges, the idea has not been entirely ruled out. Recent developments in astrophysics and gravitational wave astronomy, particularly those from the LIGO and Virgo collaborations detecting mergers of black holes, have revived interest in the possibility of primordial black holes. Some of these mergers involve black holes of masses and frequencies that might be consistent with primordial origins. Ongoing and future observational efforts aim to explore various mass ranges and properties of primordial black holes more comprehensively. While we continue to seek direct evidence for dark matter particles and alternative explanations, the primordial black hole hypothesis remains an intriguing possibility that could, if proven, offer revolutionary insights into both dark matter and the formation of the early universe. Weakly interacting massive particles. WIMPs are among the leading candidates to explain the elusive nature of dark matter. These hypothetical particles are thought to have significant mass and interact only through the weak nuclear force and gravity, making them extraordinarily difficult to detect. The concept of WIMPs emerges naturally from extensions to the standard model of particle physics, such as supersymmetry, which posits the existence of heavier counterparts to known particles. One of these potential particles could be a WIMP, possessing the right properties to account for the observed effects of dark matter on the cosmic scale. One key reason WIMPs are considered viable dark matter candidates is the so-called WIMP miracle. When scientists calculate how WIMPs would have behaved in the early universe, they find that particles with the right mass and weak interaction properties would have naturally resulted in an abundance consistent with the observed density of dark matter today. This elegant coincidence strengthens the case for WIMPs as dark matter constituents. Detecting WIMPs directly involves several experimental approaches. Direct detection experiments, such as those conducted with large underground detectors filled with supercooled noble gases like xenon or argon, aim to spot the rare interactions between WIMPs and atomic nuclei. These interactions would produce tiny signals of light or heat, which researchers analyze to determine if they match the expected profile of WIMP interactions. Indirect detection methods focus on looking for the byproducts of WIMP annihilations or decays. If WIMPs exist, they could occasionally collide and annihilate each other, producing detectable particles like gamma rays, neutrinos, or other standard particles. These signals could be observed by space-based or ground-based telescopes. Another approach involves searching for anomalies in cosmic radiation that could hint at WIMP interactions. When particles collide, they might annihilate each other and produce gamma rays, neutrinos, or other particles detectable by instruments like the Fermi Gamma Ray Space Telescope. Particle accelerators such as the Large Hadron Collider seek to create WIMPs by colliding protons at extremely high energies. Scientists examine the debris from these collisions to spot missing energy or momentum signatures indicative of WIMPs. While WIMPs remain undetected, ongoing research and technological advancements push the boundaries, offering hope for eventual identification. Confirming WIMPs' existence would solve the dark matter mystery and potentially reveal new fundamental aspects of particle physics and the universe's fabric. Scientists use sophisticated techniques to detect dark matter particles directly, leveraging both underground detectors and advanced astronomical observatories. Although dark matter doesn't interact with light and remains invisible to traditional telescopes, it is theorized to interact via gravity and potentially the weak nuclear force. One primary method involves large underground detectors designed to identify interactions between dark matter particles and atomic nuclei. These detectors, located deep underground to shield from cosmic rays and background radiation, use noble gases like xenon or argon kept in a liquid state at ultra-low temperatures. When a dark matter particle interacts with the nucleus of an atom within the detector, it produces tiny flashes of light or minute amounts of heat. Despite the infrequency of these interactions, ultra-sensitive photodetectors and thermal sensors capture these rare events. Experiments such as Xenon in Italy and Lux Zeppelin in the United States exemplify this approach, employing enormous tanks of liquid xenon monitored for potential interactions. Another technique focuses on indirect detection methods, looking for byproducts of dark matter interactions in space, such as gamma rays, neutrinos, or electron-positron pairs that could be generated if dark matter particles annihilate each other or decay. Instruments like the Fermi Gamma Ray Space Telescope observe regions like galaxy centers, where dark matter density is high, searching for unexpected particle excesses. Particle accelerators offer another avenue for potential dark matter detection. By smashing protons together at extremely high energies, as done at the Large Hadron Collider in Switzerland, physicists attempt to recreate conditions similar to those following the Big Bang. The goal is to produce dark matter particles inferred from missing energy and momentum in collision events. This indirect signature suggests the creation of particles that do not interact like those in the standard model, potentially indicating dark matter. Hence, scientists employ an array of cutting-edge technologies and methodologies, pushing detection boundaries. While direct evidence of dark matter remains elusive, these innovative and complementary approaches significantly narrow down the possibilities, bringing us closer to uncovering one of the universe's greatest mysteries. Ultra-high energy cosmic rays are particles, primarily protons or heavier atomic nuclei, that travel through space at nearly the speed of light and possess energy far exceeding typical cosmic rays. These particles can have energies millions of times greater than those produced in man-made particle accelerators, making them some of the most energetic particles in the universe. The precise origins of ultra-high energy cosmic rays remain one of the great mysteries in astrophysics. However, several potential sources are thought to be responsible for their extraordinary energies. One hypothesis involves active galactic nuclei AGNs, which are supermassive black holes at the centers of distant galaxies. These AGNs are surrounded by vast accretion disks of gas and dust, which, when falling into the black hole, can get accelerated to incredible speeds, generating powerful jets capable of propelling particles to extreme energies. Another potential source could be gamma-ray bursts, among the most energetic events observed in the universe. These bursts occur when massive stars collapse into black holes or when binary neutron stars collide. The intense explosion releases enormous amounts of energy in a short time, potentially accelerating particles to ultra-high energies. Supernova remnants within our galaxy are also considered potential contributors, particularly those involving very massive stars. The shock waves generated by supernova explosions can accelerate particles to high energies through a process known as Fermi acceleration. While supernovae are well-established sources of lower energy cosmic rays, it is possible that under the right conditions, they could also produce ultra-high energy cosmic rays. Additionally, interactions between cosmic rays and interstellar or intergalactic magnetic fields can also play a role in accelerating particles. These magnetic fields can bend and twist particle trajectories, amplifying their energies over vast distances through a process known as diffusive shock acceleration. Detecting and studying ultra-high energy cosmic rays involve ground-based observatories like the Pierre Auger Observatory in Argentina and the Telescope Array Project in Utah. These observatories use extensive arrays of detectors spread over large areas to capture and analyze the secondary particle showers produced when ultra-high energy cosmic rays collide with molecules in Earth's atmosphere. By studying the patterns, isotopes, and energy spectra of these cosmic ray impacts, scientists hope to unravel the origins and acceleration mechanisms of these extraordinarily energetic particles. As we gather more data, the secrets of ultra-high energy cosmic rays slowly reveal themselves, potentially offering new insights into some of the most violent processes in the cosmos. Cosmic ray air showers occur when high-energy cosmic rays, primarily composed of protons or heavier nuclei, enter Earth's atmosphere and collide with atmospheric particles. This collision initiates a cascade of secondary particles that spread out in an extensive shower, which scientists can detect and study using ground-based observatories. When a primary cosmic ray, traveling nearly at the speed of light, strikes a molecule in the upper atmosphere, it initiates a high-energy collision, producing a variety of secondary particles. These first-generation particles typically include pions, kaons, and other hadrons. The process is highly energetic, with the initial impact often resulting in the creation of hundreds or even thousands of secondary particles. As these secondary particles travel further into the atmosphere, they collide with additional molecules, generating even more particles. The shower grows exponentially, creating a complex web of interactions. During this cascade, pions and kaons quickly decay into lighter particles like muons, electrons, neutrinos, and photons. Photon interactions can lead to pair production, where a photon converts into an electron and its antimatter counterpart, the positron. Similarly, electrons and positrons can emit photons through a process called Bremsstrahlung, feeding back into the cascade and producing more particles. This chain reaction results in a broad shower of secondary particles that spreads wider as it propagates through the atmosphere. The composition of the secondary particles changes as the shower progresses. At lower altitudes, the shower predominantly consists of photons, electrons, and muons, as many of the hadrons have decayed or lost energy through interactions. Muons, being relatively stable and less interactive, can penetrate deep into the atmosphere, sometimes even reaching the ground, where they can be detected by sensitive instruments. Water Cherenkov tanks detect the Cherenkov radiation emitted when muons and electrons move through the water faster than the speed of light in that medium, creating a distinctive blue glow. Scintillators detect charged particles through the light produced when particles pass through specific materials. By analyzing the pattern, timing, and intensity of the detected particles, scientists can reconstruct the properties of the original cosmic ray, including its energy, arrival direction, and potentially its source. This information helps in understanding cosmic ray origins and the fundamental processes that govern high-energy particle interactions in the universe. The Oh My God particle refers to an ultra-high-energy cosmic ray detected on the evening of October 15, 1991, by the Fly-SI Cosmic Ray Detector in Utah. It astonished scientists because it possessed an energy of roughly 300 million electron volts, a level far beyond what had ever been observed before and millions of times greater than particles encountered in man-made particle accelerators. What made the Oh My God particle particularly surprising was its sheer energy, which challenged our understanding of how the universe can accelerate particles to such extreme levels. To put this into perspective, the kinetic energy of this single proton was roughly equivalent to that of a baseball traveling at a substantial speed, around 90 km/h. Such energy levels are extraordinarily difficult to achieve, considering the known mechanisms of particle acceleration in astrophysical environments. The detection of the Oh My God particle raised numerous questions about the potential sources of such high-energy cosmic rays. Conventional astrophysical objects, such as supernova remnants or even active galactic nuclei, typically cannot account for the extraordinary energies observed. Some scientists speculated that exotic and rare astrophysical events like colliding neutron stars, supermassive black hole jets, or even processes related to the early universe just after the Big Bang might be responsible. Additionally, the Oh My God particle also posed a puzzle related to the GZK limit, Greisen-Zatsepin-Kuzmin limit, a theoretical upper bound on the energy of cosmic rays. According to this limit, cosmic rays with energies above roughly 5 million electron volts should interact with the cosmic microwave background radiation, losing energy over vast distances. Therefore, observations of such high-energy particles suggest that they either originate from relatively nearby extragalactic sources or that some unknown mechanism allows them to preserve their energy over greater distances than currently understood. Since the detection of the Oh My God particle, several other ultra-high-energy cosmic rays have been observed, but the original discovery remains a landmark event in astroparticle physics. These detections continue to spur research and debate about the processes capable of producing such phenomenal energies, pushing the boundaries of our understanding of the most energetic phenomena in the universe. Cosmic rays pose significant challenges and risks for space travel and the health of astronauts. These high-energy particles, originating from the Sun, distant stars, and other cosmic sources, can profoundly affect both spacecraft and the human body. One primary concern is the health risk from prolonged exposure to cosmic rays. Unlike Earth's surface, which benefits from the planet's magnetic field and atmosphere acting as protective shields, space lacks such defenses. Consequently, astronauts are directly exposed to these high-energy particles, which can penetrate human tissue and even spacecraft material. The radiation can cause various biological effects, including DNA and cellular structure damage, increasing the risk of cancer, cataracts, neurological disorders, and other health issues. The longer the mission, such as a journey to Mars, the greater the cumulative exposure and associated risks. Beyond individual health, cosmic rays can also impact spacecraft electronics through a phenomenon called single-event effects. When high-energy particles strike electronic components, they can induce errors, disrupt operations, or permanently damage critical systems. Ensuring the reliability of spacecraft and its instruments in the face of such potential disruptions is vital for mission planning and engineering. To mitigate these risks, several strategies are employed. Spacecraft are designed with shielding materials to reduce astronauts' and sensitive electronics exposure to cosmic rays. Although complete protection is impossible without impractically heavy shields, materials like polyethylene and water offer some degree of attenuation. Additionally, spacecraft trajectories and mission durations are carefully planned to minimize exposure during periods of heightened solar activity, such as solar flares, which can significantly elevate the already considerable levels of radiation in space. For astronaut health, space agencies are also exploring the development of pharmaceuticals and other medical countermeasures that might help mitigate the effects of radiation exposure. Continuous monitoring of radiation levels using onboard sensors provides real-time data to assess and respond to elevated risks during the mission. In conclusion, cosmic rays present a formidable challenge for space exploration. Through advanced engineering, prudent mission planning, and ongoing research into protective measures, the goal is to safeguard astronauts as humanity pushes further into the cosmos. The broader understanding and mitigation of these effects are essential to the success and health of future long-duration space missions. Neutrino detectors are remarkable instruments that allow scientists to peer into the heart of some of the universe's most dramatic events. Unlike photons or charged particles, neutrinos barely interact with matter, making them incredibly challenging to detect but simultaneously perfect messengers from the extreme environments where they originate. For instance, they can travel directly from supernovae or the depths of the Sun without being deflected or absorbed, carrying crucial information about those sources. By catching these elusive particles, neutrino detectors help us understand processes like nuclear fusion inside stars. The Sun, powered by such fusion reactions, emits a constant stream of neutrinos. Studying them gives us direct evidence of the Sun's inner workings, validating models of stellar physics. Similarly, detecting neutrinos from supernovae helps scientists investigate the explosive deaths of massive stars, shedding light on the production of heavy elements in the universe and the birth of neutron stars or black holes. Neutrinos also offer insights into the most fundamental aspects of physics. For instance, their ability to change from one type to another, a phenomenon known as neutrino oscillation, has provided compelling evidence that they indeed have mass, contrary to earlier assumptions. This discovery has profound implications for our understanding of particle physics and the fundamental forces governing the universe. Furthermore, exploring neutrinos from extragalactic sources opens up a new window into high-energy astrophysics. These particles might originate from active galactic nuclei or other mysterious cosmic phenomena, giving researchers clues about the most energetic processes in the cosmos. By studying neutrinos, scientists obtain a unique and otherwise unreachable perspective on both the most distant and the most hidden corners of the universe. Time dilation is a fascinating consequence of Einstein's theories of relativity and plays a crucial role in the functionality of Global Positioning System (GPS) satellites. These satellites orbit the Earth at high speeds and at different altitudes compared to the planet's surface. According to general relativity, time runs slower in stronger gravitational fields, meaning clocks on Earth's surface tick slightly slower than those further away in space. Meanwhile, special relativity predicts that due to their high velocities, time on board the satellites also runs slightly slower compared to a stationary observer on Earth. For the GPS to work accurately, the clocks on these satellites must synchronize precisely with clocks on Earth. Without adjusting for time dilation, even a tiny discrepancy can result in significant errors in position calculations. Specifically, the combined effects of special and general relativity mean that the satellite clocks tick faster than those on Earth by about 38 microseconds per day. While this might seem minuscule over time, it would lead to significant errors in position measurements errors as large as 10 kilometers per day. To counteract this, the clocks on GPS satellites are preset to tick slightly slower on the ground, ensuring that when they reach orbit, they match Earth's timekeeping. These adjustments allow GPS to provide the accurate location data that is now indispensable for navigation, communication, and countless other technologies. Relativity's influence on time also has broader implications, especially in understanding the universe. The principles underlying time dilation help explain the behavior of objects near massive celestial bodies, such as black holes, where the effects become extreme. In these intense environments, time can slow down to a crawl compared to distant observers, showcasing the profound relationship between time, space, and gravity. In conclusion, understanding and accounting for time dilation is crucial not only for the precision of modern technologies like GPS, but also for exploring the fundamental nature of the cosmos itself. As we continue to develop our knowledge of relativity and its effects, we further unravel the complex fabric of the universe. Conclusion. The cosmos presents a vast array of mysteries that continue to challenge and expand our understanding of the universe. From the paradoxes of black holes to the enigma of dark matter and dark energy, these phenomena push the boundaries of human knowledge, inviting us to explore deeper into the unknown. As our technology and scientific theories evolve, we are likely to uncover answers to some of these profound questions while discovering new ones that will propel our quest for knowledge even further. The study of the universe is not just a journey into space, but a journey into the very nature of existence, revealing the intricate connections between all things. When you look at the stars, you realize how vast our universe is and how little we know about it. Vera Rubin. Our universe is a vast and wondrous expanse, brimming with an extraordinary variety of celestial phenomena. It encompasses everything from the dazzling brilliance of countless stars and the sprawling majesty of galaxies to the enigmatic and mysterious forces that challenge our understanding, such as the immense gravitational pull of black holes and the elusive particles that comprise dark matter. The cosmos is a place of infinite wonder, far more bizarre and captivating than anything we could have ever imagined. We invite you to embark on a journey with us as we explore the most astonishing discoveries and the most puzzling questions that modern astronomy has to offer. Together, we will venture to the farthest reaches of the observable universe, gazing into the depths of space and time, and ponder the mysteries that might lie beyond the limits of our current knowledge. NASA's Juno mission has revealed a complex and intricate tapestry of Jupiter's atmosphere, surprising scientists with its findings. Among the most striking discoveries are the enormous Earth-sized cyclones clustered around Jupiter's poles. These cyclones, unlike any storm systems on Earth, form geometric patterns with remarkable regularity. At the North Pole, 8 cyclones arrange themselves into an octagonal pattern, while the South Pole hosts a pentagon-like formation of 5 cyclones. These storms remain stable over extended periods, defying existing meteorological models by resisting merger or dissipation. Another fascinating aspect uncovered by Juno is the uneven distribution of ammonia within Jupiter's atmosphere. Ammonia appears highly concentrated near the equator, forming what scientists have termed an ammonia-rich equatorial plume. This discovery suggests complex atmospheric processes, potentially involving upwelling that brings ammonia from deep within the planet to its upper atmosphere. Moreover, Juno-S data reveal that these atmospheric phenomena extend much deeper than previously thought, reaching hundreds of miles below the cloud tops. This depth offers new insights into Jupiter SE's internal dynamics, challenging prior assumptions about the gas giant's atmospheric composition and behavior. The New Horizons flyby of Pluto has revolutionized our understanding of this distant dwarf planet, revealing it to be far more complex and dynamic than anticipated. One of the most significant revelations is the diversity of Pluto's surface, which features vast icy plains, deep canyons, and towering mountains made of water ice. Perhaps the most iconic feature uncovered by New Horizons is the heart-shaped region named Tombaugh Regio, home to Sputnik Planitia, a nitrogen ice plain exhibiting signs of glacial activity. This suggests that Pluto is geologically active, with ongoing processes that continuously reshape its surface. Additionally, New Horizons revealed Pluto's unexpectedly thin but layered atmosphere, composed mainly of nitrogen with traces of methane and carbon monoxide. These layers extend much higher than predicted, creating a hazy, stratified visual effect as sunlight interacts with atmospheric particles. The atmosphere also undergoes significant seasonal changes, implying active climatic processes. Furthermore, the flyby detected small, localized geysers or ice volcanoes, indicating recent or ongoing internal heat sources driving surface renewal. These findings collectively shatter the long-standing perception of Pluto as a static, frozen world, presenting it instead as a vibrant, evolving entity with a fascinating and intricate landscape. Scientific evidence pointing to a subsurface ocean beneath Europa's icy crust is compelling and multifaceted. Observations made by the Galileo spacecraft detected a magnetic field around Europa, likely induced by an electrically conductive layer beneath the surface, most plausibly a salty liquid water ocean. Supporting this theory, gravity measurements reveal inconsistencies in Europa's density and mass distribution, suggesting a thick water-based layer beneath the ice. Additionally, surface geology offers visual clues to this hidden ocean. High-resolution images show chaotic terrain with disrupted ice resembling broken ice flows seen on Earth's polar seas, implying that Europa's icy crust is floating on a liquid layer. Moreover, Europa's surface is crisscrossed with dark linear features known as linea, believed to be fractures filled with material from the subsurface. These fractures may form as the icy shell flexes and stretches due to gravitational interactions with Jupiter and its other moons, creating conditions that could facilitate the upwelling of subsurface water. Adding to the evidence, recent observations from the Hubble Space Telescope detected plumes of water vapor erupting from Europa's surface, akin to geysers on Earth. These plumes provide strong direct evidence of liquid water interacting with the surface, painting a compelling picture of an oceanic world hidden beneath Europa's frozen exterior, holding the tantalizing possibility of an environment where life might exist. The mysterious hexagonal storm pattern at Saturn's North Pole is one of the most bizarre and intriguing phenomena observed in our solar system. Discovered by the Voyager spacecraft in the early 1980s and observed in greater detail by the Cassini mission, this geometric wonder defies easy explanation. The hexagon is a massive cloud pattern spanning roughly 20,000 miles across, with each side measuring about 9,000 miles wider than Earth's diameter. The structure is remarkably stable, having persisted for decades, and rotates with a period of about 10 hours and 39 minutes, synchronized with Saturn's internal rotation. Scientists believe that the hexagon might be formed by atmospheric jet streams and fluid dynamics unique to Saturn's gaseous environment. One prevailing theory is that this shape is a standing wave pattern, an effect that can occur in rotating fluids. Laboratory experiments have demonstrated that when a circular tank of liquid is rotated at different speeds, it can produce polygonal patterns, mimicking what we see on Saturn but on a much smaller scale. The hexagonal integrity could be maintained by differences in wind speeds, creating a boundary where vortices can align neatly into a polygonal shape. Adding to the enigma, deep within the hexagon lies a powerful rotating storm similar to a terrestrial hurricane, but stationary and far more ferocious. This storm SI is clearly defined, surrounded by high-speed winds reaching up to 300 miles per hour. These findings challenge our understanding of planetary weather systems, suggesting that Saturn AS atmospheric dynamics operate on principles both familiar and alien, coaxing hexagons out of the natural chaos within a planet's gaseous envelope. The discovery of liquid water on Mars has fundamentally reshaped the search for extraterrestrial life, reigniting interest and enthusiasm among scientists and the public alike. In 2015, NASA announced that recurring slope lineae, dark streaks observed on Martian slopes, were formed by seasonal flows of briny liquid water. This crucial finding was made possible through data from the Mars Reconnaissance Orbiter, which detected hydrated salts, chemical fingerprints of water within these streaks. The presence of liquid water, even if it is extremely salty, opens up the possibility that microbial life could exist on Mars today, as water is a fundamental prerequisite for life as we know it. This discovery has shifted the focus of Martian exploration missions, directing efforts toward areas where liquid water or subsurface ice might be accessible. Rovers like Curiosity and Perseverance are now tasked with searching for biosignatures, chemical signs that could indicate past or present microbial life. These explorations include drilling into Martian rock and soil, analyzing samples for organic molecules, and even preparing for future missions that might return Martian samples to Earth for detailed study. Identifying regions with liquid water also aids in selecting potential landing sites for human missions, as water is essential not only for sustaining astronauts, but also for producing fuel and oxygen. Furthermore, the discovery of water stretches beyond the immediate implications for life. It informs our understanding of Mars' climatic history and geological processes, as well as the planet's potential to have been habitable in its ancient past. This has spurred an expanded interest in comparative planetology, studying Mars to uncover parallels and differences with Earth's own history. The detection of liquid water has thus reinvigorated the quest to answer one of humanity's most profound questions: are we alone in the universe? By providing a more promising environment for life, Mars has once again become a focal point for astrobiological research. The discovery of unexpected geological activity on Mercury has significantly altered our perception of this small, sun-scorched planet. Prior to recent missions, scientists assumed that Mercury, long considered a geologically dead world, had cooled and contracted sufficiently to cease any major geological changes. However, the MESSENGER spacecraft, which orbited Mercury from 2011 to 2015, revealed a dynamic landscape that continues to reshape our understanding of the planet's geology. One of the most surprising findings was the presence of relatively young fault scarps, cliff-like landforms that are indicative of tectonic activity. These scarps are the result of the planet's surface contracting as its interior cools, causing the crust to buckle and break. Even more unexpected is evidence suggesting that this tectonic activity is not confined to Mercury's distant past, but has been occurring relatively recently, possibly within the last few million years. This indicates that Mercury is still geologically active, a startling revelation for a planet that was presumed inert. These small-scale thrust faults are only a few kilometers long and a few hundred meters high, yet their fresh appearance implies that Mercury's core is continuing to cool and shrink, driving ongoing surface deformations. The young age of these features suggests that Mercury's geological engine has not entirely stopped functioning, challenging pre-existing models of planetary cooling and tectonics. Another intriguing discovery was made in the form of hollow, irregular, rimless depressions scattered across many of Mercury's craters and open plains. These bright, reflective features appear to be relatively young and may form through the sublimation of volatile substances exposed by meteor impacts, a process where solid materials transition directly into a gas. This is particularly fascinating because it implies the presence of volatile compounds beneath Mercury's surface, a surprising find given the planet's proximity to the Sun and its extreme temperatures. The ongoing formation of hollows further emphasizes that Mercury, far from being a static, desolate world, is characterized by continuous and complex geological processes. Uranus' tilted magnetic field and unusual rotation offer intriguing insights into the planet's formation and the dynamic processes that have shaped its evolution. Unlike most planets in our solar system, which have their magnetic fields more or less aligned with their rotation axes, Uranus' magnetic field is significantly tilted from its rotational axis by about 59 degrees. Moreover, this magnetic field is off-center, displaced from the planet's core by roughly 1/3 of Uranus' radius. These anomalies suggest a complex internal composition and structure, differing markedly from what we observe on Earth and other planets. The peculiar characteristics of Uranus' magnetosphere likely stem from its formation and subsequent evolutionary history. A leading hypothesis is that Uranus experienced a catastrophic collision with a massive object, possibly a protoplanet early in its history. Such an impact could have knocked the planet onto its side, causing its extreme axial tilt of about 98 degrees. This tilt results in an unusual rotation, with Uranus spinning on its side as it orbits the Sun. The collision theory also explains the off-center magnetic field, as the internal dynamo generating the magnetic field might be located in a fractured or uneven layer of the planet's icy and rocky interior. Further supporting this idea, the collision could have stirred Uranus' interior sufficiently to create a complex, multi-layered composition within its mantle and core regions. This could have led to the development of separate dynamo actions within these layers, thereby producing the tilted and offset magnetic field. Additionally, the giant impact would have caused significant mixing of materials, possibly giving rise to unexpected compositions and physical states within the planet. Consequently, Uranus' magnetic peculiarities provide a window into not only the violent events of its past, but also the ongoing processes affecting its internal dynamics and structure. The Cassini mission's grand finale, its dramatic final dive into Saturn, yielded an unprecedented wealth of data, offering new insights into the gas giant's mysterious interior, ring composition, and atmospheric dynamics. As Cassini made its final orbits, it ventured into the previously unexplored gap between Saturn and its innermost rings, a region about 1,200 miles wide. This daring maneuver allowed the spacecraft to gather high-resolution measurements and observations that were impossible from any other vantage point. One of the most significant revelations came from detailed observations of Saturn's gravity field. By precisely measuring the gravitational pull exerted on the spacecraft, scientists were able to probe Saturn's inner structure. The data indicated that the planet's core is larger and more diffuse than previously thought, encompassing a mixture of rock, ice, and metallic hydrogen spanning up to 20,000 miles in diameter. These findings challenge earlier models of Saturn's internal composition, suggesting that the core is not as compact or well-defined as once believed. Additionally, Cassini's close pass between the planet and its rings provided critical insights into the ring's mass and structure. The spacecraft's observations revealed that the rings are surprisingly lightweight, indicating they might be relatively young in astronomical terms, perhaps only about 100 million years old. Moreover, the ring material is gradually falling into Saturn, a process known as ring rain, driven by the planet's magnetic field. This discovery suggests that the rings might eventually dissipate, reshaping our understanding of their lifespan and dynamics. The mission also delivered invaluable data on Saturn's upper atmosphere. As Cassini descended into the planet, it sampled the atmosphere directly, measuring its composition and temperature while enduring extreme conditions. The spacecraft detected complex organic molecules raining down from the rings into the atmosphere, enriching it with material that could impact atmospheric chemistry. These final observations of atmospheric composition and ring interaction provide a more comprehensive picture of the processes that govern both Saturn and its iconic rings, closing the mission with a legacy of transformative scientific insights. The Great Red Spot on Jupiter, an immense storm larger than Earth itself, is one of the most iconic and enduring features in our solar system. First observed over 3 centuries ago, this colossal anticyclone has been a subject of intense scientific study and fascination. The storm is characterized by its reddish hue, likely due to complex chemical reactions between atmospheric compounds and ultraviolet radiation from the sun. Measuring about 12,000 miles in width and 25,000 miles in length at its peak, the Great Red Spot has often been referred to as a galactic hurricane, with wind speeds reaching up to 400 km/h. However, recent observations indicate that the Great Red Spot is undergoing significant changes. Data from telescopes and spacecraft like the Hubble Space Telescope and the Juno mission reveal that the storm has been gradually shrinking over the past several decades. It has decreased in size by more than half, and its shape has evolved from an elongated oval to a more circular form. This reduction is so pronounced that it now measures about just 10,000 miles across. Additionally, the colors within the spot have varied, sometimes appearing more vividly red and at other times more muted. Each of these changes hints at underlying atmospheric dynamics and shifts in chemical compositions. Scientists are still debating the reasons behind the Great Red Spot's changes. One hypothesis suggests that interactions with smaller surrounding vortices are siphoning off the storm's energy, leading to its gradual diminishment. Another possibility is that alterations in Jupiter's overall atmospheric conditions are influencing the storm's dynamics. While the exact future of the Great Red Spot remains uncertain, its ongoing evolution provides a unique opportunity to study the mechanisms driving Jupiter's chaotic atmosphere, enriching our understanding of planetary weather systems both within and beyond our solar system. The intriguing possibility of a ninth planet lurking in the distant reaches of our solar system has captivated astronomers in recent years. Fueled by compelling indirect evidence, this hypothetical planet, often referred to as Planet 9, is thought to reside far beyond the orbit of Neptune, in the region known as the Kuiper Belt. The first hint of its existence came from the peculiar orbital behavior of certain trans-Neptunian objects, particularly a group of these icy bodies with highly elliptical and aligned orbits. These clustering patterns are unusual and suggest the gravitational influence of an unseen massive object. The leading proponents of the Planet 9 hypothesis, astronomers Konstantin Batygin and Mike Brown, proposed in 2016 that a planet roughly 10 times the mass of Earth could explain these anomalous orbits. Their calculations indicate that this massive planet would orbit the Sun at an average distance of around 400 to 800 astronomical units. 1 astronomical unit is the distance between Earth and the Sun, taking between 10,000 to 20,000 Earth years to complete a single orbit. Such a distant and sizable planet would exert sufficient gravitational force to shepherd the TNOs into their observed configurations, acting as a cosmic shepherd guiding their paths. Further supporting evidence comes from computer simulations that test the stability of the outer solar system with and without the presence of Planet 9. These simulations show that including a ninth planet results in a more accurate representation of the current arrangement and motion of trans-Neptunian objects. Additionally, some researchers point to irregularities in the orbits of known planets and dwarf planets, suggesting that the gravitational influence of a distant large object could account for these discrepancies. While no direct observation of Planet 9 has been made, various astronomical surveys and telescopes are actively hunting for this elusive world. Its detection would not only confirm a long-suspected member of our solar system, but also enhance our understanding of planetary formation and the dynamic processes governing the outer regions of our cosmic neighborhood. The search for Planet 9 remains one of the most tantalizing quests in contemporary astronomy, offering the promise of a significant discovery in our own celestial backyard. Hot Jupiters are a class of exoplanets that bear striking similarities to Jupiter in terms of mass and size, but defy conventional expectations by orbiting extremely close to their host stars. These planets are located so near their stars that their orbital periods are usually less than 10 days, causing them to experience intense stellar radiation and heat. As a result, surface temperatures on hot Jupiters can soar to thousands of degrees Celsius, making these worlds blisteringly hot. The existence of hot Jupiters challenges traditional theories of planetary formation, which are largely based on our understanding of our own solar system. According to the widely accepted core accretion model, Gas giants like Jupiter should form beyond the snowline, the region in a young star system where temperatures are low enough for volatile compounds like water to condense into solid ice grains. In such environments, icy grains can rapidly accumulate to form a solid core, which can then gather a substantial envelope of gas. The proximity of hot Jupiters to their stars contradicts this model, as it would be nearly impossible for such massive planets to form in the high-temperature environments close to a star. This discrepancy has led scientists to propose alternate explanations. One leading hypothesis is the concept of planetary migration, which suggests that hot Jupiters originally formed beyond the snowline like conventional gas giants, but later migrated inward due to gravitational interactions with the protoplanetary disk or other planets. This inward journey could result in a dynamically unstable orbit that stabilizes close to the star. Additionally, tidal forces exerted by the host star could circularize the migrating planet ES orbit and lock it into synchronous rotation, where one side permanently faces the star. This results in a phenomenon known as tidal locking, contributing to the extreme temperature variations between the planet day and night sides. The discovery of hot Jupiters has sparked a re-evaluation of planet formation models and highlighted the dynamic and diverse architectures that planetary systems can assume. Their study continues to deepen our understanding of the myriad ways in which planets can evolve and maintain stable orbits under a wide range of stellar and environmental conditions. The discovery of the TRAPPIST-1 system has had a profound impact on our understanding of habitable worlds and has significantly expanded the scope of where we might look for extraterrestrial life. Announced in 2017, the TRAPPIST-1 system, located about 40 light-years from Earth, comprises 7 Earth-sized planets orbiting a cool, dim M-dwarf star. What makes this discovery particularly remarkable is that 3 of these planets reside in the star-S habitable zone, the region where conditions might be just right for liquid water to exist on the surface, a key criterion for habitability as we understand it. This system has challenged several preconceived notions about the conditions necessary for habitability. One of the major revelations is that potentially habitable worlds can exist around M-dwarf stars, which are the most common type of star in our galaxy. Unlike our Sun, M-dwarfs are smaller, cooler, and emit most of their radiation in the infrared spectrum. This means planets need to orbit very close to these stars to be in the habitable zone. In the case of TRAPPIST-1, all 7 planets orbit closer to their star than Mercury does to the Sun. Despite these tight orbits, the planets are not necessarily hostile. The TRAPPIST-1 star's lower luminosity and cooler temperatures create a compelling case for the potential of life in these tight-knit systems. The discovery has also emphasized the idea that habitable worlds might be much more common than previously thought. The sheer number of potentially life-supporting planets in just one system suggests that there could be many more such systems throughout the Milky Way. This realization energizes the search for life beyond Earth and prioritizes the study of M-dwarf systems in exoplanet research. Moreover, the close proximity and transit alignment of the TRAPPIST-1 planets make them ideal candidates for atmosphere characterization with current and upcoming telescopes, such as the James Webb Space Telescope. Detailed atmospheric studies can reveal the presence of gases that might indicate biological activity, such as oxygen and methane, further aiding the search for extraterrestrial life. The TRAPPIST-1 system has revolutionized our understanding of where habitable worlds might be found, suggesting that environments suitable for life might be much more widespread than previously believed. It underscores the significance of M-dwarf stars as potential hosts for life, prompting a reorientation of observational strategies and sparking renewed excitement in the quest to find life beyond our solar system. A super-Earth is a type of exoplanet that has a mass larger than Earth-S, but significantly less than that of the gas giants like Uranus and Neptune. Typically, these planets have masses up to about 10 times that of Earth. Super-Earths can be rocky like our planet, or they may also possess thick atmospheres. Depending on their mass and proximity to their host star, their composition likely ranges from terrestrial-like structures with significant quantities of rock and metal to ocean worlds or planets with extensive gas envelopes. The discovery of super-Earths has expanded our understanding of planetary formation and the diversity of planetary systems in the galaxy. They are particularly intriguing because their size places them in a range where they could potentially have Earth-like conditions, including the possibility of liquid water and habitable environments. However, their exact characteristics can vary widely. Some may have atmospheres that are too thick to support life as we know it, while others might be more habitable. Observations have shown that super-Earths are extremely common in our galaxy. Indeed, studies using data from the Kepler Space Telescope and other observational programs have revealed that they are among the most prevalent types of exoplanets. Estimates suggest that around 30 or more of Sun-like stars could host at least one super-Earth in their habitable zones, where conditions might be right for liquid water to exist. The high frequency of super-Earths raises fascinating questions about the likelihood of life beyond our solar system. It also challenges our current theories of planetary formation, which were initially based on our solar system's architecture, where no super-Earth exists. The fact that these planets are so common suggests that the processes that lead to their formation might be more robust than those that create Earth-sized planets like our own. In some ways, super-Earths represent a vital component of the exoplanetary landscape, offering a middle ground between terrestrial planets and gas giants. Their prevalence in our galaxy not only makes them compelling targets for the search for extraterrestrial life, but also drives ongoing efforts to understand the complex processes that govern planetary formation and evolution. Astronomers employ a variety of sophisticated methods to detect exoplanets, each with its unique advantages and challenges. These techniques have revolutionized our understanding of the universe, revealing thousands of worlds beyond our solar system. The most prominent methods include the transit method, the radial velocity method, direct imaging, astrometry, and gravitational microlensing. The transit method has been extraordinarily successful, particularly with space telescopes like Kepler and TESS. This method involves monitoring the brightness of a star over time. When an exoplanet crosses in front of its host star, it causes a slight temporary dimming of the star's light. By measuring these periodic dimming events, astronomers can infer the presence of a planet, estimate its size, and determine its orbital period. This method is particularly effective for identifying planets that orbit relatively close to their stars. The radial velocity method, also known as the Doppler spectroscopy method, detects exoplanets by measuring the star's motion toward or away from us. As a planet orbits a star, its gravitational pull causes the star to wobble slightly. This wobble affects the light spectrum of the star, causing periodic shifts toward red and blue wavelengths as the star moves away from and toward us, respectively. By analyzing these shifts, astronomers can infer the presence of a planet, its mass, and its orbital characteristics. This method is especially useful for detecting larger planets that exert a significant gravitational influence on their stars. Direct imaging is a more challenging and less common method, primarily due to the difficulty of distinguishing the faint light of an exoplanet from the overwhelming brightness of its host star. Nevertheless, advancements in technology, such as adaptive optics and coronagraphs, have enabled astronomers to capture images of exoplanets directly. Direct imaging is particularly valuable for studying the atmospheres and surface conditions of exoplanets, as it allows for the acquisition of detailed spectra. Astrometry involves precisely measuring the positions of stars in the sky and detecting tiny changes in their positions due to the gravitational pull of orbiting planets. This method requires exceptional precision and is less commonly used, but it can be effective for detecting larger planets at greater distances from their stars. Gravitational microlensing takes advantage of the gravitational field of a star to magnify the light of a background star when it passes in front. If the foreground star has a planet, the planet's gravitational field can create a distinctive signature in the light curve, indicating its presence. This method is particularly useful for finding planets at considerable distances from their stars, and even for detecting rogue planets that do not orbit any star. Each of these methods contributes valuable information about exoplanets, and when used in combination, they provide a more comprehensive understanding of planetary systems beyond our own. Together, they have illuminated the incredible diversity of exoplanets, from hot Jupiters to rocky super-Earths, expanding our knowledge of the universe and the potential for life beyond Earth. The Goldilocks zone, also known as the habitable zone, is a region around a star where conditions may be just right, neither too hot nor too cold for liquid water to exist on the surface of a planet. This concept borrows from the Goldilocks tale, indicating that the environment within this zone is just right for sustaining life as we know it. Scientists emphasize the importance of liquid water because it is a fundamental ingredient for life on Earth and is believed to be vital for life elsewhere in the universe. Liquid water acts as a solvent, allowing chemical reactions to occur that are necessary for the development of biological systems. The significance of the Goldilocks zone extends beyond just the presence of water. It also influences the types of atmospheres a planet can maintain. Planets in this zone have better chances of holding on to their atmospheres, which can shield life forms from harmful radiation and contribute to climate stability. For instance, Earth is within the Sun's Goldilocks zone, enabling it to support a diverse range of ecosystems. Finding exoplanets within their stars' habitable zones is a key focus for astrobiologists searching for potential extraterrestrial life, as these planets are the most promising candidates where life-supporting conditions could be present. Thus, the Goldilocks zone is a critical factor in the ongoing quest to determine whether we are alone in the universe. Certain exoplanets orbit their stars in exceptionally short periods, sometimes completing a full revolution in just a few hours. Due to their proximity to their host stars, these planets are often classified as ultra-short-period planets and are drawn so close to their stars that the gravitational forces between the bodies become immense. This tight orbit results in incredibly fast orbital speeds. Such extreme proximity also subjects these exoplanets to intense stellar radiation and tidal forces, leading to unique and harsh environments. The proximity of these planets to their stars means they experience temperatures rising into thousands of degrees Celsius, causing dramatic atmospheric and surface phenomena. For instance, these exoplanets may exhibit synchronized rotation, showing the same face to their star at all times, a state known as tidal locking. This situation results in one side of the planet being perpetually baked by stellar heat, while the opposite side remains in constant darkness and significantly cooler. The intense conditions raise intriguing questions about the types of atmospheres these planets might sustain and whether they could support life in forms radically different from those we are familiar with on Earth. This phenomenon underscores the diversity of planetary systems in the galaxy and challenges our understanding of the potential for life in such extreme environments. Rogue planets are fascinating celestial wanderers that drift through the galaxy without tethering to the gravitational pull of a host star. They have been ejected from their original planetary systems, possibly due to dynamic interactions with other planetary bodies or the gravitational influence of a nearby passing star. Despite this isolation, rogue planets demonstrate remarkable resilience in the interstellar medium, surviving in the cold depths of space through various means. These planets possess internal heat sources that can support them, despite the lack of sunlight. For example, many rogue planets retain the residual heat from their formation in their cores, slowly radiating warmth over eons. Additionally, some larger rogue planets may experience geothermal heating generated by radioactive decay within their interiors, similar to the processes found on Earth. This heat can create subsurface oceans beneath thick ice crusts, where liquid water might exist in a stable state. Such conditions raise intriguing possibilities for life, suggesting that these solitary travelers could harbor microbial ecosystems in deep, habitable environments, shielded from the rigors of space. Rogue planets challenge conventional notions of habitability and expand our understanding of where life might thrive in the universe. Binary star systems, where two stars orbit around a common center of mass, introduce complex gravitational dynamics that profoundly influence planetary formation and habitability. Planets in these systems typically fall into two categories based on their orbits: circumbinary planets, which orbit both stars in a wide, encompassing path, and circumstellar planets, which orbit just one of the stars, with the second star being a distant companion. The formation of planets in these systems faces significant challenges due to the fluctuating gravitational forces exerted by two stars. This can lead to destabilizing perturbations in the planetary disk, potentially preventing planetesimals from coalescing efficiently. However, if the initial conditions are favorable, planets can still form and thrive. For example, NASA's Kepler mission has identified several circumbinary planets, debunking previous assumptions that such environments were too chaotic for stable planetary formation. Regarding habitability, the twin suns of a binary system can influence a planet's climate and radiation exposure. A stable orbit in the habitable zone, where conditions for liquid water are met, must be maintained despite the gravitational tug-of-war. Circumbinary planets might experience more varied climate patterns due to the shifting positions of their twin suns, potentially resulting in complex seasonal changes. On the other hand, a circumstellar planet might face periodic gravitational disturbances from the secondary star, affecting its orbit and consequently its climate stability. Despite these challenges, the discovery of planets in binary systems broadens the scope of potential habitable worlds, illustrating the incredible adaptability of planetary systems in the galaxy. A lava world is an exoplanet characterized by extreme surface conditions, where vast regions are covered with molten rock. Such planets typically orbit very close to their host stars, enduring intense heat that keeps their surfaces in a perpetually molten state. One of the most noted examples of a lava world is the exoplanet 55 Cancri e, which orbits its star so closely that temperatures can soar above 2,000 degrees Celsius, melting rock into a searing lava landscape. Studying lava worlds provides crucial insights into planetary evolution, particularly regarding the thermal and geological processes at play. These planets offer natural laboratories for understanding the early stages of planetary development, resembling the molten conditions that Earth likely experienced shortly after its formation. Observations of lava worlds can shed light on processes such as planetary differentiation, where heavier materials sink to form a core and lighter materials create a crust. Moreover, the intense heat and volcanic activity on these worlds enable scientists to study outgassing processes, where volatile compounds are released from a planet's interior to the atmosphere, an essential aspect of atmosphere formation and evolution. Additionally, the extreme environments of lava worlds help to refine theoretical models of planet-star interactions, especially concerning tidal locking and planetary deformation under strong gravitational forces. By examining these fiery exoplanets, scientists can better grasp the range of planetary conditions across the universe, leading to a deeper understanding of the factors influencing planetary formation, stability, and potential habitability. Some exoplanets defy our traditional understanding of atmospheric composition by exhibiting features and elements that are unexpected or unlike anything observed within our own solar system. These peculiarities challenge existing models of planetary formation and atmospheric science, prompting researchers to rethink the chemical and physical processes that govern such environments. One striking example is the exoplanet WASP-33b, a type of gas giant known as a hot Jupiter. It orbits so close to its host star that its atmospheric temperatures can reach up to 3,000 degrees Celsius. At such extreme temperatures, the atmosphere contains exotic elements like titanium oxide, a molecule more commonly associated with stellar rather than planetary atmospheres. This discovery not only highlights the intense thermal dynamics of hot Jupiters, but also suggests the presence of strong thermal inversion layers, where temperature increases with altitude instead of decreasing. Another intriguing case is the exoplanet HD 189733b, which confounds scientists with its deep blue hue. Unlike Earth, whose blue color comes from oceans and atmospheric scattering, HD 189733b's color is attributed to a hazy atmosphere filled with high-altitude clouds of silicate particles. These particles are believed to form a type of exotic weather system where glassy rain falls sideways due to ferocious winds blowing at speeds of up to 5,000 miles per hour. Such enigmatic atmospheric compositions necessitate more complex and nuanced models of planetary formation and evolution. They also underscore the diversity of environmental conditions that can exist, potentially leading to novel chemical pathways and processes. By studying these extraordinary atmospheres, scientists are not only expanding our understanding of what is possible in planetary science, but also refining the criteria for habitability and the potential for diverse forms of life. The first image of a black hole, unveiled in April 2019, was captured using an innovative and unprecedented approach called Very Long Baseline Interferometry. This technique involved an international collaboration under the Event Horizon Telescope (EHT) project, which linked together 8 ground-based radio telescopes located across the planet. By synchronizing these telescopes to observe the same region of space simultaneously and combining their data, scientists effectively created a virtual Earth-sized telescope capable of achieving the high resolution necessary to capture the black hole. The black hole imaged is located at the center of the galaxy M87, approximately 53 million light-years away from Earth. The EHT targeted this supermassive black hole, known as M87, aiming to capture its event horizon, the boundary beyond which nothing, not even light, can escape its gravitational grip. Achieving this involved meticulously coordinating the telescopes, which were spread across continents, including sites in Hawaii, Chile, Spain, and the Antarctic, and required exceptionally precise atomic clocks to ensure synchronization down to the microsecond. To assemble the final image, the EHT team gathered petabytes of data over multiple nights and employed advanced algorithms to process and interpret the colossal data sets. The resulting image revealed a bright ring-like structure with a dark central region, consistent with theoretical predictions of a black hole's shadow. This iconic depiction not only provided visual confirmation of black holes' existence, but also offered a valuable opportunity to test and refine Einstein's general theory of relativity under extreme conditions. The successful capture of this image marks a monumental achievement in astrophysics, showcasing the power of global collaboration and technological innovation in expanding our understanding of the universe. The event horizon of a black hole is a fascinating and mysterious boundary, marking the point of no return. At this boundary, the gravitational pull becomes so overwhelming that not even light can escape its grasp, making the event horizon essentially an invisible surface. Anything that crosses it disappears from the observable universe. The concept of the event horizon is rooted in the theory of general relativity, which describes how objects with substantial mass warp the fabric of space-time. One key aspect of the event horizon is that it represents a threshold beyond which conventional physics ceases to be adequate. As an object approaches the event horizon, it experiences extreme gravitational forces that create extraordinary effects. For instance, from an external observer's perspective, time appears to slow down drastically for the object nearing the event horizon due to intense gravitational time dilation. To the observer, the object never seems to quite reach the event horizon. Instead, it appears to freeze and gradually fade away as its light becomes increasingly redshifted. For the object itself, however, the experience is markedly different. Upon crossing the event horizon, it would continue its descent into the black hole without noticing any sudden changes at the exact crossing point. According to classical general relativity, however, as it ventures further, it would be subjected to stronger tidal forces that could eventually spaghettify or stretch it lengthwise while compressing it sideways due to the black hole's immense gravitational gradient. Inside the event horizon lies the singularity, where the curvature of space-time becomes infinite and the laws of physics as we currently understand them break down. This presents one of the most profound puzzles in modern astrophysics, driving ongoing research to unify general relativity with quantum mechanics. The event horizon thus remains a key area of study, illuminating the limits of our understanding and pushing the boundaries of theoretical physics. The formation of supermassive black holes, which reside at the centers of most galaxies, including our Milky Way, is a subject of intense study and fascination in astrophysics. These cosmic giants can have masses millions to billions of times that of our Sun, and their origins are thought to be intricately linked with the evolution of galaxies themselves. One predominant theory suggests that supermassive black holes originate from the collapse of massive gas clouds in the early universe. These primordial clouds, containing vast amounts of hydrogen and helium, could rapidly collapse under their own gravity to form seed black holes with masses between 100 and 1,000 times that of the Sun. Over time, these seed black holes could grow significantly through a process known as accretion, as they attract and consume surrounding gas and dust, accumulating mass and releasing enormous amounts of energy in the form of radiation, often observed as quasars. Another possible formation mechanism involves the merging of smaller black holes in the dense environments of early galaxies. Frequent collisions and mergers of stars could lead to the formation of numerous stellar mass black holes. Over billions of years, these smaller black holes could merge to form increasingly larger ones, eventually evolving into supermassive black holes. Galactic mergers, which were more common in the early universe, likely played a critical role in this process, as the central black holes of colliding galaxies would eventually coalesce. The relationship between supermassive black holes and their host galaxies is also crucial. Observations reveal a strong correlation between the mass of a galaxy's central black hole and the mass of its bulge, suggesting a co-evolutionary process. The energy emitted by the accretion of matter onto the black hole can regulate star formation within the galaxy, influencing its growth and evolution. Despite numerous insights, the exact pathways forming these colossal black holes remain an active area of research, with ongoing observations and simulations aiming to unravel this cosmic mystery. Gravitational waves are ripples in the fabric of space-time, caused by some of the most violent and energetic processes in the universe. Predicted a century ago by Albert Einstein's general theory of relativity, these waves travel at the speed of light, carrying information about their cataclysmic origins as well as the nature of gravity itself. The detection of gravitational waves represents one of the most groundbreaking advances in astrophysics, offering a new way to study celestial phenomena, particularly black holes. Gravitational waves are generated by accelerating massive objects, such as when two black holes spiral into each other and merge. When these waves pass through Earth, they cause minuscule distortions in space-time that can be detected by highly sensitive instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO and Virgo. The first direct detection of gravitational waves, announced in 2016, came from such a merger of two black holes about 3 billion light-years away. This observation confirmed not only the existence of gravitational waves, but also provided the first direct evidence of binary black hole systems. Studying gravitational waves opens a unique window into the hidden workings of black holes. Unlike electromagnetic waves, gravitational waves are not easily absorbed or scattered by matter, allowing them to travel across the universe largely undisturbed. This means they can carry pristine information from extreme environments that are otherwise inaccessible. By analyzing the waveform of gravitational waves, scientists can infer the properties of their sources, including the masses, spins, and even the dynamics of the black holes involved. Furthermore, gravitational wave astronomy helps us understand the population and distribution of black holes in the universe. It can reveal the rates of stellar mass black hole mergers, offering insights into the environments where these black holes form and evolve. The data gathered also tests the predictions of general relativity under the most extreme conditions, potentially pointing to new physics if anomalies are found. In this way, gravitational waves not only enrich our understanding of black holes, but also augment our comprehension of fundamental physics. Hawking radiation is a theoretical prediction made by physicist Stephen Hawking in 1974, suggesting that black holes are not entirely black, but can emit radiation due to quantum effects near their event horizons. This groundbreaking idea arises from the interplay between quantum mechanics and general relativity, two pillars of modern physics that typically operate in distinct realms: quantum mechanics at the atomic scale and general relativity at cosmic scales. Hawking radiation is a consequence of the peculiar properties of quantum fields in curved space-time near the event horizon of a black hole. The strong gravitational field is thought to cause pairs of virtual particles, one particle and its antiparticle counterpart, to spontaneously form from the quantum vacuum. Normally, these pairs annihilate each other almost immediately. However, if such a pair forms right at the edge of the event horizon, it is possible for one particle to fall into the black hole while the other escapes into space. To an outside observer, this escaping particle appears as radiation emanating from the black hole. The particle that falls into the black hole effectively has negative energy relative to the outside universe, causing the black hole to lose a tiny amount of mass over time. The concept of Hawking radiation challenges our understanding of black holes in several profound ways. First, it implies that black holes are not eternal over incredibly long timescales. They can evaporate completely as they emit Hawking radiation and lose mass. This leads to the intriguing possibility that black holes can ultimately vanish, releasing their energy back into the universe. Moreover, Hawking radiation touches on the puzzling issue of information loss in black holes. According to classical general relativity, all information about the matter that falls into a black hole is lost to the rest of the universe, residing within the event horizon and ultimately disappearing with the black hole's evaporation. However, this notion conflicts with the principles of quantum mechanics, which assert that information must be preserved. This tension between the two theories has sparked significant debate and research, leading to new concepts such as the holographic principle and the idea of black hole complementarity. Hawking radiation thus serves as a tantalizing bridge between quantum mechanics and general relativity, pointing toward the need for a unified theory of quantum gravity that can reconcile these seemingly incompatible domains. Black holes have an astounding ability to distort time and space around them due to their immense gravitational fields, a phenomenon predicted by Einstein's general theory of relativity. The stronger the gravitational field, the more pronounced the distortion, reaching extremes near the event horizon, the boundary beyond which nothing can escape the black hole's pull. Firstly, let us consider the concept of space-time, which combines the three dimensions of space with the dimension of time into a single four-dimensional continuum. A black hole exerts such a strong gravitational force that it warps this continuum to an extreme degree. Imagine space-time as a two-dimensional rubber sheet. Placing a heavy object on this sheet will cause it to stretch and curve around the object. Similarly, a black hole creates deep pits in the fabric of space-time, dramatically bending the paths that light and matter take when passing near it. This warping of space has intriguing observational consequences. Objects near a black hole will follow curved trajectories as they are deflected by the warped space-time, resulting in phenomena like gravitational lensing, where light from background stars or galaxies bends around the black hole, creating multiple or distorted images. The stronger the black hole's gravitational field, the more pronounced this lensing effect becomes, providing astronomers with indirect evidence of black holes. Time, too, experiences significant distortion near a black hole, a phenomenon known as gravitational time dilation. According to relativity, the stronger the gravitational field, the slower time ticks relative to an observer at a distance. Near a black hole, this effect is magnified to an extraordinary extent. For an object approaching the event horizon, time appears to slow down drastically from the perspective of a distant observer. If a person were watching from a safe distance, they would see the object gradually slow and freeze at the boundary, never actually observing it cross into the black hole. However, the object itself would perceive time normally and would cross the event horizon without noticing. This extreme time dilation and spatial distortion have profound implications for our understanding of the universe. They challenge our perceptions of what is possible within the realms of physics and provide a unique laboratory for testing the predictions of general relativity. These extraordinary effects underline the importance of black holes in the broader context of cosmic evolution and the ongoing quest to understand the fundamental nature of reality. A quasar, short for quasi-stellar object, is one of the most luminous and energetic phenomena in the universe and is intrinsically linked to supermassive black holes. These extraordinary objects reside in the centers of galaxies where they draw in vast amounts of surrounding matter. As this matter falls toward the black hole, it forms an accretion disk, a swirling, superheated disk of gas, dust, and other material. The extreme gravitational forces exerted by the black hole accelerate and compress this material, causing it to emit staggering amounts of electromagnetic radiation, particularly in the radio, ultraviolet, and X-ray wavelengths. The immense brightness of quasars is primarily due to the processes occurring in this accretion disk. Friction and collision among the particles within the disk generate immense heat and release energy, which travels outward as intense radiation. Quasars can outshine entire galaxies despite their relatively compact size. Some quasars are so luminous that they can be observed billions of light-years away, providing valuable insights into the early universe. The relationship between quasars and black holes offers a glimpse into the dynamics of galaxy evolution. The central supermassive black hole powers the quasar by consuming the surrounding material at an astonishing rate. This accretion process not only fuels the quasar's brilliant radiation, but also plays a role in regulating star formation within the host galaxy. The energy radiated by the quasar can drive powerful outflows of gas and dust, which may either trigger star formation by compressing nearby clouds or inhibit it by blowing away the raw material needed for star creation. Thus, quasars are pivotal in shaping their galactic environments over cosmic timescales. Moreover, the observation of quasars has been instrumental in enhancing our understanding of supermassive black holes. The first quasar discovered, 3C273, led to the realization that these objects are closely tied to black holes and are not merely distant stars or galaxies. Quasars also serve as beacons that illuminate the structure and composition of the universe, allowing astronomers to study the intergalactic medium and trace large-scale cosmic structures. As such, these astounding objects continue to be a focal point of research, aiding in the exploration of fundamental questions about the nature of matter, energy, and the evolution of the cosmos. Binary black hole systems, comprising two black holes orbiting around a common center of mass, exhibit behaviors that are markedly distinct from solitary black holes. These interactions lead to complex gravitational dynamics and fascinating astrophysical phenomena that provide rich opportunities for observation and study. One of the most striking features of binary black hole systems is the emission of gravitational waves. As the two black holes orbit each other, their immense gravitational fields cause ripples in space-time that propagate outward at the speed of light. These gravitational waves carry away energy from the system, causing the black holes to gradually lose orbital separation and spiral closer together. The closer they get, the stronger the gravitational wave signals become, eventually culminating in a dramatic merger. The detection of these waves, as achieved by observatories like LIGO and Virgo, provides direct evidence of binary black hole systems and allows scientists to study the properties of black holes, such as their masses and spins, with unprecedented precision. The merger event itself is an extraordinary spectacle involving the fusing of two black holes into a single, more massive black hole. This process releases a tremendous amount of energy in the form of gravitational waves, often more than the combined energy output of all the stars in the observable universe for the brief moment of the merger. These merger events also provide crucial tests for general relativity, allowing researchers to explore the behavior of gravity in extreme conditions. Before merging, binary black hole systems also exhibit unique dynamical behaviors. The intense gravitational interaction between the pair can lead to phenomena such as orbital precession, where the orientation of the orbit changes over time. This effect is similar to the precession of a spinning top, but it occurs due to the complex interplay of the black hole's masses and spins. The geometry of space-time around the binary system becomes highly distorted and dynamic, a stark contrast to the relatively static warping found around solitary black holes. Furthermore, the formation and evolution of binary black hole systems also differ significantly from their solitary counterparts. Binary systems can form both from the collapse of massive stellar binaries and through dynamic interactions in dense stellar environments, such as globular clusters. These formation scenarios can influence the characteristics of the black holes, such as their masses, spins, and the eccentricities of their orbits. Binary black hole systems offer a dynamic and complex laboratory for understanding gravitational physics, stellar evolution, and the nature of black holes. Their distinctive behaviors, particularly their emission of gravitational waves and their eventual mergers, provide invaluable data that enhances our comprehension of the cosmos. The firewall paradox is a thought-provoking problem in theoretical physics that challenges our understanding of black holes and the principles of quantum mechanics and general relativity. It arises from attempts to reconcile the behavior of black holes with the fundamental tenet of quantum mechanics that information cannot be destroyed. According to general relativity, an observer falling into a large black hole would not experience significant changes as they cross the event horizon due to the principle of equivalence, which states that the laws of physics in a small region of space-time are the same in a freely falling frame as they would be in the absence of gravity. This means that the event horizon should not be a special or violent place. Instead, it should be smooth and regular. However, from the perspective of quantum mechanics, and in particular Hawking radiation, the story becomes more complicated. Hawking proposed that black holes emit radiation due to quantum effects near the event horizon, leading to the gradual reduction in the mass of the black hole over time. This process implies that the black hole can eventually evaporate entirely, raising the question of what happens to the information about everything that fell into the black hole. If the information is lost, it would violate a fundamental tenet of quantum mechanics, which asserts that information must be preserved. To resolve this violation, some theorists suggested that the information might be encoded in the Hawking radiation itself. But this proposal leads to another issue. If there is entanglement between particles just inside and outside the horizon to preserve information, breaking this entanglement would require a significant release of energy, effectively creating a firewall at the event horizon. This firewall would incinerate anything falling into the black hole, contradicting the principle of equivalence that posits a smooth horizon. Thus, the firewall paradox forces a choice between one of three deeply held principles: the smoothness of the event horizon, the preservation of information, or the rules of quantum field theory in curved spacetime. Resolving the paradox would likely require a deeper understanding of how gravity and quantum mechanics coexist, pointing toward a theory of quantum gravity. This ongoing debate underscores fundamental questions about the nature of black holes, the fabric of spacetime, and the ultimate laws of physics that govern our universe. Astronomers and cosmologists have long been puzzled by the existence of intermediate mass black holes, which range from 100 to 100,000 times the mass of our Sun. These black holes create a gap in our understanding of black hole formation, nestled between the well-established categories of stellar mass black holes and supermassive black holes. Stellar mass black holes are known to form from the collapse of massive stars, typically between 10 to 100 solar masses, while supermassive black holes, found at the centers of galaxies, tip the scales at millions to billions of solar masses. The existence of black holes that fall in the intermediate range does not align neatly with either of these known formation processes. One challenge posed by intermediate mass black holes is the ambiguity surrounding their origin. The formation of stellar mass black holes through supernova explosions does not usually yield black holes of such intermediary sizes. Similarly, the mechanisms involved in the births of supermassive black holes, which involve accretion of mass over billions of years, or the merging of multiple smaller black holes in dense star clusters, do not easily explain the presence of these moderately sized entities. Moreover, the difficulty lies in the detection and study of these black holes, as they are neither small enough to be easily seen through X-ray emissions from binary systems, nor large enough to influence their galactic environments as strikingly as their supermassive counterparts. This fascinating middle ground challenges scientists to rethink and broaden their models of black hole growth and evolution, potentially requiring entirely new mechanisms or stages in the life cycles of black holes. The cosmic web is a vast, intricate network of filaments composed primarily of dark matter and gas, and it underpins the large-scale structure of the universe. This web can be visualized as a three-dimensional spider web stretching across the cosmos, where the densest knots and threads serve as the scaffolding for galaxies and clusters of galaxies to form. Stretching across billions of light years, the cosmic web is the grand architecture within which all cosmic structures are embedded. The nodes of this web, where filaments intersect, are especially dense and act as gravitational wells that draw in more matter, leading to the formation of galaxy clusters. The cosmic web significantly influences the universe's overall shape and dynamics. For starters, the distribution of dark matter within the web gravitationally attracts ordinary matter, catalyzing star formation and the development of galaxies in these dense regions. Additionally, the filamentary structures facilitate the flow of gas and galaxies along their paths, contributing to the ongoing growth and evolution of cosmic structures. This continuous movement along the web helps to distribute elements necessary for star and planet formation across different regions of the universe. Therefore, the cosmic web not only forms a map of the universe as vast and varied terrain, but also plays a crucial role in the processes that lead to the complex structures we observe today, ranging from individual galaxies to enormous superclusters of galaxies. Galaxy clusters serve as cosmic laboratories that provide compelling evidence for the existence of dark matter through several key observations. First and foremost, when astronomers measure the velocities of galaxies within a cluster, they find that these galaxies move at such high speeds that the visible matter alone, including stars and gas, cannot account for the gravitational pull necessary to keep them bound together. This discrepancy suggests that there must be an additional, invisible form of matter-dark matter that provides the extra gravitational force needed to stabilize the cluster. Furthermore, gravitational lensing offers another powerful line of evidence. This phenomenon occurs when the massive gravitational field of a galaxy cluster bends and distorts the light from background objects, such as more distant galaxies. By analyzing the degree of this distortion, scientists can map the distribution of mass within the cluster. Remarkably, these mass maps reveal much more mass than what is visible through direct observations of stars and hot gas alone, once again pointing to the presence of dark matter. Another key piece of evidence comes from the study of the temperature and distribution of the hot gas in galaxy clusters, as observed through X-ray emissions. This hot gas, which comprises most of the visible mass in a cluster, is held in place by gravity. The temperature of the gas indicates the depth of the gravitational well it resides in. When scientists perform these calculations, they find that the gravitational well is far deeper than can be accounted for by the visible gas and stars alone, implying that dark matter must be providing the additional gravitational pull. Together, these various lines of evidence converge to strongly support the existence of dark matter, which is thought to make up about 85% of the total mass in the universe. Cosmic voids are vast, cavernous regions of space that contain very few galaxies or matter of any kind. These empty expanses can span tens of millions of light-years across and are some of the largest structures in the universe. Despite their emptiness, cosmic voids play a crucial role in our understanding of the large-scale structure of the universe. They are essentially the dark counterpoints to the dense, bright regions of the cosmic web, where galaxies congregate along filaments and clusters. The study of these voids provides valuable insights into the distribution of matter, the properties of dark energy, and the overall evolution of cosmic structures. One of the key revelations from studying cosmic voids is their use in improving our understanding of dark energy, the mysterious force driving the accelerated expansion of the universe. By examining the distribution, size, and shape of voids, scientists can gather clues about how dark energy acts over vast distances and over different epochs of the universe's history. The expansion rate of voids, for example, can offer indirect measurements of the universe's expansion rate, offering a complementary method to other observations like supernovae. Moreover, cosmic voids help refine our models of galactic formation and distribution. The properties of voids, such as their scarcity of galaxies and low-density environment, make them excellent laboratories for studying processes that would be impossible to isolate in denser regions. For instance, the absence of significant gravitational interaction in voids allows scientists to observe the impacts of cosmic phenomena like galactic winds and small-scale structure formation without the interfering effects present in more crowded areas. In these seemingly endless and empty voids of space, where the silence of the cosmos reigns, some of the most fundamental forces that shape our universe are laid bare. Here, the intricate dance of gravity, dark energy, and other cosmic forces can be dissected and understood in ways that provide a unique and invaluable perspective. This understanding complements the insights we gain from studying the dense knots and filaments of the cosmic web, where matter congregates in grand structures that span light years. By exploring both the emptiest and the most crowded regions of the universe, we can piece together a more complete and nuanced picture of how everything around us came to be. If you are fascinated by the mysteries of the universe and eager to dive deeper into the latest discoveries, we invite you to join our growing community. Subscribe to our channel to stay updated on the most groundbreaking research, stunning visualizations, and thought-provoking discussions in the field of astronomy and cosmology. Together, let's unravel the secrets of the cosmos and embark on a journey of exploration that knows no bounds. The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. Carl Sagan. The origin of the universe, a journey through time and thought. For millennia, humanity has been captivated by the mysteries of existence, seeking to unravel the nature of the universe and its origins. The question of how the universe began has always held a central place in human thought, acting as a cornerstone not only for scientific inquiry, but also for philosophical and theological contemplation. This profound curiosity has driven civilizations across the globe to explore the fundamental questions: what existed before us? How did everything come into being? Throughout history, different cultures have sought to answer these questions through a rich tapestry of myths, religions, and philosophical treatises, each creating intricate belief systems and rituals that reflect their understanding of the cosmos. In ancient times, every society developed its unique explanation for the creation of the world, often rooted in careful observations of natural phenomena such as the changing seasons, lunar phases, or the movement of planets across the sky. These early explanations, though they may appear simplistic by modern standards, were deeply connected to the natural world and represented humanity as first attempts to make sense of the incomprehensible forces shaping their environment. These myths were not just stories, they were profound reflections of the human experience, imbued with symbolism and meaning that conveyed the essence of existence from the perspective of those who lived in a world of mysteries. Mythology and religion served as the primary frameworks for understanding the origin of the world for countless generations. From the ancient Egyptian gods who shaped the cosmos out of primordial chaos, to the Greek titans who imposed order on the abyss, and the Sumerian deities who forged the universe from the bodies of vanquished giants, these narratives were rich with symbolism that explained the creation of the world through the lens of human perception. These myths, deeply intertwined with religious beliefs, became the bedrock of entire civilizations, passed down through generations and remaining central to people's understanding of the cosmos. As human knowledge advanced, so too did our ability to perceive the universe in new ways. The development of science marked a transformative shift in how humanity approached the question of the universe's origin. With a focus on observation, experimentation, and empirical evidence, science began to offer new, more structured models of the cosmos that gradually supplanted the mythological explanations of old. Among these scientific breakthroughs, one of the most revolutionary was the Big Bang theory, which provided a radically new perspective on cosmology and our place within it. The Big Bang theory, supported by key observations such as the redshift of galaxies and the cosmic microwave background radiation, proposed that the universe began as an infinitely small, dense point, a singularity where all matter and energy were concentrated. This singularity then underwent a massive explosion, creating space, time, and everything that exists within it. This concept of an expanding universe with galaxies drifting apart over billions of years fundamentally changed our understanding of the cosmos and our place within it. The introduction of the Big Bang theory marked a turning point in modern cosmology, inspiring a wave of new research and exploration into the origins of the universe. This theory opened up new avenues for understanding the processes that occurred in the earliest moments after the universe's creation, and it continues to be a central focus of scientific inquiry. Today, scientists employ advanced technologies and sophisticated observational methods to probe the mysteries of the cosmos. From the study of black holes to the detection of gravitational waves, each discovery bringing us closer to answering the age-old question, how did our universe come into existence? In our ongoing quest to understand the universe, we are reminded that the story of creation is not just a scientific endeavor, but a deeply human one. It reflects our desire to connect with the cosmos, to understand our place in the grand scheme of existence, and to find meaning in the vastness of space. As we continue to explore the universe, we are not only uncovering the secrets of the cosmos, but also discovering more about ourselves, our origins, our place in the universe, and our future in the ever-expanding expanse of space. The Big Bang Theory, unveiling the origins and evolution of the universe. The Big Bang Theory, one of the most profound scientific concepts ever developed, posits that approximately 8 billion years ago, the entirety of the universe's matter and energy was concentrated in an incredibly small and dense point known as a singularity. This singularity was the birthplace of everything we know today, containing the entire mass and energy of the universe within a space so infinitesimally small that it defies human comprehension. The theory asserts that at this singular moment, a rapid expansion began, marking the inception of what we now call the Big Bang. It is crucial to understand that the term explosion is metaphorical, rather than an explosion in the conventional sense. It was an immense and sudden expansion of space itself, initiating the universe's ongoing evolution. This initial expansion set in motion a series of processes that would eventually lead to the formation of the universe as we know it. In the first fractions of a second following the Big Bang, the universe existed in an extremely hot and dense state, where elementary particles like quarks and gluons roamed freely in a primordial soup known as quark-gluon plasma. At this stage, the conditions were so extreme that atoms could not yet form, as the intense heat and energy kept matter in a highly ionized and chaotic state. However, as the universe continued to expand, it began to cool, allowing quarks to combine into protons and neutrons within the first seconds after the expansion began. This moment of cooling was a pivotal event in the universe's history, as it set the stage for the formation of the first atomic nuclei. Through a process known as nucleosynthesis, these protons and neutrons began to fuse together, creating the first light elements such as hydrogen and helium. These primordial elements would later serve as the building blocks for the formation of stars, galaxies, and other cosmic structures. The significance of this early nucleosynthesis cannot be overstated, as it laid the foundation for the universe's complex architecture, which would evolve over billions of years. Despite the groundwork laid by nucleosynthesis, it would take approximately 380,000 years after the Big Bang for the universe to cool sufficiently for photons, the basic units of light, to move freely through space. Before this cooling, the universe was in an opaque state, with light constantly being scattered by the hot plasma, preventing it from traveling any significant distance. However, as the temperature dropped to a critical point, atoms began to form, and photons were no longer impeded by the plasma, allowing the universe to become transparent to light. This moment, known as the recombination epoch, was a turning point in cosmic history. It is during this epoch that the cosmic microwave background CMB radiation, a faint glow that permeates the entire universe, was first emitted. The CMB is one of the most compelling pieces of evidence for the Big Bang Theory, offering a snapshot of the universe in its infancy. The discovery of the cosmic microwave background radiation in 1965 provided a powerful confirmation of the Big Bang Theory. This radiation, which fills the universe uniformly, is the residual heat from the Big Bang, and its study allows scientists to peer back in time to the very earliest stages of the universe's existence. By analyzing the CMB, researchers can glean insights into the conditions that prevailed just moments after the Big Bang, offering a unique opportunity to explore the universe's development from its very inception. In the billions of years that followed the Big Bang, the universe continued to expand and cool, allowing gravitational forces to coalesce matter into the first stars and galaxies. These early stars, in turn, became the cosmic forges where heavier elements such as carbon, oxygen, and iron were created through nuclear fusion. These elements, synthesized in the hearts of stars, would later become the essential building blocks for planets and, ultimately, for life itself. The formation of these stars and galaxies marked the beginning of a new chapter in the universe's evolution, as complex structures began to emerge from the primordial chaos. Today, the Big Bang Theory remains the dominant model in cosmology, providing a comprehensive framework for understanding both the origin and evolution of the universe. Modern research continues to deepen our understanding of the processes that occurred in the moments following the Big Bang, as well as to explore the mysterious components of the universe, such as dark matter and dark energy. These enigmatic substances are believed to constitute the majority of the universe's mass and energy, yet they remain largely elusive, influencing the universe's fate in ways that scientists are only beginning to comprehend. As we continue to explore the cosmos, the Big Bang Theory serves as a guiding light, helping us to unravel the mysteries of the universe's origins and its ongoing evolution. Each new discovery brings us closer to understanding the intricate web of forces and processes that shape the universe from its birth in the Big Bang to the vast, complex cosmos we observe today. Through this lens, we not only seek to understand the universe's past, but also to anticipate its future, as we strive to answer the ultimate question: what is the fate of the universe, and what role do we play in its grand narrative? The inflation hypothesis, unraveling the early moments of the universe. To account for the remarkable uniformity in the distribution of matter across the universe and the homogeneity observed in the cosmic microwave background, CMB radiation, scientists have proposed the inflation hypothesis. This hypothesis emerged as a response to several key questions that remained unresolved within the framework of the classical Big Bang theory. The inflation hypothesis posits that at an extraordinarily early stage in the universe's history, approximately 1036 seconds after the Big Bang, the universe underwent a phase of rapid and exponential expansion. This expansion occurred at an astonishing speed, such that in less than a fraction of a second, the universe's size increased by an unimaginable factor, expanding billions of times in mere moments. The inflationary phase played a pivotal role in shaping the universe as we observe it today. One of the most critical contributions of inflation is its ability to explain the remarkable uniformity in the distribution of matter throughout the cosmos. Without this inflationary period, the universe might have exhibited significant irregularities, with vast regions of dense matter interspersed with empty voids. Inflation effectively smoothed out these initial irregularities, distributing matter more evenly across the vast expanse of space and ensuring the uniformity that characterizes the observable universe. In addition to explaining matter distribution, the inflation hypothesis also addresses the apparent flatness of the universe on large scales. According to the principles of general relativity, gravity should have induced a curvature in space-time, leading to a highly curved universe on large scales. However, observations reveal that the universe appears remarkably flat, a feature that the inflationary model accounts for by suggesting that during the rapid expansion, space stretched so extensively that any initial curvature became imperceptible. This process is akin to taking a highly curved surface and stretching it so much that it appears almost flat, thereby explaining the observed flatness of the universe. Another significant consequence of the inflation hypothesis is its ability to explain the uniformity of the cosmic microwave background radiation. Within the classical Big Bang theory, it is challenging to understand why regions of the universe that are located on opposite sides of the sky and that could not have exchanged information due to the finite speed of light appear so strikingly similar. The inflation hypothesis resolves this conundrum by asserting that before the inflationary phase, all parts of the observable universe were in close proximity within a very small volume. This proximity allowed for the exchange of information and the establishment of common physical conditions across the entire universe. After inflation, these regions were separated by vast distances but retained their similar characteristics as observed in the CMB. Moreover, the inflation hypothesis predicts the existence of tiny quantum fluctuations in the very early universe, which during the phase of exponential expansion were stretched to cosmic scales. These fluctuations manifested as slight variations in matter density, which later became the seeds for the formation of galaxies and other large-scale cosmic structures. This prediction aligns with the small anomalies observed in the cosmic microwave background, which correspond to these early density variations and have shaped the universe's structure as we know it today. Over the past few decades, the inflation hypothesis has garnered substantial support from observational evidence. One of the most significant milestones came in 2013 when data from the Planck satellite revealed that the cosmic microwave background radiation exhibits characteristics that align with predictions made by the inflationary theory. In particular, the satellite detected traces of the very quantum fluctuations that should have originated during the inflationary period, providing a strong endorsement of the hypothesis. Despite these successes, the inflation hypothesis remains an area of active research and debate within modern cosmology. Competing theories, such as the Big Bounce scenario, offer alternative explanations for the universe's origin and evolution without necessitating an inflationary phase. The Big Bounce model, for instance, suggests that the universe undergoes cyclic phases of contraction and expansion, avoiding the singularity and inflation altogether. Nevertheless, the inflation hypothesis continues to be the most widely accepted model, explaining many of the observed features of our universe with remarkable consistency. As research into inflation and its alternatives progresses, it will continue to play a central role in advancing our understanding of cosmology. Scientists are leveraging the most advanced technologies and instruments available, such as gravitational wave observatories and next-generation telescopes, to probe even deeper into the universe's early history. These tools will enable astronomers and physicists to test the predictions of the inflation hypothesis with greater precision, potentially confirming or refuting the model and offering new insights into the origins and evolution of the cosmos. In the quest to understand the universe's earliest moments, the inflation hypothesis stands as a cornerstone of modern cosmology, providing a framework for interpreting the vast and complex history of the cosmos. Whether through supporting evidence or challenges from alternative theories, the study of cosmic inflation promises to continue driving the frontier of our knowledge, bringing us ever closer to unraveling the mysteries of the universe's inception and its ultimate fate. Cosmological paradoxes and alternative hypotheses, exploring the frontiers of the universe. Although the Big Bang theory remains the cornerstone of modern cosmology, it is not without its challenges and unresolved questions, which have spurred the development of alternative hypotheses. These alternative models aim to provide new perspectives on the origin and evolution of the universe, offering innovative approaches to addressing the cosmological paradoxes that the Big Bang theory leaves unanswered. One such hypothesis is the cyclic universe model, also known as the cycle model. According to this idea, the universe did not have a singular beginning, but instead undergoes endless cycles of expansion and contraction. In this model, the universe periodically collapses into a state of extremely high density, similar to a singularity, and then expands again, undergoing a process analogous to the Big Bang. Each cycle begins with a new Big Bang, followed by billions of years of expansion and cooling until gravitational forces eventually lead to another collapse. This cyclical process implies that the universe has no definitive beginning or end. Instead, it is an eternal sequence of cosmic rebirths, with each new expansion effectively erasing the traces of the previous cycle. This concept has profound implications, both scientifically and philosophically, as it challenges the notion of a linear timeline and introduces the possibility of a universe that is infinite in both time and space. Another intriguing hypothesis is the concept of the multiverse, which posits the existence of an infinite number of universes, each with its unique physical laws, parameters, and even space-time structures. According to this hypothesis, our observable universe is merely one among countless others in a vast multiverse. The idea of the multiverse extends beyond the traditional scope of cosmology, touching on the boundaries of what can be considered a scientific theory. Many aspects of the multiverse may lie beyond direct observation and experimental verification, leading to fascinating yet controversial discussions within the scientific community. Within the framework of the multiverse, many of the perplexing characteristics of our universe could be explained. For example, the question of why physical constants have the specific values they do might find resolution in the context of the multiverse. Perhaps there are myriad universes with different sets of constants, and we happen to live in one where the conditions are just right for life to exist. This idea, known as the anthropic principle, suggests that our universe might not be unique, but rather a part of a larger, more complex structure. According to this principle, the observed properties of the universe are a consequence of our existence within it. If the universe were different, we simply wouldn't be here to observe it. However, the multiverse hypothesis faces significant scientific and philosophical challenges. One of the most pressing issues is the problem of falsifiability. If other universes are inherently inaccessible to observation, how can we prove or disprove their existence? This raises fundamental questions about the nature of scientific inquiry itself. Can a theory be considered scientific if it is not subject to empirical verification? The multiverse hypothesis thus sits at the edge of scientific discourse, prompting debates about the limits of human knowledge and the scope of scientific theories. Another alternative to the Big Bang theory is the Big Bounce hypothesis, which suggests that the current phase of the universe's expansion was preceded by a phase of contraction. According to this theory, the universe did not emerge from a singularity in a one-time event, but rather from a big rebound following a previous contraction. This model attempts to bridge the gap between the classical Big Bang concept and the cyclic universe idea, proposing that what we perceive as the beginning of our universe might actually be a transitional phase in an ongoing cycle of cosmic events. In this scenario, the singularity is not the absolute beginning of everything, but a critical juncture in a continuous series of expansions and contractions, each cycle giving rise to a new phase of cosmic evolution. These alternative hypotheses, while still speculative, open up intriguing possibilities for further research and philosophical reflection. They challenge our conventional understanding of the universe's origins and push the boundaries of what we can comprehend with our current scientific tools and theories. Moreover, they raise important questions about the limits of human knowledge. How far can we go in our quest to understand the universe, given the constraints of our methods and technologies? As cosmology continues to advance, it remains one of the most dynamic and rapidly evolving fields of science, where each new discovery has the potential to radically alter our perception of reality and our place within it. In the ongoing search for answers to these fundamental questions, scientists are developing new theories and conducting increasingly precise observations, aiming to shed light on the universe's greatest mysteries. Whether through refining existing models or proposing entirely new frameworks, the pursuit of knowledge in cosmology is a journey that continuously expands the horizons of human understanding. As we probe deeper into the cosmos, we are not only exploring the origins of the universe, but also confronting the profound questions about the nature of existence itself. Questions that may ultimately redefine our understanding of the universe and our role within it. Cosmic microwave background radiation, the faint echoes of the universe's birth. One of the most profound achievements in modern cosmology is the discovery and study of cosmic microwave background radiation (CMBR). This faint but omnipresent radio signal, which permeates the entirety of space, is a relic of the Big Bang, a subtle yet enduring pulse that echoes across the cosmos. First detected in 1965 by American physicists Arno Penzias and Robert Wilson, the CMBR provided compelling evidence in support of the Big Bang theory, offering a unique window into the universe's infancy and allowing us to glimpse the very earliest moments of its existence. The cosmic microwave background radiation originated approximately 380,000 years after the Big Bang, during a pivotal period when the universe had cooled sufficiently to allow atoms to form and for light or photons to travel unimpeded through space. Prior to this epoch, the universe was a seething plasma of free electrons and nuclei which scattered and absorbed light, rendering the cosmos opaque. However, as the universe expanded and cooled to about 3000 Kelvin, electrons and protons began to combine to form neutral hydrogen atoms. This transition allowed photons to move freely for the first time, giving rise to the CMBR, effectively the first light of the universe. As this primordial radiation has spread across the expanding universe over billions of years, it has cooled and today is observed in the microwave spectrum at a temperature of approximately 2.7 Kelvin above absolute zero. Although this radiation is incredibly faint, it holds within it a wealth of information about the early universe, preserving an imprint of the universe's structure and composition during its earliest stages. The study of CMBR has become a cornerstone of cosmology, providing insights into the universe's age, composition, and overall geometry. Through the analysis of the CMBR, scientists have been able to extract precise data about the age of the universe, currently estimated at about 13.8 billion years, as well as its composition and geometry. For instance, minute variations in the CMBR's temperature correspond to slight fluctuations in density that existed in the early universe. These fluctuations later became the seeds from which galaxies and large cosmic structures formed. The detailed study of these temperature anomalies, revealed through high-resolution maps of the CMBR, has confirmed the existence of the initial quantum fluctuations predicted by the inflation hypothesis, further solidifying our understanding of the universe's formative moments. Significant advancements in our understanding of the CMBR have been made possible by satellite missions such as COBE Cosmic Background Explorer, WMAP Wilkinson Microwave Anisotropy Probe, and Planck. These missions have provided high-resolution maps of the temperature anomalies within the CMBR, allowing scientists to refine key parameters of the Big Bang model. These include the precise estimation of the universe's age, the proportions of its matter and energy components, and the overall curvature of space-time. The data collected by these missions not only reinforced the basic predictions of the Big Bang theory, but also allowed for a deeper exploration of the universe's most elusive components. Moreover, studies of the CMBR have provided crucial insights into the presence of dark matter and dark energy, mysterious substances that constitute the vast majority of the universe's total mass and energy, yet remain invisible and poorly understood. The subtle temperature variations in the CMBR offer indirect evidence of these components, revealing their significant influence on the universe's expansion and evolution. The patterns observed in the CMBR suggest that dark matter played a critical role in the formation of the first galaxies, while dark energy is believed to drive the accelerated expansion of the universe. The CMBR also serves as a tool for exploring the topology of the universe, the study of its overall shape and structure. If the universe had a closed or complex topology, such features would manifest in the characteristics of the CMBR. However, despite extensive research, no definitive evidence has been found to suggest that our universe has an unusual topology, implying that it is most likely infinite or at least extraordinarily large in scale. The study of the CMBR continues to be one of the most vital endeavors in modern cosmology, as it offers unparalleled insights into the universe's earliest moments and ongoing evolution. Future missions and more advanced observational instruments are expected to delve even deeper into the mysteries of the CMBR, potentially uncovering additional secrets about the universe's origin, structure, and ultimate fate. Each new discovery in this area brings us closer to answering the most fundamental questions about our cosmic home: how it began, how it has evolved, and what its future may hold. As scientists continue to explore the echoes of the Big Bang, they are not only reconstructing the history of the universe, but also advancing our understanding of the cosmos on the most profound levels, deepening our appreciation for the intricate and awe-inspiring nature of reality itself. The discovery of cosmic microwave background radiation, a serendipitous leap in cosmology. The discovery of cosmic microwave background radiation, CMBR, in 1965 stands as one of the most momentous achievements in the history of cosmology. This faint yet pervasive radiation, a relic of the early universe, was uncovered by American radio engineers Arno Penzias and Robert Wilson, who were then working at Bell Telephone Laboratories. Their groundbreaking discovery was not the result of a targeted search for cosmological evidence, but rather a serendipitous outcome of their work on telecommunications research. At the time, Penzias and Wilson were engaged in tuning a large radio antenna, famously known as the Horn antenna, for use in satellite communications. During their experiments, they encountered an unexpected and persistent problem, a faint but constant noise that appeared in their measurements. This noise, a low-level hiss of radiation, was omnipresent, refusing to disappear regardless of where they pointed the antenna. Initially, they suspected that the source of the interference might be related to terrestrial factors, such as faulty radio equipment or even mundane causes like birds nesting in the antenna structure. Despite their meticulous efforts to eliminate every possible source of the noise, including clearing out the nests and ensuring the equipment was in perfect condition, the mysterious radiation persisted, baffling the engineers. Realizing that the noise was not of terrestrial origin, Penzias and Wilson considered the possibility that it might be coming from the sky itself. Although they lacked the theoretical background to immediately interpret the nature of this radiation, they were astute enough to recognize its significance. Their discovery, they soon realized, was something extraordinary, an anomaly that defied conventional explanation and pointed to a far more profound cosmic origin. At the same time, a team of scientists at Princeton University, including Jim Peebles and Robert Dicke, were conducting research that directly related to the predictions of the Big Bang theory. These researchers were specifically looking for the remnant radiation from the Big Bang, theorizing that it would have cooled over billions of years to manifest as faint microwave radiation detectable across the sky. When Penzias and Wilson reached out to the Princeton team, it became evident that the mysterious noise they had detected was indeed the long-sought cosmic microwave background radiation, the afterglow of the Big Bang, as predicted by cosmological models. The realization that this faint radiation was the CMBR represented a monumental confirmation of the Big Bang theory. It provided direct evidence that the universe had indeed expanded from a state of extremely high density and temperature. The detection of the CMBR validated the theoretical predictions that the early universe, filled with hot plasma, would have emitted radiation that, as the universe expanded and cooled, would remain as a faint microwave signal observable today. The significance of this discovery cannot be overstated. Penzias and Wilson's work earned them the Nobel Prize in Physics in 1978, a recognition of their crucial contribution to our understanding of the universe. Their discovery not only bolstered the Big Bang theory as the leading explanation for the origin of the universe, but also laid the groundwork for a new era of cosmological research. The CMBR became a cosmic Rosetta Stone, providing scientists with a tool to unlock the secrets of the universe's earliest moments. Following this landmark discovery, the study of the CMBR advanced rapidly. Subsequent research, particularly through satellite missions such as COBE Cosmic Background Explorer, WMAP Wilkinson Microwave Anisotropy Probe, and Planck, utilized increasingly sophisticated instruments to map the minute temperature fluctuations in the CMBR with unprecedented precision. These detailed maps not only confirmed the overall framework of the Big Bang theory, but also provided crucial data to refine our understanding of the universe's key characteristics. The temperature anomalies in the CMBR, for instance, offered insights into the primordial density fluctuations that eventually led to the formation of galaxies and other large-scale structures in the cosmos. The discovery of the CMBR thus marked a pivotal moment in the history of cosmology, fundamentally altering our understanding of the universe's origin and evolution. It opened a new window into the early universe, allowing scientists to peer back in time to the first moments after the Big Bang. This discovery also spurred the development of new theoretical models and hypotheses, as well as the refinement of existing ones, expanding our comprehension of the universe's intricate and complex nature. Today, the CMBR remains a central focus of cosmological research. As we continue to develop more advanced observational technologies and instruments, our ability to study this radiation in even greater detail promises to yield further insights into the fundamental processes that shaped the universe. Each new discovery builds on the legacy of Penzias and Wilson's serendipitous encounter with the faint hum of the early universe, bringing us closer to unraveling the deepest mysteries of our cosmic origins and the ultimate fate of the universe itself. Characteristics of cosmic microwave background radiation. Unveiling the early universe. The cosmic microwave background radiation, CMBR, is a remarkable and invaluable remnant from the early universe, characterized by its remarkably uniform temperature of approximately 7 Kelvin, which is equivalent to 245 degrees Celsius. This makes it one of the coldest known phenomena in the cosmos, a faint whisper of the universe's infancy. Despite this apparent uniformity, meticulous studies have revealed tiny temperature variations within the CMBR, known as anisotropies. These anisotropies, representing differences in temperature of just fractions of a thousandth of a degree, provide a crucial window into the conditions of the early universe, offering insights into the subtle fluctuations in matter density that occurred shortly after the Big Bang. The study of these minute anisotropies has been pivotal in advancing our understanding of the processes that shaped the universe during its formative moments. The slight variations in matter density indicated by these temperature differences were the seeds from which galaxies, star clusters, and other large-scale cosmic structures eventually formed. In essence, the anisotropies captured in the CMBR serve as a map of the early universe, illustrating how matter was distributed across the cosmos at a time when the universe was still relatively homogeneous and in its infancy. These temperature variations in the CMBR are not merely random fluctuations. They are rich with information about the fundamental forces and phenomena that govern the early universe. One such phenomenon is the influence of gravitational waves, which were predicted by Einstein's general theory of relativity. Gravitational waves, which are ripples in the fabric of space-time, can leave subtle imprints on the CMBR, causing additional oscillations in the temperature distribution. By studying these imprints, scientists can gain valuable insights into the role that gravitational waves played in shaping the early universe, as well as how they influenced the evolution of space-time itself during those critical first moments after the Big Bang. Furthermore, the anisotropies in the CMBR provide a wealth of information about the distribution of dark matter, a mysterious and elusive substance that does not interact with light and remains invisible to direct observation. Despite its invisibility, dark matter exerts a significant gravitational influence on visible matter and plays a crucial role in the formation and stabilization of galaxies. The presence of dark matter can be indirectly inferred through its gravitational effects on the distribution of matter, effects that manifest in the anisotropies of the CMBR. By analyzing these variations, scientists can better understand the role of dark matter in the early universe and its contribution to the formation of cosmic structures. These small variations in temperature and density within the CMBR also provide critical insights into the state and evolution of the early universe, including how its density and temperature changed over time. For example, data from the CMBR has confirmed that the early universe was extremely homogeneous on large scales, with only minor deviations in density that later served as the foundation for the large-scale structure of the cosmos. This homogeneity, coupled with the small anisotropies, offers clues about the underlying physical processes that govern the universe's expansion and the eventual formation of galaxies and clusters. The study of CMBR anisotropies has been significantly advanced by satellite missions such as WMAP Wilkinson, Microwave Anisotropy Probe, and Planck. These missions have provided high-precision measurements of the anisotropies, allowing scientists to refine our understanding of the universe's age, composition, and geometry with unprecedented accuracy. The data gathered from these missions has not only confirmed the presence of anisotropies, but has also enabled precise measurements of their parameters, leading to significant refinements in the models and theories that describe the evolution of the universe. The importance of studying CMBR anisotropies extends beyond merely understanding the universe's past. They offer a unique opportunity to explore the early stages of cosmic formation and to comprehend how tiny differences in matter density ultimately gave rise to the vast and intricate structures we observe today. These studies help us refine our picture of the universe, providing crucial information about its age, composition, shape, and expansion history. The ongoing exploration of the CMBR and its anisotropies remains one of the most fruitful areas of research in cosmology, continually yielding new data that test and expand our theories and hypotheses about the universe's origins and evolution. Each new discovery in this field brings us closer to answering the most fundamental questions about the nature of our cosmic home, deepening our understanding of how the universe came to be and what its future might hold. Through this exploration, we are not only uncovering the secrets of the early universe, but also piecing together the broader narrative of the cosmos, a story that spans billions of years and encompasses everything we know about reality. Missions to study the CMBR, pioneering the exploration of the early universe. The exploration of the cosmic microwave background radiation. CMBR has been one of the most crucial undertakings in modern cosmology, made possible by a series of groundbreaking space missions. Each of these missions has contributed significantly to our understanding of the universe's origins, structure, and evolution. The journey began with the launch of the COBE Cosmic Background Explorer satellite by NASA in 1989, a mission that marked the dawn of precision cosmology. COBE was the first satellite dedicated to measuring the CMBR with high accuracy, providing the initial evidence of its uniformity and revealing subtle anisotropies, tiny temperature fluctuations that indicated the presence of early density variations in the universe. These findings were pivotal, as they confirmed the core predictions of the Big Bang Theory and offered a new framework for studying the universe's evolution. While COBE's contributions were monumental, its resolution was limited, leaving much room for improvement. Recognizing this, scientists developed and launched the WMAP Wilkinson Microwave Anisotropy Probe mission in 2001, also under NASA's auspices. WMAP significantly enhanced the resolution of CMBR observations, achieving microkelvin precision in temperature measurements. The detailed maps produced by WMAP offered an unprecedented view of the anisotropies in the CMBR, allowing scientists to refine key cosmological parameters such as the universe's age, composition, and rate of expansion. One of WMAP's most significant achievements was the precise determination of the Hubble parameter, which describes the rate at which the universe is expanding. This mission also provided strong evidence for the existence and relative proportions of dark matter and dark energy, mysterious components that dominate the universe's mass-energy content. According to WMAP's data, the universe consists of approximately 5 ordinary matter, 27 dark matter, and 68 dark energy, with an estimated age of about 8 billion years. These findings had a profound impact on our understanding of the universe, shaping the direction of subsequent research and laying the groundwork for future explorations. The next major advance in the study of the CMBR came with the launch of the Planck satellite by the European Space Agency ESA in 2009. Planck represented a significant leap forward in observational cosmology, equipped with instruments even more sensitive than those on WMAP. The mission provided the highest resolution maps of the CMBR to date, offering an incredibly detailed view of the early universe. Planck's data allowed scientists to refine models of the universe's infancy, providing more accurate values for key cosmological parameters, such as the curvature of the universe and the densities of its various components. Planck's findings confirmed and expanded upon the results obtained by WMAP, offering new insights into the inflationary hypothesis, a theory that suggests the universe underwent a rapid expansion in its earliest moments. The high-precision maps created by Planck revealed the intricate details of CMBR anisotropies, offering a unique glimpse into the primordial quantum fluctuations that later gave rise to the large-scale structures of the cosmos, such as galaxies and clusters of galaxies. These discoveries further solidified the Big Bang theory and provided additional support for the concept of cosmic inflation. The contributions of the COBE, WMAP, and Planck missions extend far beyond confirming the existence and characteristics of the CMBR. They have fundamentally transformed cosmology. These missions have opened new avenues for understanding the universe, offering insights that were previously unimaginable. The data collected by these satellites have become the cornerstone of modern cosmological models, guiding research into the universe's earliest moments and its subsequent evolution. As scientists continue to analyze the vast troves of data from these missions, they are also developing new methods and technologies to push the boundaries of our knowledge even further. Future missions, potentially equipped with even more sensitive instruments, may be capable of addressing the remaining mysteries surrounding dark matter, dark energy, and the universe's first moments. Such advancements could bring us closer to answering fundamental questions about the nature of our cosmic origins and the ultimate fate of the universe. The study of the CMBR remains one of the most dynamic and promising fields in cosmology. Each new discovery in this area not only enriches our understanding of the universe, but also brings us closer to a more complete and unified picture of its origins and evolution. As we continue to explore the faint echoes of the Big Bang, we are unraveling the deepest secrets of the cosmos, piecing together the story of the universe from its inception to its current state, and perhaps even glimpsing what lies ahead in its future. To the structure of the universe, unveiling the cosmic web. When we gaze at the night sky, the stars may appear to be scattered randomly, but in reality, they adhere to complex cosmic laws that organize matter across all levels, from the smallest atoms to the largest galaxies. The universe is composed of billions of galaxies, each containing billions of stars, yet these galaxies do not exist in isolation. Instead, they are part of a grander, interconnected framework known as the cosmic web, a vast network of galaxy clusters, superclusters, and filaments held together by the invisible threads of dark matter and the binding force of gravity. This intricate structure did not arise by chance, but is the result of the gravitational interactions of matter since its emergence after the Big Bang. The initial density fluctuations in matter, captured in the cosmic microwave background radiation, served as the seeds from which the first galaxies formed. Over time, under the influence of gravity, these denser regions attracted more matter, leading to the creation of stars and galaxies. These galaxies, in turn, merged into clusters and superclusters, forming the large-scale structures that dominate the universe today. On the largest scales, the universe resembles a cellular structure, where galaxies and their clusters are connected by filaments of matter that intersect at nodes, known as superclusters. These superclusters are the largest gravitationally bound systems in the universe, containing thousands of galaxies spread over vast regions of space. Between these filaments lie immense voids, regions where the density of matter is extraordinarily low. This cosmic web was discovered through extensive mapping of galaxy distributions, made possible by advances in powerful telescopes and sophisticated data analysis techniques. One of the most awe-inspiring structures uncovered through these studies is the Hercules Corona Borealis Great Wall, a colossal supercluster that spans about 10 billion light-years. This supercluster is one of the largest known structures in the universe, illustrating the sheer scale and complexity of the cosmos. It is within such vast regions of space that galaxies cluster together, with immense voids stretching between them, creating a landscape of cosmic grandeur. At the center of most galaxies, including our Milky Way, reside massive black holes that play a crucial role in the dynamics and evolution of these galaxies. These black holes influence star formation by regulating the amount of gas available for new stars to form. The gravitational interactions between galaxies within clusters often lead to collisions and mergers, which are significant events in the evolutionary history of galaxies and the universe as a whole. Dark matter, which constitutes a substantial portion of the universe's total mass, remains one of the greatest mysteries in modern cosmology. Although it does not interact with ordinary matter through electromagnetic forces and is therefore invisible, Its gravitational influence is unmistakable in the formation of large-scale structures. Without dark matter, the gravitational pull of ordinary matter would be insufficient to form galaxies and keep them intact. The distribution of dark matter forms the scaffolding upon which all visible cosmic structures are built, shaping the universe at every level. Superclusters, the nodes of this cosmic web, are often gravitationally bound to one another, creating a vast network of filaments and intersections that permeate the entire cosmos. Within this web, visible matter accumulates in regions where the gravitational pull of dark matter is strongest, leading to the formation of galaxies, star clusters, and planetary systems. These regions of concentrated matter are the birthplaces of stars and planets, the building blocks of cosmic evolution. On smaller scales, stars themselves are organized into galaxies, which exhibit a wide variety of shapes and sizes. Spiral galaxies, like our Milky Way, are characterized by their rotating disk structure, with arms winding out from a central bulge. Elliptical galaxies, on the other hand, have a more spherical or oval shape and are often composed of older stars. Irregular galaxies lack a distinct structure, often resulting from gravitational interactions or collisions with other galaxies. The diversity in galaxy shapes and sizes is a testament to the complex histories and environmental interactions that have shaped them over billions of years. The study of the universe's structure is a central focus of modern astronomy and cosmology. Advances in technology, including the development of large optical and infrared telescopes, as well as radio telescopes, have enabled astronomers to uncover increasingly detailed aspects of this cosmic structure. These tools have allowed scientists to map the distribution of galaxies across vast distances and to understand the processes that have shaped the universe's evolution. Future missions, such as the James Webb Space Telescope JWST and a host of ground-based observatories, promise to deepen our understanding of the universe's structure and history. The JWST, with its advanced capabilities, will be able to peer further back in time than ever before, offering new insights into the formation of the first galaxies and the role of dark matter in shaping the cosmic web. These observations will reveal new facets of the cosmic order, enhancing our understanding of the forces that govern matter at all levels and providing answers to some of the most fundamental questions about the universe's origin and evolution. As we continue to explore the structure of the universe, we're not only mapping the distribution of matter on the grandest scales, but also uncovering the intricate processes that have shaped the cosmos from its earliest moments to its present state. This research is a journey toward understanding the universe as a whole, revealing the complex interplay of forces that have given rise to the cosmic web, the galaxies within it, and ultimately, the stars and planets that make up our cosmic home. Galaxies and their types. The building blocks of the universe. Galaxies are the fundamental building blocks of the universe, playing a crucial role in its structure, evolution, and the formation of stars and planetary systems. These colossal systems contain billions of stars, vast clouds of gas and dust, and a significant amount of dark matter that influences their dynamics and overall evolution. Galaxies do not exist in isolation. They interact with one another, forming larger structures such as clusters and superclusters, and these interactions can dramatically influence the formation of stars and planetary systems within them. Depending on their shape and structure, galaxies are categorized into several main types: spiral, elliptical, lenticular, and irregular. Spiral galaxies. Spiral galaxies are among the most common and well-studied types of galaxies. They are easily recognized by their distinct structure, a central nucleus surrounded by a flat disk from which spiral arms extend. These spiral arms are regions of intense star formation, filled with young, hot stars that glow with a bluish hue, as well as clouds of gas and dust. The Milky Way, our home galaxy, and the Andromeda Galaxy are classic examples of spiral galaxies. Spiral galaxies are further classified into subtypes based on the characteristics of their central nucleus and the configuration of their spiral arms. For instance, some spiral galaxies have a prominently defined central bulge, while others have a more diffuse core. Additionally, a subset of spiral galaxies features a bar-like structure that extends across the nucleus, with spiral arms emanating from the ends of the bar. These are known as barred spiral galaxies. The structure and dynamics of spiral galaxies make them rich sites of ongoing star formation, contributing to the dynamic nature of the universe. Elliptical galaxies. Elliptical galaxies, in contrast to their spiral counterparts, have a smooth, spherical or ellipsoidal shape and lack the distinct features such as spiral arms or disks. They are highly symmetrical and consist mainly of older, evolved stars. The processes of star formation in elliptical galaxies are nearly non-existent, largely because they contain very little gas and dust. The absence of these materials, which are the raw ingredients for star formation, explains the prevalence of older stars and the subdued activity in these galaxies. Elliptical galaxies can vary significantly in size, ranging from dwarf elliptical galaxies, which contain just a few million stars, to giant elliptical galaxies, which can house trillions of stars. These galaxies are often found at the centers of galaxy clusters, and many are believed to have formed from the merger of smaller galaxies. The lack of new star formation and the dominance of older stars give elliptical galaxies a reddish appearance, in contrast to the bluish glow of star-forming spiral galaxies. Lenticular galaxies. Lenticular galaxies represent an intermediate type between spiral and elliptical galaxies. They have a flat disk structure similar to that of spiral galaxies, but lack the well-defined spiral arms. Lenticular galaxies, also known as S0-type galaxies, contain little gas and dust, and as a result, star formation processes are minimal or entirely absent. This makes lenticular galaxies resemble elliptical galaxies in many respects, particularly in their star composition and the cessation of star formation. Lenticular galaxies are thought to have evolved from spiral galaxies that have lost most of their interstellar gas, which is necessary for forming new stars. Over time, the depletion of this gas leads to a halt in star formation, leaving behind a disk of older stars and little ongoing activity. The transformation from a spiral to a lenticular galaxy is often driven by interactions with other galaxies or environmental effects within galaxy clusters. Irregular galaxies. Irregular galaxies, as their name suggests, do not have a defined shape or structure. These galaxies can contain a mix of young and old stars, along with significant amounts of gas and dust, making them active regions of star formation. The chaotic structure of irregular galaxies is often the result of gravitational interactions with other galaxies, which can disrupt their form and lead to the absence of any clear shape. One of the most well-known examples of an irregular galaxy is the Large Magellanic Cloud, a satellite galaxy of the Milky Way. Irregular galaxies may be remnants of larger galaxies that have been torn apart by gravitational forces, or they may result from the merging and interaction of galaxies, leading to their disordered appearance. Despite their chaotic structure, irregular galaxies are key sites of star formation, contributing to the ongoing evolution of the universe. The role of galaxies in the universe. Each type of galaxy plays a vital role in the grand tapestry of the universe, contributing to our understanding of cosmic processes that have unfolded over billions of years. The study of galaxies, whether spiral, elliptical, lenticular, or irregular, provides critical insights into how galaxies form, evolve, and interact with one another. These interactions are not only crucial for the galaxies themselves, but also for the formation of stars, planetary systems, and potentially life. Research into galaxies is ongoing, with new discoveries continually refining our understanding of these cosmic structures. The evolution of galaxies, the role of dark matter in shaping them, and their eventual fate are all subjects of intense study. Future missions and advanced observational technologies promise to reveal even more about the nature of galaxies, offering clues about the future of our own galaxy, the Milky Way, and its place in the vast, interconnected universe. As we continue to explore these immense structures, we gain a deeper appreciation of the complexity and beauty of the cosmos, and we move closer to answering some of the most profound questions about the origins and destiny of the universe itself. Galaxies, in all their varied forms, are the engines of cosmic evolution, and understanding them is key to understanding the universe as a whole. Superclusters and the cosmic web. The grand architecture of the universe galaxies are not isolated entities. They congregate into clusters and superclusters, forming intricate hierarchical structures that are crucial for comprehending the macroscopic organization of the universe. Galaxy clusters are assemblies of galaxies ranging from a few dozen to thousands, all bound together by the force of gravity. These clusters contain vast amounts of matter, both visible and invisible, and the gravitational interactions within them dictate the dynamics and evolution of the galaxies they encompass. Superclusters are even grander structures that aggregate numerous galaxy clusters and groups, creating colossal cosmic formations. These superclusters are among the largest known structures in the universe, spanning hundreds of millions of light-years. One of the most renowned superclusters is Laniakea, which encompasses our local group of galaxies, including the Milky Way. Laniakea unifies many galaxy clusters, which are not just gravitationally bound, but also dynamically linked, forming a coherent cosmic entity that influences the large-scale behavior of the universe. However, these superclusters do not exist in isolation. They are interconnected in a vast and intricate network known as the cosmic web. This cosmic web is a colossal lattice of filaments composed of galaxies and dark matter stretching across billions of light-years. These filaments create a framework on which galaxies and their clusters are suspended, linking together at nodes where superclusters reside. Between these filaments lie vast expanses known as voids, regions where the density of matter, including galaxies, is exceedingly low. Voids constitute a significant portion of the universe's volume, emphasizing the contrast between the densely populated filaments and the almost empty spaces in between. The cosmic web is more than just a poetic metaphor. It is a tangible and observable representation of how matter is distributed throughout the universe. It illustrates the role of gravity and dark matter in shaping the universe's large-scale structure. The gravitational pull within the cosmic web's filaments is a critical factor in the formation of galaxies and their clusters. Dark matter, although invisible and undetectable by direct observation, exerts a profound influence on visible matter by creating gravitational fields that govern the motion and evolution of galaxies within the web. The study of the cosmic web is also pivotal for understanding dark matter. The distribution of galaxies and clusters within the web's filaments provides clues about the underlying distribution of dark matter, which acts as the glue that holds these vast structures together. By observing how dark matter's gravitational influence affects visible matter, scientists can refine their models of dark matter's behavior and better understand its role in the formation and evolution of the universe. Modern astronomical research, including large-scale galaxy surveys and observations of the cosmic microwave background radiation, continues to enhance our understanding of the cosmic web. These studies are complemented by advanced computer simulations that model the evolution of the cosmic web based on observational data. These simulations allow scientists to explore the processes that lead to the formation of filaments and nodes, and to investigate how the structure of the cosmic web changes over time. The cosmic web remains one of the most captivating and enigmatic topics in modern cosmology. Its study opens new avenues for exploring the fundamental laws of nature that govern the distribution of matter across the universe. As research progresses, astronomers and physicists are inspired to pursue new discoveries that may unravel some of the deepest mysteries of the cosmos and its evolution. These ongoing studies not only enhance our understanding of the universe's structure, but also provide insights into the forces that have shaped it since the dawn of time. The cosmic web is a testament to the complexity and beauty of the universe, a grand tapestry woven by the interplay of gravity, dark matter, and the fundamental forces that govern the cosmos. As we continue to map and study this vast structure, we gain a deeper appreciation for the intricate processes that have created the universe as we know it today, and a glimpse into the forces that will continue to shape its future. The local group and the Milky Way. Our cosmic neighborhood. The Milky Way galaxy, our cosmic home, is not an isolated island in the vastness of space, but part of a larger structure known as the Local Group. This small cluster of galaxies is a close-knit community of about 54 galaxies, all gravitationally bound to one another. Among its most prominent members are the Milky Way, the Andromeda Galaxy M31, and the Triangulum Galaxy M33, along with a host of smaller, less massive galaxies such as the Large and Small Magellanic Clouds. These galaxies, varying in type from spirals to ellipticals and irregulars, each contribute to the dynamic interplay that governs the Local Group S evolution. The Milky Way and Andromeda are the two giants of the Local Group, each with a massive halo of stars, gas, and dark matter that influences their smaller companions. The Andromeda Galaxy, the largest in the group, is on a slow but inevitable collision course with the Milky Way. This cosmic encounter, predicted to occur in about 4-5 billion years, will reshape both galaxies, merging them into a new, larger galaxy, sometimes referred to as Milkomeda or Milkdromeda. This future collision is a reminder of the dynamic and ever-changing nature of the universe, where even seemingly stable structures like galaxies are subject to constant evolution and transformation. The Local Group S smaller galaxies, such as the Magellanic Clouds, are important for understanding the Milky Way S past and future. These dwarf galaxies are currently interacting with the Milky Way, with gravitational forces pulling them closer, causing streams of stars and gas to stretch between them and our galaxy. These interactions may eventually lead to the Magellanic Clouds being absorbed by the Milky Way, contributing to its mass and star formation activity. While the Local Group is relatively small compared to other galactic clusters, it is part of a much larger cosmic structure known as the Virgo supercluster, also referred to as the Laniakea supercluster. This immense supercluster is a vast collection of thousands of galaxies, all bound together by gravity, forming part of the intricate cosmic web that permeates the universe. The Local Group occupies a tiny corner of this vast supercluster, with its galaxies moving within the larger gravitational field of Laniakea, influenced by the mass distribution of the entire supercluster. The Virgo supercluster, including the Local Group, is not static but part of the cosmic web, a network of filaments and nodes where galaxies and galaxy clusters are concentrated. Within this web, the Local Group S galaxies are not only moving but also interacting with their environment, influenced by the gravitational forces of neighboring galaxies and clusters. These interactions shape the future trajectories and eventual fates of the galaxies within the Local Group. The Local Group S location within the Virgo supercluster places it in a region where cosmic flows guide the movement of galaxies toward larger concentrations of matter, such as the Great Attractor, a gravitational anomaly in intergalactic space that draws galaxies toward it, including those within the Local Group. This cosmic dance within the supercluster reflects the larger scale movements of galaxies and clusters, illustrating how local dynamics are influenced by the broader cosmic environment. The study of the Local Group, and particularly the Milky Way S place within it, provides valuable insights into the processes that govern galaxy formation, evolution, and interaction. By examining the Local Group S structure and dynamics, astronomers can better understand the history of our galaxy and predict its future. This includes not only the eventual merger with Andromeda, but also the ongoing interactions with smaller galaxies and the influence of the larger supercluster environment. As our observational capabilities improve with advancements in telescopes and space missions, our understanding of the Local Group and its role within the cosmic web will continue to deepen. These studies will shed light on the fundamental processes that shape galaxies and their interactions, offering a clearer picture of the forces that have molded the universe into its present form and will continue to influence its evolution for billions of years to come. In this context, the Local Group is more than just a collection of galaxies. It is a dynamic, evolving system that provides a microcosm of the larger universe. Understanding its complexities helps us comprehend the broader processes at work across the cosmos, from the formation of stars and planets to the eventual fate of entire galaxies. As we look out into the universe, the local group serves as our immediate cosmic neighborhood, offering a glimpse into the intricate and interconnected nature of the universe. The Milky Way, our galactic home. The Milky Way is a barred spiral galaxy that serves as the cosmic home of our solar system. With a diameter of about 100,000 light-years, the Milky Way is a vast and intricate structure containing between 100 and 400 billion stars, although the exact number remains a topic of ongoing research. The galaxy's central region, known as its nucleus, is densely populated with stars and other celestial objects, and at its very heart lies a supermassive black hole named Sagittarius A. This black hole, with a mass roughly equivalent to 4 million solar masses, exerts a powerful gravitational influence on the surrounding stars and gas, anchoring the galaxy's core and playing a crucial role in its dynamics. The Milky Way is characterized by its classic spiral structure, featuring a central bar from which its spiral arms extend. These arms are not just beautiful swirling structures, but are active regions where stars are born. The main spiral arms of the Milky Way, namely the Perseus arm, the Sagittarius arm, and the Cygnus arm, are rich in stars, gas, and dust. Within these arms, giant molecular clouds serve as stellar nurseries where young, hot stars are formed, illuminating the arms with their brilliant blue light. These regions of active star formation contribute to the ongoing evolution of the galaxy, replenishing its stellar population and shaping its future. Surrounding the visible disk of the Milky Way is a spherical halo composed of older stars, globular clusters, and a substantial amount of dark matter. This dark matter, which does not emit or interact with electromagnetic radiation in a way that makes it directly observable, is inferred from its gravitational effects. It is believed to account for a significant portion of the Milky Way's total mass, providing the necessary gravitational force to hold the galaxy together and maintain its structure. The halo's dark matter is a critical component in understanding the galaxy's overall dynamics, influencing the rotation curves of stars and the stability of the galactic disk. The solar system is situated within one of the Milky Way's spiral arms, specifically in the Orion arm, sometimes referred to as the Orion Spur. This arm is located about 27,000 light-years from the galactic center, placing our solar neighborhood relatively close to the galactic plane. The Sun, along with other stars in the Orion arm, orbits the center of the Milky Way at an impressive speed of approximately 220 kilometers per second. This journey around the galactic center, known as the galactic year or cosmic year, takes about 230 million years to complete. During this time, the solar system experiences the gradual but profound changes in the galaxy's structure and environment. The Milky Way is not a solitary entity. It constantly interacts with other galaxies within the local group. One of the most significant of these interactions is its impending collision with the Andromeda Galaxy. Andromeda, the Milky Way's nearest large neighbor, is on a collision course with our galaxy, moving toward it at a speed of about 110 kilometers per second. In approximately 5 billion years, these two spiral giants are expected to merge into a single, much larger galaxy, likely forming a giant elliptical galaxy. This cosmic event will be accompanied by dramatic changes in the structure of both galaxies, with their spiral arms becoming distorted and eventually merging into a more homogeneous elliptical shape. Despite the scale and violence of this collision, the vast distances between individual stars mean that the likelihood of direct stellar collisions is extremely low. For stars like the Sun, the merger will pass relatively peacefully, although the gravitational interactions between the two galaxies will dramatically alter the orbits of many stars, potentially flinging them into new trajectories or even ejecting them from the newly formed galaxy altogether. The eventual merger of the Milky Way and Andromeda will be a defining moment in the evolution of the local group, marking the transition of two vibrant spiral galaxies into a single, massive elliptical galaxy that will dominate the local universe. As we look toward the future of the Milky Way, we also gain insights into the galaxy's past and present. The study of its structure, star formation processes, and interactions with other galaxies helps us understand not only the history of our cosmic home, but also the broader processes that govern the evolution of galaxies throughout the universe. With each new discovery, we continue to deepen our knowledge of the Milky Way, revealing the intricate and dynamic nature of the galaxy we call home. Humanity and the Universe. A journey of discovery and reflection. Throughout its history, humanity has been driven by an insatiable curiosity to understand its place within the vast and seemingly infinite universe. From the earliest days of civilization, people have gazed up at the stars, pondering what lies beyond their immediate surroundings, how the cosmos came into existence, and what role humanity plays in this grand cosmic order. In their attempts to make sense of the incomprehensible, our ancestors crafted myths, religious beliefs, and philosophical systems that sought to explain the mysteries of existence and the laws governing the universe. The mythology of ancient cultures was rich with imagery of celestial gods and cosmic battles, reflecting a deep human desire to find meaning in the phenomena observed in the night sky. These myths served as early attempts to impose order on the chaos of the universe, attributing the movements of the stars, the cycles of the moon, and the changing seasons to the actions of divine beings. In many cultures, the heavens were seen as the realm of the gods, and the stars were often thought to be the spirits of the ancestors, or the physical manifestations of deities watching over the world. As societies evolved, religions emerged that offered more structured and holistic worldviews, connecting the earthly with the heavenly, and providing explanations for the origin and destiny of humanity within the context of divine plans. For example, in many religious traditions, the creation of the universe was seen as the work of a supreme being or beings, and the heavens were regarded as a reflection of the divine order. These religious beliefs provided a framework for understanding the cosmos and humanity's place within it, offering solace and meaning in the face of the vast and often overwhelming mysteries of existence. At the same time, philosophers began to seek rational explanations for the nature of the universe, using logic, observation, and reasoning to construct the first scientific models of the world. The ancient Greek thinkers, such as Pythagoras, Plato, and Aristotle, laid the foundations for the scientific method, proposing theories about the structure of the cosmos that would influence thought for centuries. Their ideas, though often speculative and limited by the knowledge of their time, represented a significant shift toward a more systematic and empirical approach to understanding the universe. With the advent of modern science and technology, humanity's relationship with the cosmos underwent a profound transformation. The invention of the telescope by Galileo Galilei in the early 17th century marked the beginning of a new era of exploration, allowing us to see farther into space than ever before and challenging long-held beliefs about the nature of the universe. The realization that Earth was not the center of the universe, but rather one planet orbiting an average star in a vast galaxy, was a humbling and revolutionary shift in perspective. As technology advanced, so too and deepened our understanding of the solar system. Powerful telescopes, such as the Hubble Space Telescope, have allowed us to peer into the depths of the universe, observing distant galaxies, nebulae, and other celestial phenomena that were previously beyond our reach. These tools have enabled us to explore the origins of the universe, the formation of stars and galaxies, and the fundamental forces that govern the cosmos. In the modern era, space science has not only enhanced our knowledge of the universe, but has also raised profound questions about the nature of existence itself. We now contemplate the origins of the universe, its ultimate fate, and the possibility of other forms of life beyond Earth. The discovery of exoplanets in distant star systems has opened up new possibilities for understanding the potential for life elsewhere in the universe, challenging our assumptions about our uniqueness and our place in the cosmos. Despite these advances, the universe remains full of mysteries. The more we learn, the more questions arise, each discovery opening new horizons for exploration. Concepts such as dark matter and dark energy, which make up the majority of the universe's mass and energy but remain poorly understood, remind us of how much we have yet to uncover. The pursuit of knowledge about the universe is not only a scientific endeavor, but also a reflection of humanity's deep-seated need to understand the nature of reality and our place within it. In this context, humanity's quest to comprehend its place in the universe is an ongoing journey, one that transcends mere scientific inquiry and taps into the very essence of what it means to be human. This quest has driven us to look beyond our world, to search for answers in the stars, and to dream of one day unraveling the mysteries of the cosmos. As we continue to explore, we carry with us the hope that future generations will build upon our discoveries, opening new dimensions of understanding and revealing the infinite possibilities that the universe holds. Our exploration of the cosmos is not just about discovering distant galaxies or understanding the fundamental forces of nature, it is also about discovering ourselves. In the process of probing the universe, we gain new insights into the nature of life, consciousness, and our connection to the greater whole. As we look to the stars, we are reminded of the vastness of the universe and the smallness of our place within it. Yet we are also reminded of our capacity for wonder, curiosity, and the relentless pursuit of knowledge. The universe, in all its vastness and complexity, remains the ultimate frontier for humanity. Our journey through the cosmos is a testament to our enduring spirit of exploration, a journey that continues to inspire, challenge, and transform us. As we move forward, we will continue to seek answers to the deepest questions about the universe, our place within it, and the future of our cosmic journey. Space exploration. Humanity's journey beyond Earth. Space exploration has emerged as one of humanity's most ambitious and defining pursuits in the 20th and 21st centuries. The history of space exploration began with the groundbreaking achievement of overcoming Earth's gravitational pull, a feat that symbolized the dawn of a new era in science and technology. The launch of the first artificial satellite, Sputnik 1, by the Soviet Union in 1957 marked the beginning of humanity's journey into space. This historic event not only demonstrated that it was possible to venture beyond our home planet, but also ignited a fervor for discovery that has driven technological and scientific advancements ever since. It served as a catalyst for rapid change, inspiring generations of scientists, engineers, and dreamers who believed in the potential to conquer space and unravel its mysteries. The flight of Yuri Gagarin in 1961, the first human to journey into space, was a monumental milestone in human space exploration. Gagarin's orbit around Earth was more than just a technical achievement. It was a symbol of human courage, ingenuity, and the relentless pursuit of knowledge. This historic event paved the way for future manned missions and demonstrated that humans could survive and operate in the harsh environment of space. Gagarin's achievement was followed by other significant milestones, culminating in one of the most remarkable moments in human history, the Apollo 11 mission's successful landing on the Moon in 1969. When Neil Armstrong and Buzz Aldrin set foot on the lunar surface, they not only fulfilled a long-held dream of exploring the Moon, but also proved that with determination, even the most ambitious goals could be realized through collective effort and technological innovation. Decades after these initial triumphs, humanity's exploration of space continues to evolve and expand. Space agencies such as NASA National Aeronautics and Space Administration, ESA European Space Agency, Roscosmos Russian Space Agency, and CNSA China National Space Administration, along with private companies like SpaceX, Blue Origin, and others, are at the forefront of pioneering new missions that push the boundaries of what was once thought impossible. These organizations are developing and launching missions aimed at exploring the farthest reaches of the solar system and beyond, sending robotic probes and spacecraft to planets like Mars, Jupiter, Saturn, and even venturing beyond the heliosphere, the outermost boundary of our solar system. Mars exploration has become a focal point of contemporary space science. The red planet, with its intriguing potential for past or present life, has captivated the imagination of scientists and the public alike. Robotic explorers like NASA's Curiosity and Perseverance rovers have been tirelessly traversing the Martian surface, conducting experiments and collecting data that could unlock the secrets of Mars history. These missions are not only searching for signs of ancient life, but also assessing the planet's suitability for future human colonization. The findings from these rovers are expanding our understanding of planetary processes and the conditions that may exist on other worlds, bringing us closer to the dream of establishing a human presence on Mars. In addition to planetary exploration, space telescopes like the Hubble Space Telescope and the recently launched James Webb Space Telescope, JWST, have revolutionized our ability to observe the universe. These powerful instruments allow scientists to peer deep into space, capturing images and data from the most distant objects in the cosmos, from newborn stars and galaxies to potentially habitable exoplanets orbiting other stars. These observations are opening new horizons in our understanding of the structure and evolution of the universe, offering glimpses into the earliest epochs of cosmic history and providing critical insights into the forces that shape our cosmic environment. Among the most ambitious endeavors in space exploration are the plans to send humans to Mars and establish permanent colonies there. Projects like NASA's Artemis program, SpaceX's Starship initiative, and other visionary efforts aim to achieve the long-held dream of making humanity a multi-planetary species. These missions represent a new era in space exploration, where humans will not only visit another planet, but live and work on its surface. Establishing a human presence on Mars is seen as a crucial step in ensuring the long-term survival of humanity, offering a potential safeguard against existential threats on Earth and providing a platform for further exploration of the solar system. Looking even further into the future, the exploration of other star systems is becoming increasingly feasible with the development of advanced technologies. Projects like Breakthrough Starshot, an initiative to develop small, light-powered spacecraft capable of reaching nearby star systems such as Alpha Centauri within a human lifetime, represent the next frontier in space exploration. If successful, these missions could mark the beginning of interstellar exploration, opening the door to the discovery of new worlds and the search for extraterrestrial life beyond our solar system. Space exploration remains one of the most thrilling and consequential fields in science and technology, driving humanity forward toward new horizons and groundbreaking discoveries. The opportunities that space exploration presents are boundless, offering the potential to answer some of the most fundamental questions about the universe and our place within it. Every new mission, whether it is a robotic probe sent to a distant planet or a telescope capturing light from the edge of the universe, brings us closer to understanding the vast cosmos we inhabit. As we continue to push the boundaries of what is possible, space exploration stands as a testament to human ingenuity, perseverance, and the innate desire to explore the unknown. It is not just a scientific endeavor, but a deeply human one, rooted in our quest for knowledge, our drive to explore new frontiers, and our enduring hope for a future that reaches beyond the confines of our home planet. As we venture further into space, we carry with us the collective dreams of humanity, poised to discover the infinite possibilities that the universe holds for us and future generations. Impact on society and culture. The cosmic influence space exploration has profoundly influenced the development of science, technology, and culture, serving as a wellspring of inspiration and motivation for humanity over the decades. From the moment humans first comprehended the vastness of the universe, space has symbolized limitless possibilities and the unending quest for knowledge. It has inspired the creation of art, literature, and cinema, giving rise to new genres and styles that reflect our awe and reverence for the mysteries of space. Science fiction has become a cornerstone of global culture, offering imaginative depictions of space travel, alien civilizations, and interstellar conflicts. Novels like Arthur C. Clarke's 2001: A Space Odyssey, films such as George Lucas's Star Wars and Carl Sagan's Contact not only captivate the imagination, but also challenge us to consider the possibilities and challenges that humanity may face as we venture into the cosmos. These works often explore themes that go beyond science and technology, delving into philosophical questions about the nature of reality, time, space, life, death, and our place in the vast universe. Space has thus become a powerful symbol, not just of scientific progress, but also of our deepest philosophical quests. Music, too, has been deeply influenced by space exploration. Composers and musicians have drawn inspiration from the cosmos, creating works that evoke the wonder and mystery of space. Gustav Holst's Symphonic Suite, The Planets, is a classical example, capturing the character of each planet in our solar system. In contemporary music, songs like David Bowie's Space Oddity reflect humanity as yearning to explore the unknown and push beyond the boundaries of our world. These musical works mirror our collective fascination with space and our desire to reach new horizons, both physically and metaphorically. The philosophical and scientific ideas related to space exploration have significantly altered our perception of reality. The realization that we live on a small, fragile planet, orbiting an average star in a galaxy among billions, forces us to reconsider our place in the cosmos. The Copernican revolution, which revealed that Earth is not the center of the universe, marked the beginning of a profound shift in scientific thought. It was a humbling revelation that humans are not the focal point of creation, but rather part of a vast, complex, and largely unknown system. This understanding has brought about deep changes in our worldview. The recognition that humanity is just a small part of the grand cosmic tapestry has fostered a more global and unifying perspective. It has inspired the concept of planetary consciousness, a recognition of our shared responsibility to protect our planet, the only home we have. Space exploration, particularly the iconic images of Earth captured by astronauts during the Apollo missions, has given us the opportunity to see our planet as a whole, a small, delicate blue orb suspended in the vastness of space. This overview effect has been transformative, encouraging a sense of stewardship and a greater awareness of the interconnectedness of all life on Earth. The practical benefits of space exploration extend far beyond the philosophical. The technologies developed for space missions have led to numerous innovations that have profoundly impacted life on Earth. Satellite communications, GPS, weather forecasting, and Earth observation are just a few examples of space technologies that have become integral to modern life. Advances in materials, science, robotics, and medicine originally developed for space exploration have found widespread applications on Earth, improving the quality of life for millions of people. These achievements demonstrate that space exploration is not just about expanding our knowledge of the universe, it also brings tangible benefits that enhance our everyday lives. Space exploration has also played a crucial role in fostering international cooperation. The complexities and challenges of space missions often require collaboration between scientists, engineers, and governments from multiple countries. The International Space Station ISS is perhaps the most prominent example of such cooperation. As a joint project involving space agencies from the United States, Russia, Europe, Japan, and Canada, the ISS serves as a symbol of what humanity can achieve when nations work together toward common goals. It stands as a testament to the power of collaboration in overcoming global challenges, whether in space exploration or addressing issues here on Earth. In this way, space has a profound and multifaceted impact on our culture, science, technology, and philosophy. It changes how we see the world and our place in it, inspiring new achievements and opening new horizons for knowledge and creativity. The starry sky continues to evoke a sense of wonder and a desire to explore the unknown, driving human progress and expanding our understanding of the universe. As we continue to gaze upward and venture outward, space will remain a source of inspiration, challenging us to dream big, think deeply, and strive for greatness. Through space exploration, humanity not only reaches for the stars, but also gains a deeper appreciation of the preciousness of our planet and the shared journey of all life within the vast cosmos. Conclusion. The study of the universe transcends mere scientific inquiry. It is a profound journey that touches on the most fundamental questions of our existence. Space, with its boundless expanses and countless mysteries, represents the ultimate arena for human imagination and scientific exploration. Every new discovery brings us closer to understanding the nature of the universe, but it also serves as a humbling reminder of the vastness and complexity of the cosmos in which we live. This exploration challenges our beliefs, expands the boundaries of our knowledge, and compels us to view the world with fresh perspectives. As we embark on the search for new worlds, study exoplanets, explore distant galaxies, or attempt to peer into the farthest corners of space, we are not just uncovering the mysteries of the universe, we are opening new horizons for humanity itself. These discoveries fuel our curiosity, inspire further exploration, and drive the creation of new technologies that can propel our society forward. Space exploration forces us to reflect on who we are, what our goals are, and where we are headed as a species. The endeavor of exploring space also serves as a poignant reminder of our vulnerability and responsibility. It leads us to understand that our planet is not just our home, but also a unique and fragile corner of the universe that requires our protection and care. The new perspective on Earth, gained through the lens of space exploration, enhances our appreciation of the significance of our existence and underscores the importance of preserving our planetary home for future generations. Ultimately, our exploration of space is not only an attempt to understand the universe, but also a quest to understand ourselves and our place within this grand cosmic design. We are but a small part of the vast cosmic mosaic, yet it is this very part that gives meaning and context to the entire picture. Understanding this helps us seek answers to the most profound questions we ask as a species. Where did we come from? Where are we going? What is the meaning of our existence? Perhaps one day, through space exploration, we will find the answers to these questions. But even if these answers remain elusive, the pursuit of knowledge, the desire to push beyond the known and explore the unknown, is what defines us as human beings. Space inspires us to dream, to explore, and to achieve greatness. In this relentless quest for understanding, perhaps lies the most important lesson we can learn from our great cosmic journey, that the journey itself, marked by wonder, discovery, and the ceaseless expansion of our horizons, is as significant as any destination we might reach. Somewhere, something incredible is waiting to be known. Carl Sagan. When evening descends on Earth and the sunlight disappears beyond the horizon, stars appear in the sky. These small, twinkling lights are actually giant celestial bodies located at incredible distances from us. The night invites us to peer into the boundless depths of the universe, full of mysteries and wonders. About 8 billion years ago, the Big Bang occurred, marking the beginning of everything that exists, time, space, and matter. In the first fractions of a second after this event, the universe was incredibly hot and dense. Gradually, it began to expand and cool, leading to the formation of the first elementary particles and atoms. Since then, the universe has continued to expand. Billions of galaxies, each containing billions of stars, planets, and other celestial objects, move in a cosmic dance. Our galaxy, the Milky Way, is a vast disk filled with stars, gas, and dust. At the center of the galaxy lies a massive black hole whose gravity holds the galaxy together. When we look at the night sky, our eyes can capture only a small part of what exists in the universe. Some of the stars we see are hundreds or thousands of light years away from us. The light from these stars has traveled through space for an incredibly long time before reaching our eyes. Each star we see represents a unique story, a beacon in the boundless ocean of space. Space, an untapped mystery, harbors answers we have yet to uncover. It stands as the ultimate frontier, not only for exploration, but for our quest to understand, to grasp, and to find our place in the cosmos. As we stand on the edge of the known and gaze into the vast expanses stretching beyond our comprehension, we embark on a journey that is as much about discovering the universe as it is about understanding ourselves. The observable universe, with its billions of galaxies filled with stars and planets, is a testament to the complexity and grandeur of nature. In this documentary, we will explore these cosmic distances not only to map the stars and their mysteries, but to answer profound questions that have intrigued humanity since we first looked up at the night sky. What lies at the edge of our observable universe? Are we alone, or is the universe teeming with life waiting to be discovered? The universe, vast and stretching beyond our imagination, encompasses all space, time, matter, and energy. It is woven from the fabric of galaxies, stars, planets, and the very space-time itself. Scientists estimate its age to be around 8 billion years, using data on the movement of galaxies and the cosmic microwave background, the afterglow of the Big Bang. This monumental event marked the beginning of the universe, which expanded from an infinitely dense point known as a singularity into the cosmos we observe today. One of the universe's most intriguing features is its composition. Only about 5 of it consists of ordinary matter stars, planets, and galaxies visible to us. The rest is dark matter and dark energy, mysterious entities that do not emit light or energy but have significant effects on the structure and expansion of the universe. Dark matter, making up about 27, acts as the cosmic glue holding galaxies together, while dark energy, about 68, accelerates the universe's expansion. The discovery of dark energy, which earned the Nobel Prize in Physics in 2011, revolutionized our understanding of cosmology. Understanding the universe also prompts us to reflect on the fundamental nature of reality and our place within it, intertwining cosmology with philosophy. Philosophers and scientists explore questions about the origin of the universe, its ultimate fate, and the laws governing its behavior. This pursuit of knowledge challenges our perceptions, prompting us to ponder not just the mechanics of celestial bodies, but the very essence of existence. It encourages us to explore concepts like the multiverse theory, which suggests that our universe might be just one of countless others, each with its unique laws and constants. The journey to determine the universe's age is a story intertwined with centuries of astronomical observations and theoretical breakthroughs. This journey began with ancient civilizations when people first gazed at the stars and wondered about their origins. However, scientific inquiry into the universe's age began to take shape in the 20th century, following significant discoveries in physics and astronomy. A pivotal moment was Edwin Hubble's 1929 observation that galaxies are moving away from us, indicating that the universe is expanding. This discovery laid the foundation for the Big Bang theory, the leading explanation for the universe's origin. By measuring the rate at which galaxies recede from us, astronomers determined the universe's expansion rate, known as the Hubble constant. Initial estimates suggested a young universe, but as measurements improved, the age was revised upwards. In the late 20th and early 21st centuries, advancements in technology such as the Hubble Space Telescope and later the Planck satellite refined our understanding of the cosmic microwave background. These observations provided clearer insights into the early moments of the universe and helped narrow down the Hubble constant to a more precise value. Determining the universe's age also depends on understanding the life cycles of stars. By observing the oldest stars in globular clusters, dense groups of stars held together by gravity astronomers can estimate the universe's minimum age. These stars, some of the first formed after the Big Bang, offer a stellar clock by which to gauge cosmic history. The oldest of these stars are nearly as old as the universe itself, about 13 billion years, providing a lower limit on the age of the cosmos. Delving further into the mysteries of the cosmos, the concept of the observable universe emerges as a fascinating topic, deepening our understanding of its vastness and age. The observable universe refers to the part of the entire universe that we can see or detect from Earth, limited by the speed of light and the age of the universe. Because light travels at a finite speed, approximately 299,792 kilometers per second, it takes time for light from distant objects to reach us. Thus, the observable universe essentially forms a sphere centered on Earth, extending about 5 billion light-years in radius. This radius marks the farthest distance from which light has had time to reach us since the universe began approximately 8 billion years ago. The distinction between the observable universe and the entire universe is crucial. While the former is the portion we can see, the latter includes all space, much of which remains beyond our current observational capabilities. The size of the entire universe remains unknown and may be infinitely large or closed in a manner that defies our standard notions of geometry. The observable universe contains an estimated 2 trillion galaxies, each housing millions to trillions of stars, along with even greater numbers of planets, asteroids, and comets. These staggering numbers have been derived from deep sky surveys and observations with telescopes like the Hubble Space Telescope, which has allowed us to look back in time and see the universe as it was shortly after its birth. These observations have not only expanded our knowledge of the scale of the cosmos, but also provided data on the formation and evolution of cosmic structures. Understanding the observable universe also connects with concepts such as cosmic inflation, a theory suggesting that the universe underwent exponential expansion in the first fractions of a second after the Big Bang. This rapid expansion stretched the fabric of space itself, leading to the vast distances between galaxies that we observe today. It is a concept that bridges cosmology and theoretical physics, offering explanations for the uniformity of the cosmic microwave background and the distribution of galaxies across the sky. Studying the observable universe, we confront the limitations of our current technology and the laws of physics. Light from objects beyond the observable universe has not yet reached us, making these regions inaccessible to our present view. However, advancements in telescope technology and observational methods continue to push the boundaries of what we can see, revealing more about the structure, history, and fundamental laws governing the universe. How do we observe this vast cosmos extending billions of light years? Observing the universe is a multifaceted endeavor, utilizing a variety of technologies and methodologies, each designed to capture different aspects of cosmic phenomena. At the heart of this exploration are telescopes, instruments that have evolved over centuries, from Galileo's simple optical telescopes to today, as sophisticated observatories capable of detecting various forms of electromagnetic radiation from radio waves to gamma rays. Optical telescopes, which collect visible light, were the primary tools for our first steps in cosmic observation. They allow us to see stars, galaxies, and nebulae in the observable universe. However, to understand the full complexity of the universe, we had to go beyond the visible spectrum. Radio telescopes, for example, can detect radio waves emitted by distant cosmic objects. These instruments have uncovered phenomena invisible to optical telescopes, such as the cosmic microwave background, a relic from the universe's birth that provided crucial evidence supporting the Big Bang theory. Infrared astronomy opens a window to observe celestial objects hidden by dust clouds through which visible light cannot penetrate. It has revealed new stars in their formative stages and distant galaxies hidden from view in the visible spectrum. Similarly, X-ray and gamma-ray astronomy allow us to study high-energy processes, such as those occurring around black holes and neutron stars, providing insights into the most violent and energetic events in the cosmos. The development of space telescopes marked a significant leap in our observational capabilities. Instruments like the Hubble Space Telescope, positioned beyond Earth's atmosphere, offer clearer and more detailed images, free from atmospheric distortions. The James Webb Space Telescope, launched to replace Hubble, focuses on infrared astronomy, aiming to observe the universe's first galaxies and delve into the mysteries of star and planet formation. Observing the universe also extends beyond electromagnetic radiation. Neutrino observatories detect nearly massless particles, providing keys to understanding solar processes and supernova explosions. Gravitational wave observatories, such as LIGO Laser Interferometer Gravitational Wave Observatory, have opened a new avenue for studying the universe, detecting ripples in the fabric of space-time itself caused by cataclysmic events like the collisions of black holes or neutron stars. This method offers a unique perspective on the universe, allowing us to study phenomena that emit little or no light. The process of observing the universe is an ever-evolving field, driven by technological innovations and theoretical advancements. As we delve further into our cosmic journey, we encounter natural curiosity about the boundaries of our observations. Why can we see beyond the observable universe? This question touches on fundamental aspects of physics and the nature of the universe itself. The observable universe is defined by the farthest distances from which light has had time to reach us since the universe's birth, about 13.8 billion years ago. This boundary is not physical, but represents a limit imposed by the finite speed of light and the age of the universe. Light travels at a constant speed of about 299,792 kilometers per second in a vacuum. This speed sets a cosmic limit, dictating how far we can see into the universe. Since the universe has existed for about 8 billion years, the most distant light we can observe comes from an equivalent distance, allowing us to see up to the cosmic light horizon. This horizon marks the edge of the observable universe, about 5 billion light-years away due to the universe's expansion since the Big Bang. Beyond this horizon lies the unobservable universe, which remains hidden from our view because light from these regions has not yet reached us. Furthermore, the universe's expansion, driven by dark energy, causes distant galaxies to move away from us at increasing speeds. At a certain point, known as the Hubble length, this recession speed exceeds the speed of light. This does not violate Einstein's theory of relativity, which prohibits objects within space from traveling faster than light because it is the space itself that is expanding. The concept of the observable universe also connects with the theory of cosmic inflation, which suggests that the universe underwent exponential expansion in the first fractions of a second after the Big Bang. This rapid expansion stretched the fabric of space, moving some regions so far away that their light will never reach us, further limiting our vision. This boundary of visibility pertains not only to distance, but also to time. Looking deep into the universe is like looking back in time. The farther we look, the older the light, until we reach the cosmic microwave background, the afterglow of the Big Bang, representing the earliest light that can be observed. Beyond this background lies the epoch of the universe before starlight, a period known as the Cosmic Dark Ages. So how do we observe this vast cosmos extending billions of light-years? Observing the universe is a multifaceted endeavor, utilizing a variety of technologies and methodologies, each designed to capture different aspects of cosmic phenomena. At the heart of this exploration are telescopes, instruments that have evolved over centuries, from Galileo's simple optical telescopes to today, as sophisticated observatories capable of detecting various forms of electromagnetic radiation from radio waves to gamma rays. Optical telescopes, which collect visible light, were the primary tools for our first steps in cosmic observation. They allow us to see stars, galaxies, and nebulae in the observable universe. However, to understand the full complexity of the universe, we had to go beyond the visible spectrum. Radio telescopes, for example, can detect radio waves emitted by distant cosmic objects. These instruments have uncovered phenomena invisible to optical telescopes, such as the cosmic microwave background, a relic from the universe's birth that provided crucial evidence supporting the Big Bang theory. Infrared astronomy opens a window to observe celestial objects hidden by dust clouds, through which visible light cannot penetrate. It has revealed new stars in their formative stages and distant galaxies hidden from view in the visible spectrum. Similarly, X-ray and gamma-ray astronomy allow us to study high-energy processes, such as those occurring around black holes and neutron stars, providing insights into the most violent and energetic events in the cosmos. The development of space telescopes marked a significant leap in our observational capabilities. Instruments like the Hubble Space Telescope, positioned beyond Earth's atmosphere, offer clearer and more detailed images, free from atmospheric distortions. The James Webb Space Telescope, launched to replace Hubble, focuses on infrared astronomy, aiming to observe the universe's first galaxies and delve into the mysteries of star and planet formation. Observing the universe also extends beyond electromagnetic radiation. Neutrino observatories detect nearly massless particles, providing keys to understanding solar processes and supernova explosions. Gravitational wave observatories, such as LIGO Laser Interferometer Gravitational Wave Observatory, have opened a new avenue for studying the universe, detecting ripples in the fabric of space-time itself caused by cataclysmic events like the collisions of black holes or neutron stars. This method offers a unique perspective on the universe, allowing us to study phenomena that emit little or no light. The process of observing the universe is an ever-evolving field, driven by technological innovations and theoretical advancements. As we delve further into our cosmic journey, we encounter natural curiosity about the boundaries of our observations. Why can't we see beyond the observable universe? This question touches on fundamental aspects of physics and the nature of the universe itself. The observable universe is defined by the farthest distances from which light has had time to reach us since the universe's birth, about 13.8 billion years ago. This boundary is not physical, but represents a limit imposed by the finite speed of light and the age of the universe. Light travels at a constant speed of about 299,792 kilometers per second in a vacuum. This speed sets a cosmic limit, dictating how far we can see into the universe. Since the universe has existed for about 13.8 billion years, the most distant light we can observe comes from an equivalent distance, allowing us to see up to the cosmic light horizon. This horizon marks the edge of the observable universe, about 46.5 billion light-years away due to the universe's expansion since the Big Bang. Beyond this horizon lies the unobservable universe, which remains hidden from our view because light from these regions has not yet reached us. Furthermore, the universe's expansion, driven by dark energy, causes distant galaxies to move away from us at increasing speeds. At a certain point, known as the Hubble length, this recession speed exceeds the speed of light. This does not violate Einstein's theory of relativity, which prohibits objects within space from traveling faster than light, because it is the space itself that is expanding. The concept of the observable universe also connects with the theory of cosmic inflation, which suggests that the universe underwent exponential expansion in the first fractions of a second after the Big Bang. This rapid expansion stretched the fabric of space, moving some regions so far away that their light will never reach us, further limiting our vision. This boundary of visibility pertains not only to distance but also to time. Looking deep into the universe is like looking back in time. The farther we look, the older the light, until we reach the cosmic microwave background, the afterglow of the Big Bang, representing the earliest light that can be observed. Beyond this background lies the epoch of the universe before starlight, a period known as the Cosmic Dark Ages. These voids are not static but evolve over time, expanding alongside the universe's growth under the influence of the repulsive force of dark energy. The study of these voids contributes significantly to cosmology, offering a unique perspective for understanding the universe's expansion and the nature of dark energy. Given that voids occupy most of the universe's volume, their dynamics and evolution are crucial for a comprehensive understanding of cosmic history. Moreover, the distribution and size of these voids can be used to test cosmological models, providing constraints on the properties of dark matter and dark energy. When we talk about the edge of the observable universe, we delve into a realm that stretches the boundaries of our understanding and imagination. This concept refers to the farthest extent from which light has reached us since the universe's birth around 13.8 billion years ago. This horizon separates the observable from the unobservable, marking a cosmic boundary defined by the universe's age and the speed of light. The observable universe is a sphere centered around the observer, us on Earth, with a radius of about 46.5 billion light-years. This measurement might seem counterintuitive given the universe's 13.8 billion year age. The discrepancy arises because the universe has been expanding, space itself has stretched, carrying light from the early universe far beyond a simple product of its age and the speed of light. Thus, the edge of the observable universe is not a fixed shell, but a dynamic frontier, constantly moving outward as light from more distant regions reaches us. This edge represents the limit of our cosmic vision, beyond which galaxies and their light have yet to reach Earth. It's important to clarify that this boundary is not an edge in the traditional sense. The universe doesn't end at this point, but our ability to observe it does. Beyond this frontier lies more of the universe, potentially infinite in extent, filled with galaxies, stars, and other cosmic objects we have yet to see. The concept of the edge of the observable universe also intertwines with the inflationary model of the early universe, which suggests a period of exponential expansion shortly after the Big Bang. This rapid expansion pushed vast regions of the universe beyond our observational reach, contributing to the vastness of the unobservable universe. It reminds us of the dynamic nature of the universe, which has been expanding and evolving for billions of years. The edge of the observable universe is not only a physical boundary, but also a temporal one. Looking into space is like looking back in time. Light from the edge of our observable universe brings us information from the universe's infancy, allowing us to see the formation of the first galaxies and the cosmic microwave background, the afterglow of the Big Bang. These observations are crucial for cosmology, providing insights into the universe's origins, composition, and ultimate fate. At the edge of the observable universe, we stand on the brink of cosmic discoveries and mysteries. This frontier, about 46.5 billion light-years away, represents the farthest we can see into space and consequently the earliest moments of the universe accessible to our instruments. What lies at this frontier is a glimpse into the universe's infancy, a time close to the Big Bang itself, revealed through the oldest light that can reach us, the cosmic microwave background. The cosmic microwave background is the afterglow of the Big Bang, the relic radiation left over from when the universe was just 380,000 years old and had become transparent to electromagnetic radiation. Before this epoch, the universe was a hot, dense plasma of electrons, protons, and photons. Photons, particles of light, were constantly absorbed and re-emitted by particles in this plasma, making the universe opaque. As the universe expanded and cooled, protons and electrons combined to form neutral atoms, allowing photons to travel freely. The cosmic microwave background we detect today is that same light, stretched into microwave wavelengths by the universe's expansion. Observing the cosmic microwave background provides us with a snapshot of the universe in its earliest and most uniform state, with slight temperature fluctuations corresponding to density variations. These fluctuations were the seeds of all future structures, galaxies, stars, and planets that fill the universe today. Studying the cosmic microwave background has been crucial for cosmology, offering critical evidence for the Big Bang theory and helping determine key parameters of the universe, including its age, composition, and rate of expansion. Beyond the cosmic microwave background and the earliest light lying at the edge of the observable universe, we enter the realm of speculation and theory. It is believed that the universe beyond our observational horizon continues, perhaps infinitely, filled with galaxies, stars, and planets similar to those we can observe. However, since light from these regions has not yet reached us, their existence remains beyond our current detection or study capabilities. The concept of the edge of the observable universe also challenges our understanding of space and time. In cosmology, the edge of the observable universe is not a physical barrier, but a limit imposed by the speed of light and the universe's age. The farther we look into space, the farther back in time we see. Thus, the edge of the observable universe represents the earliest moments we can observe and a boundary beyond which the universe remains unknown to us. At the edge of the observable universe lies the ancient light of the cosmic microwave background, a direct link to the universe's birth. Beyond this limit, the universe likely continues, filled with structures and phenomena yet to be discovered. The expansion of the universe plays a crucial role in shaping what we can see and understand about the cosmos. This expansion, a cornerstone concept in modern cosmology, means that the fabric of the universe itself is stretching, causing galaxies to move away from each other over time. This cosmic phenomenon directly impacts our perception of the universe, influencing both the size of the observable universe and the light that travels across these vast distances. As the universe expands, light from distant galaxies is stretched along with the space through which it travels. This stretching of light leads to a phenomenon known as redshift, where light shifts to longer, redder wavelengths as it reaches us. The farther a galaxy is, the more its light is redshifted, and the faster it appears to be receding from us. This relationship between distance and recession speed is described by Hubble's law, named after Edwin Hubble, who first observed this expansion in the 1920s. The expansion of the universe not only affects the light we see, but also limits the portion of the universe we can observe. The observable universe is bounded by the cosmic light horizon, the maximum distance from which light has had time to reach us since the universe's beginning. Due to the universe's finite age, about 13.8 billion years, there is a limit to how far we can see. The universe's expansion stretches this horizon, allowing us to see light from more distant reaches, but it also means that some regions are moving away from us so rapidly that their light will never reach us, rendering them unobservable. This expansion also has implications for the future observability of the cosmos. As the universe continues to expand under the influence of dark energy, galaxies beyond our local group, the Milky Way, and its nearest neighbors will eventually move beyond our cosmic horizon. Their light will no longer be able to reach us, making them effectively invisible and isolating us in a much smaller observable universe. Additionally, the expansion of the universe affects the cosmic microwave background, the oldest light in the universe, providing a snapshot of the cosmos just 380,000 years after the Big Bang. As the universe expands, this radiation is redshifted to longer wavelengths, becoming colder and harder to detect, gradually fading from view. One of the key contributions of the cosmic microwave background to cosmology is its role in confirming the Big Bang theory. Before its discovery in 1965 by Arno Penzias and Robert Wilson, the universe's origin was a hotly debated topic. The detection of the cosmic microwave background provided the empirical evidence needed to support the Big Bang theory, fundamentally changing our understanding of the universe's beginning. The cosmic microwave background is also invaluable for its detailed map of the early universe. The tiniest temperature fluctuations in it, as small as 1 part in 100,000, indicate density variations present in the early universe. These variations were the seeds of all current cosmic structures, from galaxies to massive clusters and superclusters. By analyzing these fluctuations, cosmologists can infer the distribution of matter and energy in the early universe, providing data on how galaxies formed and evolved over billions of years. Additionally, the cosmic microwave background is a critical tool for determining the universe's fundamental parameters, such as its age, shape, and composition. Measurements of the cosmic microwave background have helped solidify the understanding that the universe is flat on large scales and provided precise estimates of its age. They also offer insights into the nature and quantity of dark matter and dark energy, the two most mysterious components of the cosmos, which together make up about 95% of the universe's total mass energy content. The study of the cosmic microwave background also touches on the very foundations of physics, challenging and refining our understanding of the fundamental forces of nature. For instance, slight asymmetries and patterns in the cosmic microwave background have implications for the theory of inflation, the leading explanation for the universe's rapid expansion in the first fractions of a second after the Big Bang. This theory predicts a period of exponential growth that would smooth out any irregularities in the universe's density, except for the tiny fluctuations observed in the cosmic microwave background. Observing the edge of the observable universe presents a series of profound challenges, rooted both in the fundamental limitations of our technology and the laws of physics. These challenges include the vast distances involved, the faintness of the signals we seek to detect, and the complex interplay of cosmic phenomena that can obscure or distort our observations. Firstly, the immense scale of the universe is a significant obstacle. The edge of the observable universe lies about 46.5 billion light-years away, a distance light has traveled since the universe's inception about 13.8 billion years ago, considering its expansion over time. At such enormous distances, light from the earliest stars and galaxies is not only incredibly faint, but also significantly redshifted due to the universe's expansion. This redshift stretches the light into longer wavelengths, often beyond the visible spectrum, into the infrared or even microwave range, requiring highly sensitive instruments to detect these signals. Additionally, the cosmic microwave background, the afterglow of the Big Bang and the farthest electromagnetic radiation we can observe, represents both an opportunity and a challenge. While it provides a wealth of information about the early universe, it also forms a kind of cosmic veil beyond which traditional observational methods cannot penetrate. This means that any light or other electromagnetic radiation from before this epoch, roughly 380,000 years after the Big Bang, is hidden from our view. Another challenge in observing the universe's edge is the limitations of our current technology. While telescopes, both ground-based and space-based, have become increasingly sophisticated, there are inherent limits to their resolving power and sensitivity. Observing the faintest and most distant objects requires not only capturing their light, but also resolving it against the cosmic background. Innovations in telescope technology and the development of new observational methods, such as gravitational wave astronomy, offer promising paths to overcoming these obstacles, but they also require significant time, investment, and technological breakthroughs. Moreover, the interstellar and intergalactic medium gas and dust filling the space between stars and galaxies can absorb, scatter, and shift light, complicating observations further. These effects can distort the signals we receive, making it challenging to accurately interpret the data without complex models and corrections. Finally, the theoretical understanding of the universe itself poses a challenge. Our models of cosmic evolution, based on general relativity and quantum mechanics, are tested in the extreme conditions at the edge of the observable universe. Anomalies or unexpected findings in this region can challenge existing theories, requiring new approaches to explain them. This interplay of observations and theories means that understanding the universe's edge is as much a challenge of conceptual innovation as it is of technological advancement. As we continue our documentary, we encounter something mysterious: dark matter, an enigmatic substance that, despite its invisibility and elusiveness, makes up about 27% of the universe. Unlike ordinary matter, which forms stars, planets, and everything we can see or touch, dark matter does not emit, absorb, or reflect light, making it extremely difficult to detect directly. Its presence, however, is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. The story of dark matter begins with observations of galaxies and galaxy clusters. In the 1930s, astronomer Fritz Zwicky studied the Coma cluster of galaxies and found that the visible matter in the galaxies was insufficient to explain the gravitational force holding them in the cluster. The galaxies were moving so quickly that they should have flown apart if only visible matter were acting. This discrepancy suggested the presence of a significant amount of unseen matter, which Zwicky called dark matter. Further evidence for dark matter came from observations of galaxy rotation curves by Vera Rubin and others in the 1970s. They found that stars in galaxies rotated faster than expected based on the gravitational pull from visible matter alone. This again pointed to the existence of an invisible mass, providing the necessary gravitational force to hold galaxies together. Dark matter plays a crucial role in the formation and evolution of cosmic structures. Theories of cosmic evolution suggest that dark matter's gravitational pull was critical in drawing ordinary matter into dense regions that formed galaxies and galaxy clusters. Without dark matter, the universe's structure would be much less complex, and life as we know it might not exist. Despite its pivotal role in the cosmos, dark matter remains one of science's greatest mysteries. It does not interact with electromagnetic forces, meaning it neither emits, absorbs, nor reflects light, making it invisible and detectable only through its gravitational effects. Various experiments are underway to directly detect dark matter particles, including highly sensitive detectors placed deep underground to shield them from cosmic rays and other background noise. The nature of dark matter is a subject of intense study and speculation. Several candidates have been proposed, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos, but none have been detected so far. The search for dark matter is not only about understanding what constitutes most of the universe's mass, but also about a journey that challenges our understanding of physics, the universe, and the nature of matter itself. In this quest to uncover dark matter's mysteries, we confront the limits of our knowledge and technology, embarking on an exploration that bridges the realms of the very large, the cosmos, and the very small, the domain of particle physics. Solving the mystery of dark matter involves not just discovering what makes up most of the universe's mass, but also deepening our understanding of the fundamental laws governing the cosmos, offering insights into the nature of space, time, and reality itself. Dark matter, though invisible and elusive, leaves a trail of cosmic clues that have allowed scientists to infer its existence and understand its fundamental role in shaping the structure and dynamics of the cosmos. The journey to understanding dark matter's existence began with observations of galaxy clusters. In the 1930s, astronomer Fritz Zwicky studied the Coma cluster and noticed that the galaxies within it moved at such high speeds that the visible mass alone could not account for the gravitational force needed to prevent them from flying apart. This discrepancy suggested the presence of a significant amount of invisible mass, which Zwicky called dark matter. Further evidence of dark matter came from galaxy rotation curves in the 1970s. Vera Rubin and her colleagues measured the speeds at which stars rotated around the centers of galaxies. According to gravitational laws, stars on the outskirts of a galaxy should move slower than those closer to the center, where most of the visible mass is concentrated. However, observations showed that stars in the outer regions of galaxies rotated at the same speed as those closer to the center, indicating the presence of a substantial amount of invisible mass providing additional gravitational force. This mass accounts for the high orbital speeds at large distances, a phenomenon that could not be explained by visible matter alone. The cosmic microwave background, the afterglow of the Big Bang, provides another crucial piece of evidence for dark matter's existence. Detailed measurements of the cosmic microwave background by satellites such as COBE, Cosmic Background Explorer, WMAP Wilkinson Microwave Anisotropy Probe, and the Planck Space Observatory have revealed slight temperature fluctuations that indicate density variations in the early universe. The distribution and scale of these fluctuations match the predictions of models that include dark matter, suggesting that dark matter played a significant role in shaping the large-scale structure of the universe. Gravitational lensing also confirms dark matter's existence. This phenomenon occurs when the gravitational field of a massive object bends the light from a more distant object behind it. Observations of gravitational lensing, where the bending of light cannot be explained by visible matter alone, indicate the presence of massive invisible structures attributable to dark matter. These observations of galaxy dynamics, the cosmic microwave background, and gravitational lensing together form a compelling body of evidence for dark matter's existence. Dark matter's role in the universe can be likened to the framework of a building, invisible but essential for holding the structure together. One of its primary roles is in the formation of galaxies and galaxy clusters. In the early universe, the gravitational pull of dark matter initiated the gathering of gas and dust, leading to the formation of stars and galaxies. Without the gravitational framework provided by dark matter, the diffuse gas in the early universe would not have condensed enough to form the stars, planets, and galaxies we observe today. Additionally, dark matter plays a critical role in explaining galaxy rotation curves. Observations show that stars at the outer edges of galaxies rotate at the same speeds as those closer to the center, a phenomenon that contradicts expectations based solely on visible mass. Dark matter provides the additional gravitational force needed to explain these uniform rotation speeds, holding galaxies together and preventing them from tearing apart as they spin. On larger scales, dark matter influences the overall structure of the universe, known as the cosmic web. This vast network of galaxies and galaxy clusters, connected by filaments of dark matter and separated by voids, forms the backbone of the cosmos. The gravitational effects of dark matter are responsible for the clustering and distribution of galaxies, shaping them into the intricate patterns observed by astronomers. Without dark matter, the delicate structure of the cosmic web, with its filaments and nodes where galaxies cluster, would not exist. Dark matter also plays a vital role in gravitational lensing, the phenomenon where light from a distant galaxy or quasar is bent by the gravity of a foreground massive object, such as a galaxy cluster. This effect not only confirms the presence of dark matter, but also allows astronomers to map its distribution in the universe. Gravitational lensing acts as a natural telescope, magnifying and distorting light from distant objects, providing a unique tool for exploring the dark universe. Alongside the topic of dark matter, we encounter dark energy. The concept of dark energy, arose from observations of distant supernovae. In the late 1990s, two independent research teams discovered that these exploding stars, which serve as cosmic beacons, were dimmer than expected. This dimness suggested they were farther away than scientists had predicted, indicating that the universe's expansion was not slowing down as previously thought, but accelerating. This acceleration could only be explained by the presence of an unknown energy component with a repulsive force surpassing gravity's pull, pushing galaxies apart. This component was named dark energy. The nature of dark energy remains one of science's most profound mysteries. Unlike dark matter, which clumps together and helps form the universe's structure, dark energy appears to have a uniform presence throughout space, exerting an equal force everywhere. It does not dilute as the universe expands, distinguishing it from ordinary and dark matter. One leading theory suggests that dark energy might be a property of space itself, described by Albert Einstein as the cosmological constant, a term he introduced in his equations of general relativity and later called his biggest blunder. In this view, empty space is not nothing but has its intrinsic energy. Another possibility is that dark energy is a dynamic field, akin to electromagnetic fields, but with a unique repulsive property. This field, sometimes referred to as quintessence, could vary over time, unlike the cosmological constant, which remains constant. Theoretical models propose various forms of quintessence, but there is no direct evidence supporting these theories yet. Delving into the mysterious nature of dark energy, we uncover its crucial role in the universe's expansion, a force that accelerates the growth of the cosmos beyond what was once imagined. Dark energy, constituting about 68% of the universe's total energy content, acts as a counterforce to gravity, the force that pulls galaxies and other cosmic structures together. Instead of attracting, dark energy repels, stretching the fabric of the universe and causing it to expand. This acceleration was first observed in the late 1990s through studies of distant supernova. Astronomers expected these cosmic explosions to show that the universe's expansion was slowing down due to gravity. However, the data showed the opposite: the universe was expanding faster than in the past, pointing directly to the influence of dark energy. Unlike matter, which can clump together to form structures such as galaxies and galaxy clusters, dark energy is evenly spread throughout the universe, exerting the same repulsive force everywhere, leading to an increasing expansion rate over time. Dark energy's impact on the universe's expansion is profound and far-reaching. As the expansion accelerates, dark energy influences the ultimate fate of the cosmos. If its strength remains constant or increases over time, the universe could continue expanding indefinitely, becoming ever colder and emptier as galaxies drift apart and star formation eventually ceases. In more extreme models, if dark energy grows stronger, it could lead to a Big Rip scenario, where the repulsive force becomes so dominant that it tears apart galaxies, stars, planets, and eventually atoms themselves. Understanding how dark energy affects the universe's expansion involves not only measuring this expansion rate, but also constructing a history of the cosmos. Observations of the cosmic microwave background, the afterglow of the Big Bang, and large-scale galaxy surveys provide a map of the universe's evolution. These data allow scientists to trace dark energy's influence over billions of years, observing how its repulsive force has shaped the cosmos. The study of dark energy and its impact on cosmic expansion is at the forefront of modern cosmology. It challenges our understanding of physics, requiring new theories to explain its properties and effects. Theories such as quintessence suggest that dark energy is not constant, but a dynamic field that changes over time, potentially having different effects on the universe's expansion. As we near the end of this chapter on the mysteries of the cosmos, it is essential to address a common question. Are dark matter and dark energy the same at the edge of the observable universe? Despite their similar names, dark matter and dark energy are fundamentally different components of the universe, each playing a unique role in shaping its structure and evolution, even at the most distant reaches of what we can observe. Dark matter, accounting for about 27 of the universe's energy content, acts as a cosmic glue that holds galaxies and galaxy clusters together. It exerts gravitational pull, helping to form the vast web-like structures of galaxies that span the observable universe. Without dark matter, the gravitational forces created by visible matter alone would be insufficient to prevent galaxies from flying apart due to their rotation speeds. Dark matter's influence is just as critical at the edge of the observable universe as it is in our local galactic neighborhood, providing the necessary mass to form the large-scale structures we can detect even at great distances. On the other hand, dark energy, making up about 68 of the universe's energy content, represents a repulsive force that causes the accelerated expansion of the universe. Unlike dark matter, dark energy does not clump together to form structures, but is thought to be uniformly distributed throughout space. Its effect is to push galaxies apart, counteracting the force of gravity. At the edge of the observable universe, dark energy's influence is observed through the universe's expansion rate, which increases with distance. This accelerated expansion means that the farther we look into space, the faster galaxies are moving away from us, a phenomenon directly linked to dark energy's presence. The distinction between dark matter and dark energy remains consistent throughout the universe, from our local galactic group to the farthest reaches of the observable universe. Both entities play vital roles in cosmic evolution, but operate through fundamentally different mechanisms. Dark matter attracts, while dark energy repels. This duality underpins the structure and fate of the universe, influencing everything from galaxy formation to the ultimate destiny of the cosmos. As we explore the universe's edges, we encounter the limits of our understanding, where dark matter and dark energy shape the cosmic landscape in profound but distinct ways. Ongoing study of these mysterious components challenges our theories of physics and cosmology, pushing us toward deeper insights into the nature of the universe. As research continues, we may discover that the roles and properties of dark matter and dark energy evolve with our expanding cosmic horizons, but their fundamental differences remain a cornerstone of our current understanding of the cosmos. Continuing our journey into cosmic infinity, we set out to explore the various theories humanity holds about the universe. Venturing into the depths of space and time, where the known meets the unknown, this chapter unveils a tapestry of ideas and hypotheses that stretch our understanding of the cosmos to its limits and beyond. As we delve deeper, we encounter the intriguing and captivating concept of the multiverse, a theory proposing that our universe, with its galaxies and stars, might be just one bubble in a vast cosmic foam made up of countless other universes. Each of these universes, according to the theory, could contain different laws of physics, alternative histories, and possibly variations of reality that we can scarcely imagine. Exploring the concept of the multiverse takes us to one of the most exhilarating frontiers of cosmology, where the existence of multiple universes beyond our own could redefine the boundaries of reality. This theory, emerging from the intersections of inflationary theory, string theory, and quantum mechanics, suggests a cosmos filled with an infinite array of universes, each potentially governed by its own physical laws and constants. Inflationary theory posits that the rapid expansion of the universe immediately following the Big Bang could have led to the creation of numerous distinct pockets of space-time, evolving into separate universes within a grand multiverse. Similarly, string theory, in its quest to unify general relativity and quantum mechanics, introduces the possibility of multiple dimensions. These dimensions, varying in configuration, hint at a spectrum of universes, each unique in its fundamental properties. Quantum mechanics adds another layer to this theory with the principle of quantum decoherence, which suggests that every quantum possibility spawns its own universe. This interpretation opens the door to a multiverse where every conceivable outcome is realized in its own parallel universe. Despite its theoretical allure, the multiverse remains a speculative domain lacking direct evidence. The proposed universes would exist beyond the observable limits set by the speed of light and the age of our universe, making direct observation or interaction a profound challenge. This places the multiverse within the realm of theoretical models and hypotheses, awaiting indirect evidence or innovative theoretical breakthroughs for validation. Physicists and cosmologists are actively seeking signs that might hint at the reality of the multiverse, analyzing the cosmic microwave background and other cosmic phenomena for potential clues. These efforts push the boundaries of our scientific inquiry, testing the limits of what can be observed and understood about the cosmos. As we journey further into the realms of cosmic possibilities and the edge of theoretical physics, we encounter the concept of wormholes. Often depicted in science fiction as tunnels through space-time that allow instant travel across vast cosmic distances or even between different universes, wormholes are grounded in real scientific theories and equations. These hypothetical passageways through space-time are predicted by the theory of general relativity, which describes gravity as the warping of space-time by mass and energy. The mathematical foundation for wormholes comes from solutions to the equations of general relativity. One such solution, the Einstein-Rosen bridge, proposed by Albert Einstein and Nathan Rosen in the 1930s, describes a tunnel-like structure connecting two separate points in space-time. In theory, a wormhole could connect distant parts of the universe, providing a shortcut that bypasses the usual constraints imposed by the speed of light. Furthermore, a wormhole could potentially link our universe to another entirely different universe, presenting possibilities that captivate both scientists and philosophers. However, the existence of wormholes extends beyond their theoretical foundations to questions of physical reality and observation. For a wormhole to be traversable and stable, it would require a form of matter or energy with negative density, known as exotic matter, to prevent it from collapsing. Exotic matter would counteract the immense gravitational forces that would naturally close a wormhole, keeping it open for the passage of matter. Yet exotic matter and the conditions necessary to create and sustain a wormhole have not been observed in nature, and their feasibility remains speculative. Searching for evidence of wormholes involves indirect methods, as their direct observation would be extremely challenging. Scientists propose that the gravitational effects of a wormhole on light and nearby matter could potentially be detected through advanced astronomical observations. For example, a wormhole acting as a gravitational lens, bending light from a distant star in a way distinct from known objects like black holes, could provide hints of its presence. Despite the intriguing potential of wormholes, their existence remains purely hypothetical. Theoretical models allow for their possibility, but the laws of physics as we understand them and the technological constraints we face place real wormholes and the prospect of using them for cosmic travel or communication far beyond our current capabilities. The energy scales required to manipulate space-time and create a wormhole, let alone exotic matter to stabilize it, are vastly beyond present human means. Continuing the theme of theories, we encounter the theory of everything. This ambitious theory aims to unify all fundamental forces of nature into a single theoretical framework, providing a comprehensive understanding of the laws of the physical universe. The quest for a theory of everything represents the pinnacle of human ambition in physics, aiming to bridge the gap between general relativity, which governs cosmic scales, and quantum mechanics, which rules the subatomic world. General relativity, Albert Einstein's masterpiece, describes the force of gravity as the curvature of space-time caused by mass and energy. It has passed every test given to it on cosmic scales, from the orbits of planets to the bending of light by galaxies. Quantum mechanics, with its principles of uncertainty and superposition, has been equally successful in explaining phenomena at the smallest scales, from the behavior of atoms to the properties of particles in accelerators. Yet despite their individual successes, general relativity and quantum mechanics remain fundamentally incompatible. General relativity predicts a smooth fabric of space-time, while quantum mechanics suggests that space-time at the smallest scales is turbulent and frothy. The theory of everything seeks to reconcile these two pillars of modern physics into a single framework that could describe all phenomena under one set of rules. One leading candidate for a theory of everything is string theory, which posits that the fundamental particles of the universe are not point-like, but are instead one-dimensional strings. These strings vibrate at different frequencies, and their vibrations determine the properties of particles, such as mass and charge. String theory is enticing because it naturally incorporates quantum mechanics and has the potential to include gravity, suggesting a way to unite all forces. Another approach is loop quantum gravity, which attempts to quantize space-time itself, viewing it as made up of tiny loops woven into a fabric. This theory focuses on creating a quantum theory of gravity that is consistent with the principles of quantum mechanics without requiring extra dimensions or the concept of strings. Delving deeper into the theme of a theory of everything, we explore how quantum mechanics itself is intricately linked with the cosmos. Quantum mechanics, the fundamental theory in physics that describes the physical properties of nature at the scale of atoms and subatomic particles, might seem far removed from the vast expanses of the cosmos. However, its principles are deeply woven into the fabric of the universe, influencing cosmic evolution and structure in profound ways. At the heart of quantum mechanics are the principles of uncertainty and superposition, which dictate that particles can exist in multiple states simultaneously until they are observed, challenging our classical notions of reality. These principles are not only applicable to the behavior of particles in a laboratory, they are also crucial for understanding processes occurring on cosmic scales. For example, nuclear fusion, which powers stars including our Sun, is governed by quantum tunneling, a phenomenon that allows particles to pass through energy barriers. Without this quantum effect, stars would not ignite, and the universe as we know it, filled with light and life, would not exist. Quantum mechanics also plays a vital role in the early universe. Immediately after the Big Bang, the universe was a hot, dense plasma where quantum fluctuations, tiny fluctuations in energy occurred. These fluctuations, amplified by cosmic inflation, became the seeds for the large-scale structure of the universe, leading to the formation of galaxies and galaxy clusters. The distribution of matter throughout the universe, from the cosmic microwave background to the cosmic web of galaxies, bears the imprint of these initial quantum fluctuations. Moreover, quantum mechanics is key to understanding black holes, those enigmatic objects where gravity is so strong that not even light can escape. Stephen Hawking's work on black holes showed that due to quantum effects at the event horizon, black holes can emit radiation known as Hawking radiation. This discovery bridges quantum mechanics and general relativity, offering insights into how quantum principles apply in conditions of extreme gravity. The intriguing concept of dark matter, which holds galaxies together but does not emit light, also invites quantum explanations. Several hypothetical particles that could make up dark matter, such as WIMPs, weakly interacting massive particles or axions, arise from theories extending the standard model of particle physics, which is based on quantum mechanics. The search for these particles involves understanding their quantum properties and how they interact with the gravitational forces shaping the cosmos. In our journey through the realms of quantum mechanics and the cosmos, we naturally approach a question that has captivated human imagination across ages and cultures. Is time travel theoretically possible? Within the framework of modern physics, the concept of time travel is not merely the stuff of science fiction, but a serious scientific inquiry intersecting with our understanding of the fundamental laws of the universe. The theory of relativity, developed by Albert Einstein, provides the most significant theoretical basis for considering time travel. According to general relativity, the fabric of space-time is curved by mass and energy, and this curvature dictates how objects move through space and time. Remarkably, the equations of general relativity allow for solutions where space-time curves back on itself, forming loops known as closed time-like curves. These structures theoretically permit a path from a point in space-time to the past or future, and then back to the original point, suggesting the possibility of time travel. One hypothetical structure that could allow for such time travel is a wormhole, a bridge or tunnel through space-time connecting distant parts of the universe or different times. If a wormhole could be stabilized with exotic matter which possesses negative energy density, it might theoretically be possible to traverse it and achieve time travel. However, the existence of stable wormholes and exotic matter has not been proven, and the practical challenges of creating or finding a wormhole, let alone traveling through it, remain immense. Another concept related to time travel arises from the idea of cosmic strings, hypothetical defects in space-time left over from the early universe. If two cosmic strings were to pass close to each other, or one cosmic string were to move at a significant fraction of the speed of light, they could theoretically create conditions for time travel to the past. Despite these exciting theoretical possibilities, time travel faces numerous scientific and philosophical challenges. Firstly, paradoxes associated with time travel, such as the grandfather paradox, where a time traveler could potentially prevent their own existence, raise questions about causality and the nature of time itself. Moreover, the energy scales required to manipulate space-time for time travel are currently beyond human capabilities. Quantum mechanics also enters the discussion of time travel, particularly through the concept of quantum entanglement, which suggests a form of communication between particles that is instantaneous and independent of distance. Some interpretations of quantum mechanics propose that entangled particles are connected by wormholes, hinting at a quantum basis for space-time structures that could theoretically allow for time travel. However, utilizing such phenomena for macroscopic time travel remains speculative. Now let's address an intriguing question. Could life exist elsewhere in the universe? This question not only probes the limits of our understanding of life, but also touches on profound philosophical questions about our place in the cosmos. The universe is vast, with billions of galaxies, each containing billions of stars and potentially even more planets. The Kepler Space Telescope and other missions have discovered thousands of exoplanets, planets orbiting stars outside our solar system, many of which lie in the habitable zone where conditions could be right for liquid water, a crucial ingredient for life as we know it. These discoveries have significantly expanded our understanding of potential habitats for life, suggesting that conditions for life might be more common than previously thought. The search for extraterrestrial life spans from planets and moons within our solar system to distant exoplanets. Mars, with its evidence of past water flows and the detection of seasonal methane spikes in its atmosphere, is a primary target for missions searching for signs of past or present microbial life. Moons, such as Europa and Enceladus, with their subsurface oceans, offer another tantalizing possibility for habitability, leading to plans for future missions to explore these icy worlds. Beyond our solar system, the study of exoplanets has revealed a rich diversity of worlds, including Earth-like planets that might have conditions suitable for life. Characterizing the atmospheres of exoplanets, though still in its infancy, aims to detect biosignature gases, gases produced by living organisms that could accumulate in a planet's atmosphere, offering a potential indirect method of detecting life. The search for life also touches on the question of what form life might take in other parts of the universe. Life, as we know it, is carbon-based and uses water as a solvent. However, scientists speculate about the possibility of alternative biochemistries, such as silicon-based life forms or life existing in environments with solvents other than water, such as methane or ammonia. This opens the door to a broader understanding of life that could exist under conditions vastly different from those on Earth. Continuing our journey through the unknown realms of the cosmos, our next topic brings us closer to home, exploring the tools that serve as our windows to the universe telescopes. These marvels of engineering and science allow us to peer into the vast reaches of space, from neighboring planets to galaxies billions of light years away, aiding our quest to understand if life exists beyond Earth and uncovering the mysteries of the universe. Telescopes work by gathering and focusing light from celestial objects to create an image. The larger the telescope's light-gathering area, the fainter the objects it can observe and the more detail it can reveal. There are two main types of telescopes, refractors and reflectors, each using different mechanisms to collect light. Refractor telescopes use lenses to gather and focus light. The primary lens, known as the objective, bends incoming light rays to converge at a focal point, where the image is magnified and observed through an eyepiece. Historically significant refractor telescopes were the first type to be invented, and Galileo Galilei used one to make groundbreaking astronomical discoveries in the early 17th century. Reflector telescopes, on the other hand, use mirrors instead of lenses. A large curved mirror, known as the primary mirror, reflects light to a focal point. A secondary mirror can then redirect this light to an eyepiece or camera. Reflector telescopes have several advantages over refractors, including eliminating chromatic aberration, a distortion seen in refractors due to lenses breaking light into different colors, and the ability to build much larger telescopes since mirrors can be supported from behind, reducing sagging and distortion. Beyond these traditional telescopes, technological advancements have led to the development of specialized telescopes for observing invisible forms of electromagnetic radiation, such as radio, infrared, ultraviolet, X-ray, and gamma rays. These instruments allow astronomers to explore aspects of the universe invisible to optical telescopes, from cold dust clouds where new stars are born to high-energy environments around black holes and neutron stars. For example, radio telescopes use large antennas to detect radio waves from space, providing unique data on cosmic phenomena such as pulsars, quasars, and the cosmic microwave background radiation. Space telescopes, like the Hubble Space Telescope, operate above Earth's atmosphere, which absorbs or scatters much of the electromagnetic spectrum, offering an unobstructed view of the universe in optical, ultraviolet, and near-infrared light. Operating telescopes, whether ground-based or space-based, involves not only collecting light, but also sophisticated data analysis techniques. Images captured by telescopes are processed and analyzed using computer algorithms, revealing details and structures invisible in raw data. This analysis can include measuring distances, compositions, temperatures, and motions of celestial objects, contributing to our understanding of the universe's structure, its evolution, and the fundamental laws of physics. Now let's turn our attention to a monumental step in our astronomical capabilities, the James Webb Space Telescope, JWST. Launched into space in late 2021, the JWST represents the most complex and powerful space telescope ever built, poised to unveil the mysteries of the universe with unprecedented clarity and depth. The JWST is an international collaboration led by NASA, with significant contributions from the European Space Agency, ESA, and the Canadian Space Agency, CSA. It is designed to observe the universe in the infrared spectrum, allowing it to peer through cosmic dust clouds that obscure optical telescopes' views and detect the faint light of distant stars and galaxies. With a primary mirror measuring 5 meters in diameter, the JWST has more than 6 times the light-gathering capacity of its predecessor, the Hubble Space Telescope, enabling it to observe objects at much greater distances and, therefore, much further back in time than ever before. One of the JWST's primary goals is to study the edge of the observable universe, aiming to observe the first galaxies that formed after the Big Bang over 13.5 billion years ago. By examining these early galaxies, astronomers hope to learn more about the formation and evolution of the first structures in the universe, shedding light on the processes that led to the intricate cosmic web of galaxies we observe today. The JWST's infrared capabilities are crucial for this task, as the light from these distant galaxies has been stretched into the infrared spectrum due to the universe's expansion, a phenomenon known as redshift. Additionally, the JWST will study the atmospheres of exoplanets, potentially identifying signs of habitability or even life. Its powerful instruments can analyze the chemical compositions of exoplanet atmospheres, detecting molecules such as water vapor, carbon dioxide, and methane, which might indicate the presence of biological processes. The JWST is also set to unravel the mysteries of star formation and planet formation in our own galaxy. By observing molecular clouds where stars are born, the telescope will provide data on the conditions and processes that lead to the birth of stars and their planetary systems. This knowledge is crucial not only for understanding the origins of our solar system, but also for comprehending the diversity of planetary systems across the galaxy. As the JWST embarks on its mission, it promises to transform our understanding of the universe. Its observations are expected to challenge existing theories, reveal new phenomena, and provide answers to long-standing questions about the nature of the cosmos. From the first light after the Big Bang to the formation of galaxies, stars, and planets, the JWST will offer a window into the history and evolution of the universe, bringing us closer than ever to understanding the edge of the universe and our place within it. Over the past few decades, satellites have revolutionized astronomy by providing an observation point outside Earth's atmosphere, inaccessible to ground-based observatories. From detailed mapping of the cosmic microwave background to discovering exoplanets and monitoring cosmic phenomena, satellites have opened new windows into space, each contributing unique data that deepens our cosmic knowledge. The launch of the Hubble Space Telescope in 1990 marked a turning point in space exploration. Positioned in Earth's orbit, Hubble captured images of unparalleled clarity, revealing the dynamic and detailed structure of the universe. Its observations have led to breakthroughs in our understanding of black holes, the age of the universe, the existence of dark energy, and the processes governing the life cycles of stars. Hubble's deep field images, showing galaxies billions of light-years away, provided a glimpse into the early stages of the universe, illustrating the evolution of galaxies over time. Another significant satellite, the Cosmic Background Explorer COBE, launched in 1989, mapped the cosmic microwave background radiation, the afterglow of the Big Bang. COBE's measurements provided compelling evidence for the Big Bang theory, showing that the background radiation of the universe is remarkably uniform, with slight variations supporting models of cosmic inflation. This discovery was pivotal, earning the 2006 Nobel Prize in Physics. Following COBE, the Wilkinson Microwave Anisotropy Probe WMAP, and later the Planck satellite refined the measurements of the cosmic microwave background, creating maps with unprecedented precision. These observations helped accurately determine the age, composition, and expansion rate of the universe, contributing to the standard cosmological model that describes the universe as flat and dominated by dark energy and dark matter. Satellites also play a crucial role in the search for exoplanets. The Kepler Space Telescope, launched in 2009, was specifically designed to detect Earth-like planets in the habitable zone of their stars, where conditions might be right for liquid water. Kepler discovered thousands of exoplanets, showing that our galaxy is teeming with diverse worlds, many of which challenge our understanding of planet formation and the potential for life beyond Earth. Furthermore, satellites dedicated to observing the Sun, such as the Solar Dynamics Observatory SDO, have provided detailed data on solar activity, including sunspots, flares, and coronal mass ejections. These observations are vital for understanding the Sun's influence on space weather and its impact on Earth's environment. Continuing the theme of how scientists use telescope data to study distant objects, when light or other forms of electromagnetic radiation from distant objects reach a telescope. Whether orbital or ground-based, it is first collected by the telescope's primary mirror or lens. This light is then focused to create an image or directed into instruments such as spectrometers, which break the light down into its constituent wavelengths. Analyzing this light across different wavelengths is fundamental to studying the properties and behaviors of celestial objects millions to billions of light-years away. One key method used by scientists is spectroscopy, which involves studying the spectrum of light emitted, absorbed, or reflected by objects. Each chemical element leaves a unique fingerprint in the light spectrum, allowing scientists to determine the composition of stars, galaxies, and nebulae. Spectroscopy can reveal not only what distant objects are made of, but also their temperatures, densities, and velocities toward us or away from us, indicated by redshift or blue shift in their spectral lines. Photometry, another crucial method, measures the intensity of light from an object across a range of wavelengths. By analyzing how bright an object appears and how its brightness changes over time, astronomers can infer its size, luminosity, distance, and even the presence of planets transiting in front of stars. Variations in brightness can also indicate other dynamic processes, such as stellar pulsations or eclipsing binary stars. Data collected by telescopes often require complex processing and analysis using advanced algorithms and computer models. This process involves correcting for distortions caused by Earth's atmosphere, instrument noise, and other sources of interference. The advent of digital image processing and advances in computer technology have greatly increased the volume and quality of data that can be collected and analyzed, enabling discoveries that were impossible a few decades ago. Astronomers also use the method of parallax to measure the distances to nearby stars. By observing how a star's position shifts relative to the background of more distant stars as Earth orbits the Sun, scientists can calculate its distance from us. This fundamental measurement helps build the cosmic distance ladder used to determine the distances to far more remote objects in the universe. As we delve deeper into space through the lenses of powerful telescopes, astronomers face numerous challenges in their quest to observe distant galaxies. These challenges are related to the vast distances involved, the faintness of the objects being observed, and the limitations of our current technology and methods. Overcoming these obstacles is crucial for advancing our understanding of the universe's structure, its evolution, and the fundamental processes that govern it. One of the primary challenges is the sheer distance to these distant galaxies, which lie millions to billions of light-years away. At such vast distances, the light reaching Earth is extremely faint, making these galaxies difficult to detect and study. The expansion of the universe exacerbates this problem, as it causes the light from distant galaxies to be stretched to longer, redder wavelengths, a phenomenon known as redshift. As a result, much of the light from these galaxies falls outside the visible spectrum and must be observed using infrared and radio telescopes. Atmospheric interference is another significant obstacle for ground-based telescopes. Earth's atmosphere can distort and absorb light from distant celestial objects, making them less clear and reducing the amount of information that can be gathered. While space telescopes such as the Hubble Space Telescope and the upcoming James Webb Space Telescope are free from atmospheric interference, they are incredibly complex and costly to build and launch, limiting the number of such missions that can be undertaken. Additionally, the finite speed of light imposes fundamental limitations on our ability to observe the universe in real time. Observing distant galaxies is akin to looking back in time, as we see them as they were millions or billions of years ago, depending on their distance. While this allows astronomers to study the history of the universe, it also means that we cannot know the current state of these distant galaxies, complicating our understanding of cosmic evolution. Another challenge is the enormous amount of data produced by modern telescopes, requiring sophisticated software and algorithms for processing and analysis. Extracting meaningful information from these data, such as the properties of galaxies, the distribution of dark matter, and the rate of cosmic expansion, requires extensive computational resources and advanced data analysis methods. Interference from cosmic objects closer to home can also hinder observations of distant galaxies. Light from stars within our own galaxy and interstellar dust can obscure the view of more distant objects, necessitating methods to filter out this background noise and isolate the light from target galaxies. Despite these difficulties, astronomers continue to make significant strides in observing distant galaxies through technological innovations, the development of more sensitive detectors, and the launch of new telescopes capable of observing the universe in various wavelengths. These efforts are gradually peeling back the layers of the universe, revealing the intricate dance of galaxies through cosmic time and space, bringing us closer to understanding the grand scale of the cosmos. Transitioning to the next chapter, we embark on a journey back in time to the very beginning, the Big Bang. This monumental event marks the origin of the universe as we know it, a singular explosion from which all space, time, matter, and energy emerged approximately 8 billion years ago. It was not an explosion in space, but a rapid expansion of space itself, creating the conditions for the cosmos to evolve from a hot, dense state into the vast, cooler expanse filled with galaxies, stars, planets, and life that we observe today. The Big Bang theory is supported by multiple lines of evidence, making it the leading explanation for the origin of the universe. One of the most compelling pieces of evidence is the cosmic microwave background CMB radiation, a faint glow permeating the universe accidentally discovered in 1965 by Arno Penzias and Robert Wilson. This discovery provided a direct snapshot of the young universe, a relic of radiation from about 380,000 years after the Big Bang, when the cosmos cooled enough for photons to travel freely through space. The uniformity and slight variations in the CMB radiation match the predictions of the Big Bang theory, offering a window into the conditions of the early universe. Another pillar supporting the Big Bang theory is the observation of the universe's expansion. Edwin Hubble's observations in the 1920s, showing that galaxies are moving away from each other, revealed that the universe is not static, but expanding. This expansion, when traced back in time, implies that the universe must have originated from a single, small, dense point. The Big Bang theory explains this expansion and predicts that the farther a galaxy is, the faster it is moving away from us, a relationship known as Hubble's law, which has been confirmed by subsequent observations. The theory also successfully explains the abundance of light elements such as hydrogen, helium, and lithium. Nuclear reactions in the first few minutes after the Big Bang are believed to have produced these elements in proportions that closely match what is observed today in the universe. This nucleosynthesis, the process of forming new atomic nuclei from pre-existing matter, provides a critical test for the Big Bang theory, further solidifying its status as a cornerstone of modern cosmology. Despite its success, the Big Bang theory also opens up new questions and mysteries, such as the nature of dark matter and dark energy, which appear to dominate the universe's mass-energy content and the cause of the universe's initial expansion. Additionally, the theory does not explain what preceded the Big Bang or what caused it, leaving room for further theoretical development and discovery. Since the pivotal moment of the Big Bang, the universe has embarked on a complex journey of evolution, transitioning from a hot, dense state to the vast, structured cosmos filled with galaxies, stars, and planets that we observe today. This evolution is a story of cosmic expansion, cooling, and the relentless work of gravity, knitting the fabric of the universe together over billions of years. In the immediate aftermath of the Big Bang, the universe was a seething cauldron of particles and radiation, too hot and dense for atoms to form. During this period, known as the Planck epoch, the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces were unified. As the universe expanded, it rapidly cooled, allowing these forces to separate and the first subatomic particles, including protons, neutrons, and electrons, to emerge. About 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons to form neutral hydrogen atoms, a process known as recombination. This epoch marked the transition of the universe from opacity to transparency, allowing photons to travel freely for the first time, creating the cosmic microwave background radiation, a snapshot of the young universe that we can observe today. Over the next few 100 million years, the universe entered the cosmic dark ages, a period before the first stars ignited. During this time, gravity began to draw the first clouds of gas and dark matter together, forming the seeds of future galaxies. The end of the Dark Ages came with the formation of the first stars, whose nuclear furnaces reignited the universe. These first generations of stars were massive and short-lived, dying in spectacular supernovae that seeded the cosmos with heavier elements necessary for building planets and life. Galaxies began to take shape, forming from the gravitational collapse of dark matter halos that drew in gas and dust. Within these galaxies, new generations of stars were born, surrounded by disks of material that coalesced into planets, asteroids, and comets. Over time, galaxies grew through mergers and accretions, creating the diverse galactic structures from spirals to ellipticals that we observe today. As the universe continued to expand and cool, the rate of star formation gradually slowed, leading to the current epoch where the formation of new stars balances the death of old ones. The discovery of dark energy, a mysterious force accelerating the expansion of the universe, adds another layer to our understanding of cosmic evolution, suggesting a future where galaxies become increasingly isolated from one another. Delving into the depths of space and time, where the known meets the unknown, this chapter unfolds a tapestry of ideas and hypotheses that stretch our understanding of the cosmos to its limits and beyond. As we progress, we encounter the astonishing and captivating concept of the multiverse, a theory suggesting that our universe, with its galaxies and stars, might be just one bubble in a vast cosmic foam of countless other universes. Each of these universes, according to the theory, could contain different physical laws, alternative histories, and possibly variations of reality that are beyond human imagination. Exploring the concept of the multiverse takes us to one of the most thrilling frontiers of cosmology, where the existence of multiple universes beyond our own could redefine the boundaries of reality. This theory, emerging at the intersection of inflationary theory, string theory, and quantum mechanics, proposes a cosmos filled with an infinite number of universes, each potentially governed by its own set of physical laws and constants. Inflationary theory asserts that the rapid expansion of the universe immediately following the Big Bang could have led to the formation of numerous distinct pockets of space-time, evolving into individual universes within the grand multiverse. Similarly, string theory, in its attempt to unify general relativity and quantum mechanics, introduces the possibility of multiple dimensions. These dimensions, varying in configuration, hint at a spectrum of universes, each unique in its fundamental properties. Quantum mechanics adds another layer to this theory with the principle of quantum decoherence, suggesting that every quantum possibility spawns its own universe. This interpretation opens the door to a multiverse where every conceivable outcome is realized in its own parallel universe. Despite the theoretical appeal of the multiverse, it remains a speculative domain, lacking direct evidence. The proposed universes would exist beyond the observable horizon set by the speed of light in the age of our universe, making direct observation or interaction with them a significant challenge. This places the multiverse within the realm of theoretical models and hypotheses, awaiting indirect evidence or innovative theoretical breakthroughs for confirmation. Physicists and cosmologists actively seek signs that could hint at the reality of the multiverse, analyzing cosmic microwave background radiation and other cosmic phenomena for potential clues. These efforts push the boundaries of our scientific inquiry, testing the limits of what can be observed and understood about the cosmos. Moving further into realms of cosmic possibilities and the edges of theoretical physics, we encounter the concept of wormholes. Wormholes, often depicted in science fiction as tunnels through space-time, allowing instantaneous travel across vast cosmic distances or even between different universes, are rooted in real scientific theories and equations. These hypothetical passages through space-time are predicted by general relativity, which describes gravity as the curvature of space-time by mass and energy. The mathematical basis for wormholes comes from solutions to the equations of general relativity. One such solution, the Einstein-Rosen bridge, was proposed by Albert Einstein and Nathan Rosen in the 1930s. It describes a tunnel-like structure connecting two separate points in space-time. Theoretically, a wormhole could link distant parts of the universe, providing a shortcut that bypasses the usual constraints imposed by the speed of light. Alternatively, it could connect our universe to another entirely different universe, presenting possibilities that fascinate both scientists and philosophers. However, the existence of wormholes extends beyond their theoretical foundations to the question of physical reality and observation. For a wormhole to be traversable and stable, it would require a form of matter or energy with negative density, known as exotic matter, to prevent it from collapsing. Exotic matter would counteract the immense gravitational forces that would naturally close a wormhole, keeping it open for the passage of matter. Yet exotic matter and the conditions needed to create and maintain a wormhole have not been observed in nature, and their feasibility remains a matter of speculation. The search for evidence of wormholes involves indirect methods, as direct observation would be extremely challenging. Scientists propose that the gravitational effects of a wormhole on light and nearby matter could potentially be detected using advanced astronomical observations. For example, a wormhole acting as a gravitational lens, bending light from a distant star in a distinctive way different from known objects like black holes, could provide hints of its presence. Despite the intriguing potential of wormholes, their existence remains purely hypothetical. Theoretical models allow for their possibility, but the laws of physics, as we currently understand them, and technological limitations place real wormholes and the prospect of using them for cosmic travel or communication far beyond our reach. The energy scales required to manipulate space-time and create a wormhole, let alone the exotic matter needed to stabilize it, far exceed current human capabilities. Continuing the theme of theories, we find the theory of everything. This ambitious theory aims to unify all fundamental forces of nature into a single theoretical framework, providing a comprehensive understanding of the laws of the physical universe. The search for a theory of everything represents the pinnacle of human aspirations in physics, aiming to bridge the gap between general relativity, which governs cosmic scales, and quantum mechanics, which rules the subatomic realm. General relativity, a masterpiece of Albert Einstein, describes the force of gravity as the curvature of space-time caused by mass and energy. It has withstood all tests on cosmic scales, from the orbits of planets to the bending of light by galaxies. Quantum mechanics, with its principles of uncertainty and superposition, has been equally successful in explaining phenomena at the smallest scales, from the behavior of atoms to the properties of particles in accelerators. However, despite their individual successes, general relativity and quantum mechanics remain fundamentally incompatible. General relativity predicts a smooth fabric of space-time, while quantum mechanics suggests that space-time on the smallest scales is turbulent and frothy. A theory of everything seeks to reconcile these two pillars of modern physics into a unified framework that could describe all phenomena under a single set of rules. One of the leading candidates for a theory of everything is string theory, which posits that the fundamental particles of the universe are not point-like, but rather one-dimensional strings. These strings vibrate at different frequencies, and their vibrations determine the properties of particles, such as mass and charge. String theory is enticing because it naturally incorporates quantum mechanics and has the potential to include gravity, suggesting a way to unite all forces. Another approach is loop quantum gravity, which attempts to quantize space-time itself, viewing it as composed of tiny loops woven into the fabric. This theory focuses on creating a quantum theory of gravity that is compatible with the principles of quantum mechanics without requiring additional dimensions or the concept of strings. Continuing the theme of the theory of everything, we delve into how quantum mechanics itself is intricately linked to the cosmos. Quantum mechanics, a fundamental theory in physics describing the physical properties of nature at the atomic and subatomic levels, might at first seem distant from the vastness of the cosmos. However, its principles are deeply woven into the fabric of the universe, influencing cosmic evolution and structure to a significant extent. At the heart of quantum mechanics are the principles of uncertainty and superposition, which dictate that particles can exist in multiple states simultaneously until they are observed, challenging our classical notions of reality. These principles apply not only to the behavior of particles in the laboratory, they are also vital to understanding processes occurring on cosmic scales. For example, nuclear fusion, which powers stars, including our Sun, is governed by quantum tunneling, a phenomenon that allows particles to pass through energy barriers. Without this quantum effect, stars would not ignite, and the universe as we know it, filled with light and life, would not exist. Quantum mechanics also plays a crucial role in the early universe. Immediately after the Big Bang, the universe was a hot, dense plasma where quantum fluctuations, tiny variations in energy occurred. These fluctuations, amplified by cosmic inflation, became the seeds for the large-scale structure of the universe, leading to the formation of galaxies and clusters of galaxies. The distribution of matter throughout the universe, from the cosmic microwave background to the cosmic web of galaxies, bears the imprint of these initial quantum ripples. Moreover, quantum mechanics is key to understanding black holes, those enigmatic points where gravity is so strong that even light cannot escape. Stephen Hawking's work on black holes showed that due to quantum effects near the event horizon, black holes can emit radiation known as Hawking radiation. This discovery bridges the gap between quantum mechanics and general relativity, offering insights into how quantum principles apply under conditions of extreme gravity. The intriguing concept of dark matter, which holds galaxies together but does not emit light, also invites quantum explanations. Several hypothetical particles that could make up dark matter, such as WIMPs, weakly interacting massive particles, or axions, arise from theories extending the standard model of particle physics, which is grounded in quantum mechanics. The search for these particles involves understanding their quantum properties and how they interact with the gravitational forces shaping the cosmos. On our journey through the realms of quantum mechanics and the cosmos, we naturally come to a question that has captured human imagination across ages and cultures: is time travel theoretically possible? Within the framework of modern physics, the concept of time travel is not merely a product of science fiction, but a serious scientific inquiry intersecting with our understanding of the fundamental laws of the universe. The theory of relativity, developed by Albert Einstein, provides the most significant theoretical foundation for considering time travel. According to general relativity, the fabric of space-time is curved by mass and energy, and this curvature dictates how objects move through space and time. Remarkably, the equations of general relativity allow solutions where space-time curves back on itself, forming loops known as closed-time-like curves. These structures theoretically permit a path from a point in space-time back to the past or future, and then back to the starting point, suggesting the possibility of time travel. One hypothetical structure that could allow such time travel is a wormhole, a bridge or tunnel through space-time connecting distant parts of the universe or different times. If a wormhole could be stabilized with exotic matter possessing negative energy density, it could theoretically be traversable, allowing for time travel. However, the existence of stable wormholes and exotic matter has not been proven, and the practical challenges of creating or finding a wormhole, let alone traveling through it, remain immense. Another concept related to time travel arises from the idea of cosmic strings, hypothetical defects in space-time left over from the early universe. If two cosmic strings passed close to each other, or if one cosmic string moved in a loop at a significant fraction of the speed of light, they could theoretically create conditions for time travel into the past. Despite these tantalizing theoretical possibilities, time travel faces numerous scientific and philosophical challenges. One of them is the paradoxes associated with time travel, such as the grandfather paradox, where a time traveler could potentially prevent their own existence, raising questions about causality and the nature of time itself. Moreover, the energy scales required to manipulate space-time to achieve time travel are currently beyond human capabilities. Quantum mechanics also enters the discussion of time travel, particularly through the concept of quantum entanglement, which implies a form of communication between particles that is instantaneous and independent of distance. Some interpretations of quantum mechanics suggest that entangled particles are connected by wormholes, hinting at a quantum foundation for space-time structures that could theoretically allow time travel. However, the use of such phenomena for macroscopic time travel remains speculative. Now, let us pose an intriguing question. Could life exist somewhere else in the universe? This question not only explores the limits of our understanding of life, but also touches on deep philosophical aspects of our place in the cosmos. The universe is vast, with billions of galaxies, each containing billions of stars and potentially countless planets. The Kepler Space Telescope and other missions have discovered thousands of exoplanets, planets orbiting stars beyond our solar system, many of which are in the habitable zone, where conditions might be suitable for liquid water, a key ingredient for life as we know it. These discoveries have significantly expanded our understanding of potential habitable places for life, suggesting that conditions for life might be more common than previously thought. The search for extraterrestrial life extends from planets and moons within our solar system to distant exoplanets. Mars, with its past evidence of flowing water and the detection of seasonal methane spikes in its atmosphere, has been a primary target for missions seeking signs of past or present microbial life. Icy moons like Europa and Enceladus, with their subsurface oceans, offer another tantalizing possibility for hosting life, leading to plans for future missions to further explore these alien seas. Beyond our solar system, the study of exoplanets has revealed a rich diversity of worlds, including Earth-like planets that might have conditions suitable for life. The characterization of exoplanet atmospheres, though still in its infancy, aims to detect biosignature gases produced by living organisms that could accumulate in a planet's atmosphere, offering a potential indirect method of detecting life. The search for life also addresses the question of what form life might take elsewhere. Life as we know it is carbon-based, using water as a solvent. However, scientists speculate about the possibility of alternative biochemistries, such as silicon-based life or life existing in environments with solvents other than water, like methane or ammonia. This opens the door to a broader understanding of life that could exist under conditions vastly different from those on Earth. Continuing our journey through the unknown expanses of the cosmos, our next topic brings us closer to home, exploring the tools that serve as our windows into the universe telescopes. These marvels of engineering and science allow us to peer into the vast reaches of space, from neighboring planets to galaxies billions of light years away, aiding our quest to understand whether life exists beyond Earth and to unravel the mysteries of the cosmos. Telescopes work by gathering and focusing light from celestial objects to create an image. The larger the light-gathering area of a telescope, the fainter the objects it can observe and the more details it can reveal. There are two main types of telescopes: refractors and reflectors, each using different mechanisms to collect light. Refracting telescopes use lenses to gather and focus light. The primary lens, called the objective, bends incoming light rays to converge at a focal point where the image is magnified and observed through an eyepiece. Historically significant refracting telescopes were the first to be invented, and Galileo Galilei made groundbreaking astronomical discoveries with one in the early 17th century. Reflecting telescopes, on the other hand, use mirrors instead of lenses. A large curved mirror, known as the primary mirror, reflects light to a focal point. A secondary mirror may then redirect this light to an eyepiece or camera. Reflecting telescopes have several advantages over refractors, including the elimination of chromatic aberration, a distortion seen in refracting telescopes due to lenses dispersing light into different colors, and the ability to build much larger telescopes since mirrors can be supported from the back, reducing sagging and deformation. Beyond these traditional telescopes, technological advances have led to the development of specialized telescopes to observe invisible forms of electromagnetic radiation, such as radio, infrared, ultraviolet, X-ray, and gamma ray. These instruments allow astronomers to explore aspects of the universe invisible to optical telescopes, from cold clouds of dust where new stars are born to the violent high-energy environments around black holes and neutron stars. Radio telescopes, for example, use large antenna dishes to detect radio waves from space, providing unique insights into cosmic phenomena like pulsars, quasars, and the cosmic microwave background radiation. Space telescopes like the Hubble Space Telescope operate above Earth's atmosphere, which absorbs or scatters much of the electromagnetic spectrum, offering an unobstructed view of the universe in optical, ultraviolet, and near-infrared light. Operating telescopes, whether ground-based or space-based, involves not just collecting light but also sophisticated methods of data analysis. Images captured by telescopes are processed and analyzed using computer algorithms, revealing details and structures invisible in raw data. This analysis can include measuring the distance, composition, temperature, and motion of celestial objects, contributing to our understanding of the universe's structure, evolution, and fundamental laws of physics. Let's now turn our attention to a monumental leap in our astronomical capabilities, the James Webb Space Telescope, JWST. Launched into space in late 2021, JWST represents the most complex and powerful space telescope ever built, poised to unveil the universe's secrets with unprecedented clarity and depth. JWST is an international collaboration led by NASA, with significant contributions from the European Space Agency ESA and the Canadian Space Agency CSA. It is designed to observe the universe in the infrared spectrum, allowing it to peer through cosmic dust clouds that obscure the view of optical telescopes and detect faint light from distant stars and galaxies with a primary mirror diameter of 5 meters, JWST has a light-gathering capability more than 6 times greater than that of its predecessor, the Hubble Space Telescope, enabling it to observe objects much further away and therefore much further back in time than ever before. One of JWST's primary goals is to study the edge of the observable universe, aiming to observe the first galaxies formed after the Big Bang more than 13.5 billion years ago. By studying these early galaxies, astronomers hope to learn more about the formation and evolution of the first structures in the universe, shedding light on the processes that led to the complex cosmic web of galaxies we observe today. JWST's infrared capabilities are key to this task, as light from these distant galaxies has been stretched into the infrared spectrum due to the expansion of the universe, a phenomenon known as redshift. In addition to probing the early universe, JWST will also study the atmospheres of exoplanets, potentially identifying signs of habitability or even life. Its powerful instruments can analyze the chemical composition of exoplanet atmospheres, detecting molecules like water vapor, carbon dioxide, and methane that could indicate the presence of biological processes. JWST is also set to unravel the mysteries of star formation and planet formation in our galaxy. By observing molecular clouds where stars are born, the telescope will provide data on the conditions and processes leading to the formation of stars and their planetary systems. This knowledge is crucial not only for understanding the origins of our solar system, but also for comprehending the diversity of planetary systems throughout the galaxy. As JWST begins its mission, it promises to transform our understanding of the universe. Its observations are expected to challenge existing theories, reveal new phenomena, and provide answers to long-standing questions about the nature of the cosmos. From the first light after the Big Bang to the formation of galaxies, stars, and planets, JWST will offer a window into the history and evolution of the universe, bringing us closer than ever to understanding the edge of the universe and our place within it. Over the past few decades, satellites have revolutionized astronomy by providing a vantage point beyond Earth's atmosphere, inaccessible to ground-based observatories. From detailed mapping of the cosmic microwave background to discovering exoplanets and monitoring cosmic phenomena, satellites have opened new windows into the universe, each bringing unique data that deepens our cosmic knowledge. The launch of the Hubble Space Telescope in 1990 marked a turning point in space exploration. Orbiting the Earth, freed from atmospheric distortions, Hubble has captured images of unparalleled clarity, revealing the dynamic and detailed structure of the universe. Its observations have led to breakthroughs in our understanding of black holes, the age of the universe, the existence of dark energy, and the processes governing the life cycles of stars. Hubble's deep-field images, showing galaxies billions of light-years away, have provided a glimpse into the early stages of the universe, illustrating the evolution of galaxies over time. Another significant satellite, launched in 1989, was the Cosmic Background Explorer, COBE, which mapped the cosmic microwave background radiation, the afterglow of the Big Bang. COBE's measurements provided compelling evidence for the Big Bang theory, showing that the background radiation of the universe is remarkably uniform, with slight variations supporting models of cosmic inflation. This discovery was pivotal, earning the 2006 Nobel Prize in Physics. Following COBE, the Wilkinson Microwave Anisotropy Probe WMAP, and later the Planck satellite refined measurements of the cosmic microwave background, creating maps of unprecedented precision. These observations help to precisely determine the age of the universe, its composition, and its rate of expansion, contributing to the standard model of cosmology describing the universe as flat and dominated by dark energy and dark matter. Satellites have also played a crucial role in the search for exoplanets. The Kepler Space Telescope, launched in 2009, was specifically designed to detect Earth-like planets in the habitable zones of their stars, where conditions might allow for liquid water. Kepler discovered thousands of exoplanets, showing that our galaxy is teeming with a diversity of worlds, many challenging our understanding of planet formation and the potential for life beyond Earth. Additionally, satellites dedicated to observing the Sun, such as the Solar Dynamics Observatory SDO, have provided detailed data on solar activity, including sunspots, flares, and coronal mass ejections. These observations are crucial for understanding the Sun's impact on space weather and its effects on Earth's environment. Continuing the theme, how do scientists use data from telescopes to study distant objects? When light or other forms of electromagnetic radiation from distant objects reach a telescope, whether orbiting Earth or ground-based, it is first collected by the telescope's main mirror or lens. This light is then focused to form an image or directed into instruments such as spectrometers, which split the light into its component wavelengths. Analyzing this light at various wavelengths is fundamental to studying the properties and behavior of celestial objects millions to billions of light years away. One key method used by scientists is spectroscopy, which involves studying the spectrum of light emitted, absorbed, or reflected by objects. Each chemical element leaves a unique fingerprint in the spectrum of light, allowing scientists to determine the composition of stars, galaxies, and nebulae. Spectroscopy can reveal not only what distant objects are made of, but also their temperatures, densities, and velocities towards or away from us, indicated by red or blue shifts in their spectral lines. Photometry, another crucial method, measures the intensity of light from an object at various wavelengths. By analyzing how bright an object appears and how its brightness changes over time, astronomers can infer its size, luminosity, distance, and even the presence of planets transiting in front of stars. Variations in brightness can also indicate other dynamic processes, such as the pulsation of stars or eclipsing binary stars. Data collected by telescopes often require sophisticated processing and analysis using advanced algorithms and computational models. This process includes correcting for distortions caused by Earth's atmosphere, instrument noise, and other interference sources. The advent of digital imaging and advances in computing technology have significantly increased the volume and quality of data that can be collected and analyzed, enabling discoveries that were impossible just a few decades ago. Astronomers also use the method of parallax to measure the distance to nearby stars. By observing how the position of a star shifts relative to the background of more distant stars as Earth orbits the Sun, scientists can calculate its distance from us. This fundamental measurement helps build the cosmic distance ladder, which is used to determine the distances to much more remote objects in the universe. As we delve deeper into space through the lenses of powerful telescopes, astronomers face numerous challenges in their quest to observe distant galaxies. These challenges are linked to the vast distances, the complexity of data acquisition, and the limitations of current technologies and methods. Overcoming these difficulties is essential for advancing our understanding of the structure of the universe, its evolution, and the fundamental processes that shape it. One of the main challenges is the immense distance to these distant galaxies, which are millions and billions of light years away from us. At such distances, the light reaching Earth is incredibly faint, making these galaxies difficult to detect and study. The expansion of the universe adds to this problem, as it causes the light from distant galaxies to stretch into longer, redder wavelengths, a phenomenon known as redshift. As a result, much of the light from these galaxies falls outside the visible spectrum and must be observed using infrared and radio telescopes. Atmospheric interference is another significant barrier for ground-based telescopes. Earth's atmosphere can distort and absorb light from distant celestial objects, making them appear blurry and reducing the amount of information that can be gathered. While space telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope are not subject to atmospheric interference, they are extremely complex and costly to build and launch, limiting the number of such missions that can be undertaken. Additionally, the finite speed of light imposes a fundamental limit on our ability to observe the universe in real time. Observing distant galaxies is like looking back in time, as we see them as they were millions or billions of years ago, depending on their distance. While this allows astronomers to study the history of the universe, it also means that we cannot know the current state of these distant galaxies, complicating our understanding of cosmic evolution. Another challenge is the enormous volume of data generated by modern telescopes, requiring sophisticated software and algorithms for processing and analysis. Extracting meaningful information from this data, such as the properties of galaxies, the distribution of dark matter, and the rate of cosmic expansion, demands significant computational resources and advanced data analysis methods. Interference from cosmic objects closer to home can also hinder the observation of distant galaxies. Light from stars in our own galaxy, as well as interstellar dust, can obscure the view of more distant objects, requiring astronomers to develop techniques for filtering out this background noise and isolating the light from target galaxies. Despite these difficulties, astronomers continue to make significant advances in observing distant galaxies through technological innovations, the development of more sensitive detectors, and the launch of new telescopes capable of observing the universe in various wavelengths. These efforts are gradually peeling back the layers of the universe, revealing the intricate dance of galaxies across cosmic time and space, bringing us closer to understanding the grand scale of the cosmos. Transitioning to our next chapter, we journey back in time to the very beginning, the Big Bang. This monumental event marks the origin of the universe as we know it, an explosion from which all space, time, matter, and energy emerged around 8 billion years ago. Unlike an explosion in space, the Big Bang was a rapid expansion of space itself, setting the stage for the evolution of the cosmos from a hot, dense state to the vast, cooler space filled with galaxies, stars, planets, and life that we observe today. The Big Bang theory is supported by a wealth of evidence, making it the leading explanation for the origin of the universe. One of the most compelling pieces of evidence is the cosmic microwave background CMB radiation, a faint glow permeating the universe, accidentally discovered in 1965 by Arno Penzias and Robert Wilson. This discovery provided a direct snapshot of the infant universe. The residual radiation from around 380,000 years after the Big Bang, when the cosmos had cooled enough for photons to travel freely through space. The uniformity and slight variations in the CMB align with the predictions of the Big Bang theory, providing a window into the conditions of the early universe. Another pillar supporting the Big Bang theory is the observation of the universe's expansion. Edwin Hubble's observations in the 1920s, showing that galaxies are moving away from each other, revealed that the universe is not static but expanding. This expansion, when traced backward, suggests that the universe must have originated from a single, small, dense point. The Big Bang theory explains this expansion and predicts that the farther away a galaxy is, the faster it is moving away from us, a relationship known as Hubble's law, which has been confirmed by subsequent observations. The theory also successfully explains the abundance of light elements such as hydrogen, helium, and lithium. Nuclear reactions in the first few minutes after the Big Bang likely produced these elements in proportions that closely match what we observe today in the universe. This nucleosynthesis, the process of forming new atomic nuclei from pre-existing matter, provides a crucial test for the Big Bang theory, further strengthening its status as a cornerstone of modern cosmology. Despite its success, the Big Bang theory also opens up new questions and mysteries, such as the nature of dark matter and dark energy, which seem to dominate the mass energy content of the universe and the cause of the initial expansion of the universe. Additionally, the theory does not explain what preceded the Big Bang or what caused it, leaving room for further theoretical development and discovery. From the momentous event of the Big Bang, the universe embarked on a complex journey of evolution, transitioning from a hot, dense state to the vast, structured cosmos filled with galaxies, stars, and planets that we observe today. This evolution represents a story of cosmic expansion, cooling, and the continuous work of gravity binding the fabric of the universe over billions of years. In the immediate aftermath of the Big Bang, the universe was a seething cauldron of particles and radiation too hot and dense for atoms to form. During this period, known as the Planck epoch, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were unified. As the universe expanded, it rapidly cooled, allowing these forces to separate and the first subatomic particles, including protons, neutrons, and electrons, to emerge. About 380,000 years after the Big Bang, the the universe cooled enough for electrons to combine with protons to form neutral hydrogen atoms, a process known as recombination. This epoch marked the transition of the universe from opacity to transparency, allowing photons to travel freely through space for the first time, creating the cosmic microwave background radiation, a snapshot of the infant universe that we can still observe today. Over the next few 100 million years, the universe entered the cosmic dark ages, a period before the first stars ignited. During this time, gravity began to pull together the first clouds of gas and dark matter, forming the seeds of future galaxies. The end of the Dark Ages came with the formation of the first stars, whose nuclear furnaces lit up the universe again. These first generations of stars were massive and short-lived, dying in spectacular supernovae that seeded the cosmos with heavier elements necessary for the formation of planets and life. Galaxies began to form from the gravitational collapse of dark matter halos, drawing in gas and dust. Within these galaxies, new generations of stars were born, surrounded by disks of material that coalesced into planets, asteroids, and comets. Over time, galaxies grew through mergers and accretions, creating the diverse galactic structures from spirals to ellipticals that we observe today. As the universe continued to expand and cool, the rate of star formation eventually slowed, leading to the current era, where the formation of new stars balances the death of old ones. The discovery of dark energy, a mysterious force accelerating the expansion of the universe, adds another layer to our understanding of cosmic evolution, suggesting a future where galaxies become increasingly isolated from each other. Today, the universe represents a vast web of galaxies, each a massive island universe in its own right, separated by voids and connected by filaments of dark matter. This intricate structure, from the smallest planetary systems to the largest galactic clusters, is the result of nearly 14 billion years of cosmic evolution, a testament to the power of the physical laws shaping the universe from the simplicity of the Big Bang to the complex tapestry we observe now. The fate of the universe is a topic of intense scientific investigation and speculation, intertwined with the laws of physics as we understand them, and the critical components shaping cosmic evolution, dark matter, dark energy, and the fundamental forces of nature. The future of the universe largely depends on the properties and behavior of dark energy, the mysterious force driving the acceleration of the universe's expansion. If dark energy continues to dominate the cosmic landscape as current observations suggest, the universe will keep expanding at an accelerating rate. In this scenario, galaxies beyond our local group will recede from us ever faster, eventually disappearing beyond the cosmic horizon, becoming invisible to us due to the finite speed of light. The universe will become increasingly cold and empty, approaching a state known as the Big Freeze or heat death, where it reaches maximum entropy and no meaningful energy exchanges occur, marking the end of all astronomical processes and possibly the universe itself. Another possibility, although less supported by current observations, is the Big Crunch. If dark energy were to wane over time, or if the universe contained enough matter to reverse the expansion through gravitational pull, all matter and space could eventually collapse back into a singularity, possibly leading to another Big Bang and a cyclic model of the universe. However, the overwhelming evidence for the accelerating expansion of the universe makes the Big Crunch a less likely outcome based on our current understanding. A more speculative outcome is the Big Rip, which depends on a particular form of dark energy that increases in strength over time. In this scenario, the repulsive force of dark energy would become so dominant that it would tear apart galaxies, stars, planets, and eventually even atoms, leading to a universe in which no structures can exist. In addition to these cosmological scenarios, the future of stars, galaxies, and black holes unfolds on immense timescales. Stars will continue to form for trillions of years until the gas in galaxies is exhausted. Eventually, existing stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. Galaxies will evolve, merging and consuming smaller galaxies while their stellar populations age. Over time, even black holes are expected to evaporate through the process of Hawking radiation, leaving the universe filled with low-energy photons and subatomic particles. These visions of the future of the universe are extrapolations based on our best theoretical models and observations. As our understanding of dark energy, dark matter, and the fundamental laws of the universe deepens, our predictions may change. The study of cosmology remains a dynamic field where each discovery has the potential to alter our perspective on the past, present, and future of the universe. Continuing our cosmic journey, we turn our gaze closer to home, to the fate of our own galaxy, the Milky Way. This majestic spiral galaxy, teeming with stars, planets, and nebulae, is on a path that is both awe-inspiring and inevitable, shaped by the same cosmic forces that govern the universe as a whole. The Milky Way is currently on a collision course with our nearest galactic neighbor, the Andromeda Galaxy M31. Astronomical observations and simulations predict that in about 4 billion years, the Milky Way and Andromeda will engage in a titanic merger. This event, far from being a catastrophic collision, will be a gradual process taking hundreds of millions of years. The vast distances between stars mean that direct stellar collisions are unlikely instead. The gravitational forces between the two galaxies will drastically alter their structures, ultimately forming a single, larger elliptical galaxy, often referred to as Milkomeda or Milkdromeda. During this galactic merger, gas and dust clouds in both galaxies will interact, triggering a spectacular burst of star formation. Some regions will become denser, forming new star clusters, while other regions may be flung out, contributing to the formation of tidal tails, elongated streams of stars and gas pulled out from the galaxies. Meanwhile, the supermassive black holes at the centers of each galaxy will gradually spiral toward each other, eventually merging into an even more massive black hole. The fate of the solar system in this cosmic dance remains uncertain. The Sun and its planets may be flung into a new region of the resulting galaxy, possibly much farther from the galactic core, or they may remain relatively unscathed in a similar orbit to the current one. However, by the time the Milky Way and Andromeda begin their merger, the Sun will have already entered the final stages of its life cycle, expanding into a red giant and then shedding its outer layers, leaving behind a cooling white dwarf. In the further future, the fate of Milkomeda will be shaped by the same dark energy driving the expansion of the universe. As galaxies beyond the local supercluster recede from us ever faster, Milkomeda will become increasingly isolated in a universe where distant galaxies drift beyond detectable horizons. Over trillions of years, star formation will cease as available gas is depleted or ejected, leaving a galaxy populated by aging stars, white dwarfs, neutron stars, and black holes. In this grand cosmic narrative, the fate of the Milky Way is a testament to the dynamic and ever-changing nature of the universe. Galaxies are not static islands in space, but rather living, evolving entities that merge, form new structures, and give birth to stars and perhaps life. Expanding the narrative of the Milky Way's inevitable merger with the Andromeda Galaxy, let us delve into the cosmic dance of colliding and merging galaxies, a fundamental process that shapes the structure and evolution of the universe. This phenomenon, which might evoke images of cataclysmic collisions, unfolds over vast timescales and distances governed by the relentless force of gravity. Galactic collisions are a natural consequence of the gravitational attraction between galaxies in close proximity to each other. As galaxies drift through space, their mutual gravitational forces can draw them together. Despite the enormous distances between stars within galaxies, when two galaxies begin to interact, it is not the stars that collide, given the vast space between them, but rather the gravitational forces that significantly alter the structures of the galaxies. The initial stage of a galactic merger involves the interaction of the outer halos of the galaxies, composed of dark matter, stars, and gas. These halos exert gravitational forces on each other, causing tidal forces that can distort the shapes of the galaxies, pulling out streams of stars and gas. This process can trigger bursts of star formation as gas clouds in the spiral arms of the galaxies compress. As the galaxies draw closer, their gravitational interaction becomes more intense. The galaxies may pass through each other, their gravitational fields mingling their inner structures and leading to further bursts of star formation. Over time, the mutual gravity of the galaxies slows their relative motion, causing them to oscillate back and forth, gradually losing energy with each pass. During these encounters, supermassive black holes, if present, will begin to influence the merger process. These black holes will eventually migrate to the center of the resulting galaxy, spiraling ever closer until they merge, releasing immense amounts of energy and potentially producing jets of high-energy particles. The final stage of the merger results in the galaxies coalescing into a single entity. Depending on the initial masses, sizes, and gas content of the galaxies, the resulting galaxy can take on various forms, from elliptical galaxies, which are more rounded and contain less gas and dust, to larger spiral galaxies if enough angular momentum is retained. Throughout the process, dark matter plays a crucial role, both in pulling the galaxies together and in the dynamics of the merger. The distribution of dark matter around galaxies helps guide their movement and interaction, influencing the ultimate outcome of the merger. Galactic mergers are not isolated events, but part of the natural evolution of the universe. They contribute to the growth of galaxies, influence star formation, and play a part in the complex interplay of processes shaping the cosmic landscape. Observations of colliding and merging galaxies across the universe not only provide spectacular images, but also offer critical insights into the life cycle of galaxies, the behavior of dark matter, and the gravitational forces orchestrating the cosmos. Entering our next chapter, we dive into a more philosophical realm, contemplating a question that intertwines science, ethics, and philosophy. Should we attempt to contact extraterrestrial life? This question touches on both the spirit of human exploration and curiosity, which has driven us to explore the night sky, send spacecraft to distant planets, and scan the cosmos for signals from other civilizations, and the profound uncertainties regarding the nature of extraterrestrial life and the potential consequences of making contact. The search for extraterrestrial intelligence SETI has been an ongoing scientific endeavor for decades, using radio telescopes to listen for signals that might indicate the presence of intelligent life beyond Earth. Some initiatives have even sent messages into space, seeking to inform potential extraterrestrial civilizations of our existence. These efforts are based on the hope that we are not alone in the universe, and that the discovery of other intelligent life would be one of humanity's most profound achievements, offering unparalleled insights into the nature of life, intelligence, and our place in the cosmos. However, the question of whether we should actively attempt to contact extraterrestrial life is a subject of considerable debate. One argument in favor of contact is that it could lead to an exchange of knowledge and culture, enriching our understanding of the universe and ourselves. The potential for scientific and technological advancements is enormous, possibly offering solutions to problems we face on Earth or opening new avenues of exploration in the laws of physics, biology, and the nature of consciousness. On the other hand, there are significant concerns and risks associated with attempting to contact extraterrestrial civilizations. The history of human exploration and colonization on Earth provides cautionary examples of encounters between civilizations with different levels of technology and understanding, often leading to the exploitation or destruction of the less technologically advanced societies. The possibility that extraterrestrial civilizations might be far more advanced than us raises questions about their intentions and how they might perceive or interact with us. Moreover, the diversity of life on Earth suggests that extraterrestrial life might be vastly different from us, not only biologically, but also in their perceptions, values, and methods of communication. These differences raise ethical considerations about the right to establish contact without global consensus and the potential impact on humanity and Earth's biosphere. Philosophical considerations also play a crucial role in this debate. The act of reaching out to the cosmos is a reflection of our quest to understand our existential questions and find our place in the universe. However, it also requires us to consider the responsibility associated with such an endeavor, contemplating the consequences not only for our species, but also for any other beings we might encounter. As we reflect on whether we should attempt to contact extraterrestrial life, we face the necessity of balancing our innate curiosity and desire for knowledge with a careful consideration of potential risks and ethical dilemmas. This question invites interdisciplinary dialogue, encompassing not only scientific and technological aspects, but also philosophical, ethical, and social dimensions. Delving further into this topic, we encounter the profound impact of the vastness of the universe on our philosophical worldview. This immense expanse, filled with billions of galaxies, each containing billions of stars and potentially countless planets, stretches our imagination and challenges our understanding of existence, prompting us to reconsider human significance, the nature of life, and our search for meaning. The realization of the universe's vastness underscores our physical insignificance on the cosmic scale. Earth is but a speck in the galactic neighborhood, which itself is a tiny part of the observable universe. This perspective can evoke a sense of humility, highlighting the fragility and preciousness of life on our planet. It emphasizes the remarkable coincidence of conditions that allowed life to flourish here, in stark contrast to the seemingly inhospitable vastness of space. At the same time, the immensity and complexity of the universe inspire awe and wonder, fueling our innate curiosity and driving scientific and philosophical exploration. The quest to understand the cosmos stands as a testament to the resilience of the human spirit and our unquenchable thirst for knowledge. It challenges us to expand the boundaries of our cognitive and technological capabilities, striving not only to uncover the mysteries of the universe, but also to explore the depths of human consciousness and the limits of the mind. The possibility of other forms of life, perhaps on countless worlds scattered across distant galaxies, prompts us to ponder the universality of concepts like consciousness, morality, and the search for meaning. It raises questions about the potential for communication and mutual understanding between vastly different forms of life and the implications for our concepts of ethics, rights, and the interconnectedness of all beings. The discovery of extraterrestrial life would not only revolutionize our scientific understanding, but also fundamentally alter our philosophical and ethical frameworks, challenging anthropocentric views and expanding our notion of the community of life. On a more existential level, the vastness of the universe confronts us with the temporal and spatial limits of our existence. It prompts us to reflect on the beginning and end of the universe, the nature of time, and our place in this grand continuum. The realization that the universe existed for billions of years before us and will continue to exist long after we are gone can evoke a search for meaning and purpose that transcends individual lives, leading to reflections on legacy, memory, and the impact of our actions on future generations and the cosmos itself. So, how do we balance the costs of space exploration with the needs of Earth? This question sits at the heart of our ambitions to venture beyond our planet, challenging us to weigh the boundless potential of space discoveries against the immediate and tangible needs of our home world. It encompasses a broader debate about resource allocation, societal priorities, and the long-term vision for the future of humanity. Space exploration, from sending humans to the Moon and Mars to launching telescopes that gaze into the farthest reaches of the universe, requires significant financial investment, technological resources, and human capital. The pursuit of understanding the cosmos, searching for extraterrestrial life, and potentially colonizing other planets is inspiring and pushes the boundaries of human potential. It brings technological advancements, scientific breakthroughs, and deeper insights into our place in the universe, benefits that can ripple through society in unexpected and transformative ways. However, Earth faces pressing challenges such as climate change, poverty, disease, and resource scarcity that demand immediate attention and resources. Balancing investments in space exploration with these urgent issues on Earth raises ethical and practical considerations. It requires a critical examination of how we prioritize funding and resources, ensuring that our quest for the stars does not overshadow our commitments to our planet and its inhabitants. Balancing these seemingly competing interests requires a nuanced and forward-thinking approach. It involves recognizing that investments in space exploration and addressing Earth's challenges are not mutually exclusive, but can be complementary. Technological innovations developed for space missions, such as satellite communications, GPS technology, and advances in material science, have found critical applications on Earth, enhancing environmental monitoring, disaster response, and everyday conveniences. Moreover, space exploration can contribute to solving Earth's challenges. Studying other planets, especially Mars and Venus, provides insights into climate change and environmental degradation, offering valuable lessons for managing Earth's ecosystems. The search for extraterrestrial life underscores the uniqueness and fragility of our biosphere, highlighting the importance of preserving Earth's biodiversity. A sustainable approach to space exploration also involves international cooperation, sharing the financial burden and rewards of discoveries among nations. Joint space missions can unite humanity in a common goal, transcending geopolitical boundaries and fostering a global community that values both exploration and stewardship of our home planet. Furthermore, engaging the public and fostering a culture that values science, education, and exploration can create broad support for space missions while promoting responsible management of Earth's resources. Partnerships between public and private organizations in space ventures can also alleviate financial pressure on governments, allowing innovative funding models to support both space exploration and Earth sustainability. As we enter the final chapter of this documentary, we look to the future, our own future, and delve into one of the most exciting quests of modern science. How close are we to discovering life on other planets? This question lies at the intersection of multiple scientific disciplines, including astronomy, biology, and planetary science, and resonates deeply with our innate curiosity about whether we are alone in the universe. The search for extraterrestrial life has made significant strides in recent decades, driven by remarkable technological advancements and a better understanding of where to look for signs of life. At the heart of this search are exoplanets, planets orbiting stars beyond our solar system, some of which are located in the habitable zone, the range of distances from a star where liquid water could exist on a planet's surface. Thanks to missions like the Kepler Space Telescope and the Transiting Exoplanet Survey satellite TESS, we have identified thousands of exoplanets, a small but promising number of which are Earth-like and situated in their star's habitable zone. These discoveries provide a catalogue of worlds where life, as we know it, has the highest chances of thriving. The upcoming James Webb Space Telescope JWST is poised to revolutionize our search for life beyond Earth. With its unparalleled sensitivity to infrared light, JWST will be able to study the atmospheres of exoplanets in detail, searching for chemical signatures of life such as oxygen, methane, and water vapor. These molecules, especially when found together, could indicate the presence of biological processes. Meanwhile, missions within our solar system offer another avenue for the search for life. Mars, with its past evidence of water, remains a prime candidate, and both NASA's Perseverance rover and the European Space Agency's ExoMars rover are equipped to search for signs of past or present life. Additionally, the icy moons of Jupiter Europa and Saturn Enceladus and Titan harbor subsurface oceans that could provide suitable conditions for life, and missions like Europa Clipper and the proposed Enceladus Life Finder aim to explore these alien seas. Despite these advancements, the discovery of life beyond Earth remains elusive. The main challenge lies in the vast distances separating us from potentially habitable worlds, making direct exploration a distant possibility. Moreover, our search is limited by our understanding of life, which is based solely on Earth biology. Life on other planets might take forms vastly different from what we know, requiring us to expand our definitions and detection methods. As we contemplate the future of our cosmic exploration and the thrilling possibility of discovering life on other planets, our journey is intrinsically linked to technological advancements. These advancements will not only enhance our current capabilities, but also open new realms of exploration and understanding. The pursuit of further exploring the universe requires innovations in a multitude of areas, from propulsion systems that could take us to distant worlds to instruments that can unravel the secrets of the cosmos with unprecedented clarity. A critical area of development is propulsion technology. current methods of spacecraft propulsion are limited in the speeds they can achieve, making interstellar travel impractical within human lifespans. Concepts such as ion drives, nuclear thermal propulsion, and even theoretical ideas like antimatter engines and warp drives represent the cutting edge of research that might one day enable us to reach other star systems. Moreover, the potential of light sail technology, driven by laser beams to achieve significant fractions of the speed of light, offers a tantalizing glimpse into a future where interstellar probes could be sent to nearby star systems. Another crucial technological frontier lies in telescopes and observational technologies. The James Webb Space Telescope represents a giant leap forward, but the future holds even greater promise. Extremely large telescopes, both in space and on Earth, equipped with advanced adaptive optics to correct for atmospheric distortions, could directly image exoplanets, potentially capturing their surfaces. Additionally, the development of more sensitive detectors and the use of interferometry, where light collected by multiple telescopes is combined to enhance resolution, could allow us to study the chemical compositions of distant planetary atmospheres in search of biosignatures. Robotics and automation will also play a crucial role in the future of space exploration. As missions venture farther into the solar system and beyond, the need for autonomous spacecraft capable of making decisions in real time without waiting for instructions from Earth becomes increasingly important. Advances in artificial intelligence and machine learning will enhance the autonomy of probes and rovers, enabling them to navigate complex environments, conduct scientific experiments, and adapt to unforeseen conditions. Furthermore, the miniaturization of technologies and the development of CubeSats and nanosatellites open new possibilities for space exploration. These small, cost-effective platforms can be deployed in large numbers to study cosmic phenomena, monitor asteroids, and even serve as communication relays for interplanetary missions. Finally, the sustainability of space exploration requires advancements in life support and habitation technologies. Long-term missions to Mars and beyond will require closed-loop life support systems that recycle air, water, and waste, as well as advanced habitats that protect astronauts from cosmic radiation and extreme temperatures. The development of in situ resource utilization (ISRU) methods, which involve extracting and using resources from Martian soil or asteroids, will be crucial for establishing sustainable extraterrestrial colonies. The question that resonates with both scientific curiosity and profound philosophical implications is, what message would humanity choose to send to an extraterrestrial civilization? This question not only contemplates the practical aspects of interstellar communication, but also reflects the essence of our identity, our achievements, and our aspirations as a species. Crafting a message for extraterrestrial beings is an exercise in distilling the vast and diverse experience of human existence into a form that can be understood across cosmic distances. It requires us to think about what aspects of our world we want to share and what universal truths we might convey. The content of such a message must transcend not only interstellar space, but also the potentially vast differences in perception, cognition, and culture. A fundamental element of our message could be the mathematics and physical laws that govern the universe, as these are likely to be universal constants. Descriptions of fundamental mathematical concepts, the structure of the atom, and the principles of light and energy could serve as a common foundation for establishing communication. Visual representations of these concepts, along with binary sequences or other forms of universal coding, could provide a basis for mutual understanding. Beyond the scientific, the message should reflect the diversity and richness of life on Earth. This could include images or descriptions of our planet's biosphere, from the microscopic world of cells and DNA to the vast landscapes and oceans and the myriad forms of life that inhabit them. Such a depiction would offer a glimpse into the complexity and beauty of life as it has evolved on our world. Music and art, as expressions of human creativity and emotion, could serve as ambassadors of our cultural heritage. Selected works that evoke a wide range of emotions and ideas could transcend language barriers and offer a sense of the human spirit. Similarly, greetings in multiple languages, along with expressions of peace and the desire for friendship, could convey our social nature and hope for peaceful exchange. The philosophical and ethical principles that guide human societies, as well as our aspirations for the future, would also form an important part of our message. This might include our pursuit of knowledge, our dreams of exploration and understanding, and our commitment to caring for our planet and supporting the life it sustains. Reflecting on a message to extraterrestrial civilization also prompts us to reflect on ourselves, the values that define us, and the legacy we wish to share with the cosmos. It is a declaration of our existence, a testament to our journey through time and space, and an invitation to connect across the vast stellar expanse. Concluding our journey through the cosmos, from the fiery birth of the universe in the Big Bang to the unknown beyond our universe, we stand at a profound intersection of knowledge and imagination. This journey has not only illuminated the depths of space and time, but also shed light on our own existence, our planet, and the shared destiny that binds us to the cosmos. Through our telescopes, satellites, and probes, we have begun to unravel the grand narrative of the universe, discovering the fundamental laws that govern its expanse and the myriad phenomena that populate it. We have glimpsed the possibility of life beyond Earth, raising questions about our uniqueness and the potential for communication with other intelligent beings. The technological leaps envisioned for the future promise to deepen our understanding and extend our reach into the galaxy and perhaps beyond. Yet with each discovery come new questions. The universe, with its dark matter and dark energy, its billions of galaxies and potential multiverses, remains a vast, largely unexplored territory that challenges our deepest scientific and philosophical inquiries. The possibility of life elsewhere redefines our search for meaning and our place in the cosmic fabric. As we conclude our journey, we are left with a sense of awe at the immensity of the universe and a hope for the future, pondering the next chapter in the story of humanity. A chapter yet to be written, filled with mysteries and adventures. What do you think lies beyond our universe? Subscribe and leave your comments below. Thank you for watching. The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself, Carl Sagan. The universe we live in is incredibly vast and mysterious. Our galaxy, brimming with innumerable enigmas and marvels beyond our wildest dreams, emerged from seemingly nothing. It is just one among countless galaxies, potentially numbering in the hundreds of millions, that have yet to be discovered. These galaxies, like islands in the boundless ocean of space, float in the void, each harboring its own secrets. Each galaxy is unique, but they all share a common and still unresolved question. How did they form from apparent nothingness? Scientists propose that the birth of galaxies involves a complex process, including gravitational attraction, dark matter, and numerous other factors. Yet, even with all the modern advancements in astronomy and cosmology, this process remains one of the greatest mysteries. Contemporary telescopes and research missions continue to gather data and seek answers to these questions. Every new discovery, whether it's the detection of a new galaxy or the study of processes in known ones, brings us closer to unraveling the mystery of their origin. However, the path to fully understanding this phenomenon is still long, and perhaps this is the true beauty of science, the eternal pursuit of knowledge and the unraveling of the universe's mysteries. The universe, a perpetually expanding amalgamation of galaxies, stars, planets, and myriad forms of matter and energy, presents a profound mystery that has captivated humanity for centuries. Central to modern cosmology is the understanding that the universe began approximately 8 billion years ago with the Big Bang, a colossal explosion that marked the inception of everything we know. This event set in motion the expansion of space, creating the cosmic web we observe today. Scientists have unraveled much about the universe's composition, revealing that ordinary matter, the substance making up stars, planets, and us, constitutes a mere 5% of the universe's total mass and energy. The remaining 95% comprises dark matter and dark energy, invisible forces that govern the universe's structure and expansion, yet elude direct detection. The universe's vastness is almost beyond comprehension, stretching over billions of light-years across. This immensity houses an estimated 2 trillion galaxies, each a collection of billions of stars and untold planets, offering a humbling perspective on our place in the cosmos. The laws of physics, consistent throughout the universe, govern the motion of galaxies, the life cycle of stars, and the intricate dance of particles at the quantum level. These laws have allowed scientists to predict cosmic phenomena with astonishing accuracy, from the paths of planets to the behavior of black holes, those enigmatic entities whose gravitational pull is so strong that not even light can escape. In this cosmic journey, the role of dark energy in accelerating the universe's expansion poses a tantalizing puzzle. Discovered through observations of distant supernovae, dark energy works against the gravitational pull of matter, driving galaxies apart at an accelerating rate. This discovery has profound implications for the universe's fate, suggesting a future in which galaxies drift ever farther apart, leading to a cold, dilute cosmos. The Big Bang Theory. The Big Bang Theory stands as a cornerstone of modern cosmology, offering a compelling explanation for the origin and evolution of the universe. It posits that the universe began as an extremely hot and dense point approximately 13.8 billion years ago and has been expanding ever since. This theory is supported by a wealth of scientific evidence, including the observation of the cosmic microwave background radiation, a faint glow left over from the early universe, which provides a snapshot of the cosmos just 380,000 years after the Big Bang. This radiation, discovered accidentally by Arno Penzias and Robert Wilson in 1965, has a uniform temperature throughout the universe, confirming predictions of the Big Bang Theory and offering concrete evidence of the universe's hot, dense origin. Another pillar supporting the Big Bang Theory is the observation of the redshift of galaxies, indicating that they are moving away from us and, by implication, from each other. This discovery, made by Edwin Hubble in the 1920s, revealed that the universe is not static but expanding. The farther away a galaxy is, the faster it appears to be moving away from us, a relationship now known as Hubble's law. This expansion is a key prediction of the Big Bang Theory and suggests that the universe was once much smaller, hotter, and denser than it is today. Moreover, the theory elegantly explains the relative abundances of light elements, such as hydrogen, helium, and lithium observed in the universe. According to Big Bang nucleosynthesis, these elements were formed in the first few minutes after the Big Bang, as the universe cooled enough for protons and neutrons to combine into nuclei. The predicted abundances of these elements closely match observations, lending further credence to the Big Bang Theory. Despite its widespread acceptance, the Big Bang Theory also raises profound questions and puzzles. For instance, it does not explain what preceded the Big Bang or what lies outside the observable universe. It also introduces the concept of cosmic inflation, a rapid expansion of the universe that occurred fractions of a second after the Big Bang, to solve the horizon and flatness problems. This inflationary period predicts that the universe should appear flat and uniform on large scales, which is consistent with observations of the cosmic microwave background radiation. Our early universe. Following the Big Bang, the universe embarked on a monumental journey of expansion, transforming from an infinitesimally small point to the vast cosmos we observe today. This expansion can be likened to a balloon being inflated, where galaxies move away from each other as the space between them grows. In the earliest moments, the universe was a hot, dense soup of particles and radiation, too energetic and chaotic for atoms to form. As it expanded, this primordial fireball cooled, allowing quarks to combine into protons and neutrons, which then formed the simplest nuclei, predominantly hydrogen and helium, through the process of nucleosynthesis. This phase of rapid expansion, occurring less than a trillionth of a second after the Big Bang, is theorized to have been driven by cosmic inflation. Cosmic inflation posits that the universe expanded at a rate much faster than the speed of light during this brief period. This exponential expansion smoothed out the distribution of energy and matter across the cosmos, laying the groundwork for the uniformity we observe in the cosmic microwave background radiation. It is a concept that challenges our everyday understanding of physics, suggesting that the rules of the cosmic scale can differ vastly from those governing our observable world. As the universe continued to expand and cool, gravity began to sculpt the distribution of matter, pulling particles together to form the first stars and galaxies. These celestial bodies acted as cosmic furnaces, forging heavier elements in their cores and releasing them into space when they died, seeding the cosmos with the building blocks for planets and life. The universe's expansion is not uniform, it is influenced by the distribution of matter and energy, leading to the formation of a web-like structure of galaxies and galaxy clusters interspersed with vast voids. This expansion is still ongoing, with galaxies moving away from us in all directions. The discovery that this expansion is accelerating was a groundbreaking revelation, hinting at the presence of dark energy, a mysterious force that permeates space and exerts a repulsive force, counteracting gravity. The exact nature of dark energy remains one of the most pressing mysteries in cosmology, with researchers striving to understand how it will influence the future evolution of the universe. Formation of atoms and molecules. Delving deeper into the mysteries of the universe, we pivot our attention towards the formation of the very first atoms, a seminal event that marked a turning point in the cosmic narrative. This process, known as recombination, occurred approximately 378,000 years after the Big Bang. Before this epoch, the universe was a hot, dense plasma of electrons, protons, and photons. The temperatures were so extreme that atoms could not form without being immediately torn apart by the rampant energy. As the universe expanded, it cooled down, allowing for the first atoms to emerge. Hydrogen, the simplest and most abundant element in the universe, was the first to form. This element, consisting of just one proton and one electron, marked the dawn of a new era in cosmic history. Helium atoms, slightly more complex with 2 protons, 2 neutrons, and 2 electrons, followed shortly after. These elements laid the foundation for the chemical diversity we observe in the universe today. The formation of these first atoms was a turning point that significantly altered the universe's structure and future evolution. With atoms now stable, they began to gravitate towards each other, slowly building the first stars and galaxies. This era set the stage for the complex chemical processes that would eventually lead to the formation of planets and life itself. Following the monumental formation of the first atoms in the universe, an equally remarkable phenomenon unfolded: the birth of the first molecules. This transition from solitary atoms to the earliest molecules marks a significant chapter in cosmic history, laying the groundwork for the complex chemistry that underpins the universe as we know it. The story of how the first molecules came into existence is not only a testament to the intricacies of the cosmos, but also to the relentless pursuit of knowledge that drives our understanding of it. As the universe continued to expand and cool, conditions gradually became favorable for these freshly formed atoms, primarily hydrogen and helium, to interact in novel ways. Hydrogen, with its single electron, was particularly predisposed to forming bonds with other hydrogen atoms. The emergence of molecular hydrogen, or H2, was a critical step forward. This molecule, though simple in structure, played a pivotal role in the universe's early chemistry. The formation of molecular hydrogen provided the first building blocks for more complex chemical reactions. It acted as a coolant, allowing gas clouds to collapse more efficiently under gravity, which in turn led to the formation of the first stars. These nascent stars were the crucibles in which the first heavy elements were forged, elements that would eventually give rise to the rich chemical tapestry that makes up planets, asteroids, comets, and all living organisms. The exact timing of the first molecules' formation is a subject of ongoing research, but it is believed to have occurred a few 100,000 years after the Big Bang, following closely on the heels of atomic formation. This era set the stage for the intricate interplay of forces that would eventually lead to the universe's structure, from galaxies to planets, and the very essence of life itself. As we trace the cosmic lineage back to its origins, the roles of helium and hydrogen emerge as foundational to the early universe's evolution. These two elements, the simplest and most abundant in the cosmos, were instrumental in shaping the universe from its nascent stages. Their significance cannot be overstated, as they were the primary constituents of the primordial universe, setting the stage for all subsequent astronomical phenomena and the complex chemistry that characterizes the cosmos today. In the aftermath of the Big Bang, the universe was predominantly filled with hydrogen and helium. Hydrogen, being the lightest element with just one proton and one electron, formed the bulk of the matter in the early universe. Helium, slightly heavier with 2 protons and 2 electrons, was the second most abundant element. These elements were crucial for several reasons. First, their simplicity made them the building blocks for all other elements and molecules that would later emerge through nuclear processes within stars. The significance of hydrogen extends beyond its abundance. It played a central role in the formation of the first stars, known as Population 3 stars. These stars were massive, hot, and short-lived, but they were critical for the synthesis of heavier elements through nuclear fusion. As these first stars ended their lives in spectacular supernovae, they seeded the cosmos with heavier elements, which would eventually give rise to new stars, planets, and, ultimately, life as we know it. Helium's role, while less directly involved in chemical complexity, was no less important. Its presence influenced the dynamics of stellar evolution. Stars fuse hydrogen into helium in their cores, a process that releases vast amounts of energy and light. As stars age, they begin to fuse helium into heavier elements, leading to different types of stellar outcomes and contributing to the diversity of astronomical objects we observe today. Moreover, the ratio of hydrogen to helium in the universe provides critical insights into the conditions of the early universe and supports the Big Bang theory. Observations of this primordial helium abundance, along with the cosmic microwave background radiation, offer compelling evidence of the universe's hot, dense beginnings. Cosmic microwave background radiation building. On our journey through the cosmos, where we've uncovered the roles of helium and hydrogen, we arrive at another cornerstone of cosmology, the cosmic microwave background CMB radiation. This phenomenon is essentially the afterglow of the Big Bang, the ancient light that bathes the universe, providing us with a snapshot of the infant cosmos. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, the CMB radiation is a pivotal piece of evidence for the Big Bang theory, offering a window back in time to when the universe was just about 380,000 years old. At this juncture in cosmic history, the universe had cooled sufficiently for electrons and protons to combine and form neutral hydrogen atoms, a process known as recombination. Prior to this, the universe was a plasma of charged particles and photons, light particles, which scattered off each other frequently. However, as the universe expanded and cooled, photons could travel freely without being scattered, leading to the universe becoming transparent. The CMB is the relic of this transition, stretched to microwave wavelengths by the expansion of the universe over billions of years. The significance of the CMB radiation lies not only in its confirmation of the Big Bang theory, but also in the detailed information it provides about the early universe's conditions. The tiny temperature fluctuations within the CMB are particularly revealing. These minute differences in density and temperature are thought to be the seeds from which all the current structures in the universe, such as galaxies and clusters of galaxies, have grown. Measurements of the CMB radiation have led to precise determinations of various fundamental parameters of the universe, including its age, composition, and the rate of its expansion. For instance, the CMB data suggests that the universe is approximately 8 billion years old and composed of about 5 ordinary matter, 25 dark matter, and 70 dark energy. The CMB radiation underpins the Big Bang theory, a pivotal concept in cosmology. The Big Bang theory proposes that the universe originated from an extremely hot and dense state and has been expanding ever since. The CMB radiation is a critical piece of evidence supporting this theory, offering tangible insights into the universe's early moments. The discovery of the CMB radiation in the mid-20th century was a landmark event that provided the first direct observational evidence of the universe's hot, dense beginnings. The CMB's uniformity, with its temperature incredibly uniform across the sky at about 7 Kelvin 270, 45 degrees Celsius, yet punctuated by tiny fluctuations, paints a picture of the early universe S-state. These tiny temperature variations are crucial. They indicate regions of slightly different densities, representing the seeds of all current cosmic structures, from galaxies to clusters of galaxies. The Big Bang Theory predicts that after the initial explosion,